Okay, so it's 8 a.m. Well, here in Perth anyway. So we should get a start. Thank you for joining us at the 2022 End of Year MWA project meeting. My name is Mia Walker and I'm the first session chair for today. Please note that we are recording the talks and they will be made available on the MWA YouTube channel after the meeting. During the talks, we ask all audience members to please keep your microphones muted. If you have any questions, feel free to type them into the chat box at any time. You can also use the raise hand feature of WebEx to ask a question after the talk, and the session chair will call on you when it's your turn to speak. There is also a closed captioning tool on the screen of your device. Just tap the captions button from the core controls if you want to toggle that on or off. As a reminder, we have two prizes for today, these 3D printed MWA beam patterns, which we will happily ship anywhere in the world. One of them you are all in the draw for just being part of this meeting today, and the second one will be awarded to the best presentation from today and tomorrow. We have an exciting lineup of talks ahead of us, so let's get started. I would like to welcome our first speaker for today, the Chair of the MWA Board, Phil Edwards, for an acknowledgement of country.
Thanks, Mia. So I'd like to start by acknowledging the traditional custodians of the lands we meet on today. In my case, here in Marsfield in Sydney, that's the Wallumattagal people, and also to the Wurundjeri Yamaji, the traditional owners and native title holders of the lands the MWA ASCAP and are located on and that the SKO telescope will be built on. I pay my respects to elders and seniors past and present. Last month saw the signing of an Indigenous land use agreement between the Commonwealth Government of Australia and the Wurundjeri Yamaji. And as part of the ILUA, the Wurundjeri have gifted a Wurundjeri name to the telescope site. So what we used to refer to as the MRO now has a dual name, Inyarimana Ilgari Bundara, the CSIRO Murchison Radio Astronomy Observatory. Inyarimana Ilgari Bundara means sharing the sky and stars. A wonderful name suggested by Shakira Whitehurst, a young Wurundjeri woman. Under the terms of the ILUA scientific papers, using telescopes on the site are required to include in their acknowledgement mention of this dual name. So the MWA webpage will be updated in the near future with this, the new words to use. This is a very exciting meeting we have here. I'm going to hand over shortly to Stephen, who's going to give us an update as a project director. And has some exciting news to share with us. And I want to recognise the hard work done by the MWA management team in recent months leading up to the news Stephen will share. Thanks also to the organisers of this meeting. It's wonderful to hear the wonderful work being done by the MWA, and it takes us from the nearest star to the first stars and covers pretty much everything in between. So thanks to those who are giving talks today. Thanks to those who are coming on to listen. And I look forward to a fabulous meeting. And with that, I hand over to Stephen.
Thanks, Phil. Can you hear me okay?
Loud and clear.
All good. All right. I'll attempt to share my screen. Hang on. I'm getting there, I hope. Is that visible?
Perfect.
Yep, no worries.
Excellent. Look, I don't have much in the way of slides. I don't want to overlap with the other updates from the management team on the science front or the engineering or instrument development front. So I just have a very few brief slides. And as Phil has mentioned, I think the main thing I want to convey is the really good news that we are in a position to talk about today, which has been the result of a lot of work over the last, not just over the course of 2022, but all the way back to 2021, as the MWA board went through the process of deciding what the future of the MWA was going to look like and what the phase 3 portion of the MWA operations was going to look like. Basically, by the end of 2021, the non-Australian members of the MWA board had resolved to commit approximately $3.5 million Australian dollars of contributions towards an upgrade of the facility, as well as continued operations. And as we went into 2022, the remaining piece of that funding puzzle was the Australian contributions to phase 3. So over the last few months, we've been through the process within Australia to go through that funding allocation for the post mid-2023 period, and really happy to be able to say that the MWA has been able to retain its Australian operations funding at the same level from the NCRIS program via Astronomy Australia Limited as it has received over the last few years. So that's really good. And in fact, out of the AAL portfolio of astronomy projects, for the period going forward, the MWA was the only one of those funded projects that did not suffer a cut. The overall astronomy budget through AAL will be reduced by around about 20%. So it was an extraordinary result for the MWA to hang on to its flat funding. So that's, I think, a testament to the value that the Australian and international communities see in the MWA, the MWA's value as a precursor for the SKA. It's a recognition of all the great science and engineering that has been done in the name of the MWA. And I think it also shows a commitment from the MWA partners to keep the facility going in the lead up to the SKA. Now that was great news, but it was necessary but not sufficient. The image on this slide is the front page of an economic and social impact assessment that we commissioned through Ernst & Young. It's a really comprehensive report. If you haven't had a look at it, I'd encourage you to do so. It's available from the top page of the MWA website, and it goes through a lot of material and a lot of history of the MWA and what the investments have been like and what the returns have resulted. Also, some pretty interesting benchmarking of the MWA against other similar scale international facilities. And the bottom line of this report was that in order to remain viable for the future, the MWA needed to not just hold on to its current funding, but actually achieve a minimum 10% increment on its current funding to continue to operate. We are in an environment of pretty strongly increasing costs for all of the inputs that go into the MWA, salaries, price of diesel, price of electronics, price of computers, are all pretty strongly increasing. So merely flat funding was not really going to cut it. So we had to achieve a 10% increment on that flat funding in order to remain viable. So I'm, again, really happy to be able to report that the Western Australian state government has committed to providing that additional 10% of the operations budget for phase 3. So the bottom line is we're in pretty good shape. We have the partner commitments for the upgrade and continued operations, and we have a 10% increment on the Australian operations funding. So that allows us to continue for the phase 3 period, which notionally runs from mid-2023 to mid-2028. It's a notional 5-year period that the funding covers. Phase 3 will consist of a number of different things. You've already heard a lot over the last couple of years about MWAX, the new correlator. Been an amazing effort by the team to get MWAX designed and tested and procured, deployed and operational. So MWAX is working really well at the moment. It's operational and is heading towards being fully featured. And I expect others during the course of this meeting will describe the progress on MWAX. MWAX is capable of full 256 tile correlation. So that's going to be the target ambition for phase 3. And that's going to be enabled in the first instance by a fleet of 16 new receivers that have been produced by Shanghai Astronomical Observatory in collaboration with the MWA engineering team at Curtin. This again has been an enormous amount of really excellent collaborative work between those teams, and it's been 2.5 years in the making. So it's really exciting to see the fruits of that collaboration starting to appear. On the bottom right-hand side of this slide is the first receiver that will ship from Shanghai Astronomical Observatory to Curtin, and we expect that first receiver to arrive this month. And then we'll proceed to go through a lot of testing ahead of deployment of 16 receivers starting next year. So that should bring us, we hope, to a state where we will have 128 tiles serviced by these 16 new receivers, and we will do the absolute best we can to keep the existing 16 original receivers in an operational state for as long as possible. As we've flagged for many years, these existing receivers are now a decade plus old. They've operated continuously in the very challenging environment of the Murchison. It's something of a miracle that they're still going, largely speaking. And I think it's enormous credit to the team for having nurtured those complicated bits of electronics and kept them alive for this long. So the goal, having deployed new receivers, will be to maintain as close as possible to a fully correlated 256 tile array for phase 3. Now, obviously, that is a pretty significant step up in the scientific capabilities of the MWA. If you ignore the raw sensitivity of the instrument relative to SKA low, obviously SKA low consists of many more antennas, but a 256 tile correlated array represents only 1/4 of the baselines of SKA low. So SKA low is only, in some dimension, a factor of 4 more complicated than MWA phase 3. So it is going to be an enormous step towards SKA low, and it's going to unlock significant amounts of new scientific capability. So that's extremely exciting. But we're never satisfied. We'd like to go even a bit further than that, and so we do have a number of irons in the fire for additional funding. So we have large proposals for funding that include MWA support pending in both Canada and Japan. and we are about to submit a first stage proposal for a very large amount of money, relatively speaking, to the NSF in the US. The subject of that proposal would be to replace the 16 old receivers. So the goal out of this proposal would be to end up in a state where we have a full 256 tile correlated array, fully populated with a suite of new receivers. And these new receivers have much higher levels of performance compared to the old receivers. And we'll take the opportunity, obviously, to correct a number of the deficiencies in the existing receivers, such that the scientific quality of data coming out of the new system will be far, far better. There's a fair bit of work involved in getting those proposals in. There's quite a long period of time that you have to wait until you know what the outcome is, and the NSF proposal is a multi-stage proposal. So we won't know anything about that until well into the next year. But the point here is that we're continuing to seek additional support to continue to bring the facility up to the highest level of scientific productivity possible. It's worth noting that just this week on Monday, the SKA had its construction commencement ceremony, and this occurred out at Inyarimana Ilgari Bandara, the CSIRO Murchison Radio Astronomy Observatory. And I note this because, well, the MWA has played an absolutely fundamental and central role in the development of SKA low technologies. The photos that you see here are of the so-called aperture array verification system, which is basically an SKA low station architecture utilizing the SKA low antennas, as well as a data transport and signal processing architecture, which is reflective of the SKA system itself. There's going to be one more of these aperture array verification system stations built over the next 12 months, again at the MWA site. And the other photo here is the engineering development array version 2, which is the same architecture as the SKA station, but utilizing MWA antennas. So these prototypes have developed using the MWA infrastructure as the development platform, and many of the people involved in the MWA have been significant contributors to the engineering, software development, as well as the in-field activities that have led to a maturity for the SKA systems that allow the SKA now to go into full construction. So I thought I'd note that because it is obviously a massive milestone for the SKA itself, and the MWA has really fulfilled its obligations as an SKA precursor by making these fundamental contributions towards the development of the technologies. This admits a few interesting things that we could consider. So consider the fact that we will have 2 aperture array verification system stations and 1 engineering development array station. And each of those 3 stations consist of 256 antennas. And if you put those together with a fully correlated 256 tile MWA phase 3, and if you can put all of those signals through the same correlator and correlate all of those things together, you end up with a system that has a raw sensitivity that's roughly equivalent to 19 SKA low stations. So that's equivalent to the sort of what's called AA1, which is one of the deployment milestones for the SKA, which is AA1 is 18 stations. And AA1 would be scheduled to be in place around about, I don't know, 2026, 2027 maybe. So that you can see there's some interesting possibilities here, both for testing in a lot of detail using astronomical tests, the SKA stations, but there may well be some pretty interesting astrophysics that could be considered with a combination of MWA plus 3 SKA stations. So a few of these interesting things emerge from the combination of the MWA and the SKA work. Not a prospect for the near future, I would say, but over the course of the 5-year operations period for phase 3, I think some of these things are going to be pretty interesting to pursue. And then ultimately, by around about middle of 2028, beginning of 2029, as the MWA is reaching the end of its phase 3 operations, we hope that there will be a seamless transition to the SKA low itself, which has a due date for construction completion around about 2029. Again, that's a fair way down the track, and many things can happen in that time. So from the MWA's point of view, we're definitely remaining flexible and dynamic in how we approach the next 5-year period. But at zero level, that's sort of the decade long future that we have in front of us. I'll leave it there, Mia, and happy to take any questions.
Thanks, Stephen. It's definitely very exciting what's on the horizon for the MWA. Do we have any questions? You can put your hand up with the function on the bottom of the WebEx call, or just type them into the chat.
Perfect.
Yes. All right, no worries. Thank you again. We can move on to our Principal Scientist update from Chris Riseley.
Thanks, Mia, and thanks, Stephen. Just got to remember how to drive WebEx. It's been a little while.
No worries.
Hopefully now.
We can see that. Yep.
Excellent. Great. Okay. Well, we are a little bit early, so I've got a little bit of extra time, but that's absolutely fine. In fact, I'm also going to try and keep this relatively short and relatively appetite whetting in terms of the science updates, because this is a very heavily science-focused meeting, and we've got a whole bunch of excellent talks covering the full range of MWA science themes from a great bunch of researchers. So, you know, they're going to give you the full details of all of the science I'm going to touch on, but I will give you sort of a few highlights that I've noticed from papers over the last 6 months or so. Yes, salve, buongiorno, amici. I'm Chris Riseley. I'm your MWA Principal Scientist, and I'm joining you from Bologna in Italy. So I've been in this role for a couple of years now, and so you may have seen a few talks for this for these kind of meeting styles by me. So we like to kick off with papers by the numbers. In the last 6 months or so since the last meeting, we've had 14 new MWA papers accepted and published, and we've got 6 MWA papers currently in collaboration review. Currently undergoing peer review. This brings our new totals to this many papers. which means that we have 299 papers since the in the anno MWA period, since the MWA has been operating. So, you know, who's going to get the 300th MWA paper? We had the 200th relatively recently. In terms of citation statistics, the citation numbers are really ramping up now. We are over 10,000 citations for our MWA collaboration papers and over 2,000 citations for our MWA external papers using public data. In graphical form, this is what it looks like, and you can really see the number of cumulative publications in terms of the external papers are really ramping up to meet the to getting towards the level of collaboration papers, and you can see that these citations are growing very nicely. I've decided this year to put this on a log scale because when it was on a linear y-axis scale, it was just getting a little bit ridiculous. But you can see that the citation rate is really nicely accelerating, and so is our publication rate. And so we're getting into this stage now where we finally crossed the 10,000 citations mark for all of our papers at some point in the last 6 months, which is fantastic. So some high-level science highlights, which I'll try and speak to, but you'll get all the better details from the people actually doing the work in the rest of this meeting. So bear with me. MWA has been making great progress across all of the science working groups, from EOR, GEG, pulsars and fast transients and transients, which for the purposes of this talk, I'm going to smush into one slide because we have a lot of talks from transients and pulsars folks later. And solar, heliospheric, and ionospheric. These are our 5 MWA science working groups, and you will hear more from the people doing the work shortly. So starting off with EOR, one of the papers that caught my eye relatively recently is a paper from Kolopanis et al. They did a reanalysis of the same MWA data presented in Wenyang Li's 2019 paper using a different pipeline. They discover and kind of address a previously unidentified common mode systematic that seems to introduce a negative bias into the data. So as the EOR folks want to do, you know, we are discovering that digging deeper and deeper into the data is revealing new challenges for the detection, including systematics that aren't only positive definite, but can also be negative. And at the lower K modes, the delay spectrum calibration presented by Kolopanis et al. Shows a slight improvement due to reduced bleeding of the coarse band into the EOR window. So check out the paper for more details. It's really interesting. A paper by Trott, who will probably present some results on this shortly, discusses the multi-frequency angular power spectrum as an alternative to the classic spherically averaged power spectrum, an idea which is back to around 2005. The key idea is to essentially preserve K-mode information along the line of sight. And at the moment, the limits from maps are sort of higher than those from the classic spherically averaged power spectrum by about a factor of 3 to 5. But Cathryn collaborators did discuss a number of ideas for improving the technique and getting deeper and more sensitive limits. And finally, another paper that caught my eye was a paper by Karayuki Cheche and collaborators. Been working hard on tackling improvements in ionospheric calibration, sort of the bane of our existence at low frequencies, particularly when you're dealing with such high sensitivity science cases as EOR, and devised an improved recipe for doing so within the RTS framework. And as you can see here in the 2D power spectrum, blue colors denote calibration improvements with the new recipe versus the old recipe. You can see in some particular sections of the EOR window, there is a substantial reduction in the residual power, corresponding to an improvement in sensitivity by around a factor of 2 or so. So in certain modes, Karayuki collaborators are really giving us improvement in the scientific outcomes at the longest and most challenging wavelengths. So big props. On to the GEG. We've got a few talks in this regime coming up, so I'm going to highlight a couple of external papers. So one of the things that we all know and love about the MWA is that it has this fantastic, massive bandwidth. And we have this highly successful legacy survey from phase 1, which is GLEAM, which produced, measurements across very wide bandwidths. And this data has been out in the community for a while, and so people are really getting to grips with the data and conducting these massive broadband studies of galactic and extragalactic objects like supernova remnants, as you see here on the right in a paper by Supan et al., or on the left, a paper by Misalia et al. On a particular radio galaxy. And in the regimes I've highlighted here with these orange boxes is where the GLEAM data comes in. And the MWA is playing a key role in giving precise flux density measurements at low frequencies, which are critical for exploring the underlying physics of these kind of objects. Understanding magnetic fields and particle acceleration and aging mechanisms of these kind of interesting and challenging objects. And these are just a couple of examples using GLEAM, which continues to demonstrate the massive scientific legacy, but also really kind of giving us a teaser of what we in the community at large will achieve with GLEAM-X once that's fully realized, and also, as Stephen has suggested, observations once phase 3 is really completely realized and we're getting correlation of up to 256 tiles. And you can join us after coffee for more talks from Chenoa, Tamsyn, and Kathryn Ross on more exciting news from GG. But just to give you a little bit of a sneak peek, you may remember this plot from my talk at the last project meeting, or from Natasha's paper, showing really the kind of the fantastic impact of effectively phase 1 plus phase 2 MWA, which is kind of where we're going in this, which is kind of what we're going to end up with once phase 3 is fully realized. But to give you a couple of other examples in other environments, sort of from my own kind of field of cluster physics, in an image courtesy of Stéphane Duchesne, where we are working on the well-studied Southern Galaxy cluster Abell 3667. This is a particular double relic system where there's recently been a radio halo detected for the first time with Meerkat, and we're following it up with the MWA using deep data at the lowest frequencies. And using proper image domain gridding with WS cleaning, you can actually get significant improvements over classical stacking. And so this bodes extremely well for this study, which we are still in the process of reducing all the data and folding in the phase 1 data. So stay tuned. And speaking of work by Stéphane, here are some images of, unfortunately, this is not an MWA image, this is a Meerkat image from a recent paper by Rudnick and collaborators. But Stéphane has been working on a project using MWA data, and you can see in the contours on the right-hand figure, this shows the extent of the emission recovered by the MWA, in particular this diffuse sheet down here that is not even detected by LOFAR. So this is a really classic textbook example of the power of IDG on these very large scales, exploring these very faint, low energy particles, particle populations, and the acceleration mechanisms and physics going on there. So stay tuned for that paper as well. Onto transients and PFT. The key thing that's happened in the last few months, we've had absolutely heaps of paper submissions from the pulsars and fast transients working group, including the smart survey description paper, paper on image-based pulsar searches using VCS, and deep single pulse studies with the MWA and UGMRT. So the PFT group are really reaping the rewards of all the work put into making smart a reality, with heaps of discoveries, as mentioned in previous papers in Ramesh's paper. I'm not going to speak to the details here, but you can get the details on all of these in tomorrow's session. Speaking of transients, following up of the first of the GLEAM-X transients from Ray et al. Ray et al. Present the results of a significant simultaneous multi-wavelength follow-up campaign for the first GLEAM-X ultra-long period transient. And despite throwing just about every telescope capable of observing this thing, from radio, optical, near-infrared, and X-ray wavelengths, further observations as recently as January 2022 didn't yield any detections. So really trying to dig into the mysteries of these objects. And speaking of digging into mysteries, there's a great paper by Yajun Tian and collaborators detailing the hunt for 5 known repeating FRBs with MWA VCS data between 2014 and 2020. Unfortunately, no detections were made, but this is really the first time the VCS has been used to carry out this kind of investigation, which provides really the tightest limits yet on MWA on detections of FRBs with the MWA. So it's really cool, exciting stuff. You can join us tomorrow for all this and more from the Pulsars and Fast Transients group, many talks. Natasha Hurley-Walker's talk tomorrow on the latest and greatest news from the hunt for more MWA transients. And also Joan is giving a talk tomorrow as well on this work. So I won't speak to this anymore. Tune in for these talks. On the SHI front, again, we've had absolute reams of solar papers being submitted in the last few months, with 3 papers by Kansabanik and collaborators, 1 paper from Sharma et al. On weak emission from the solar corona, quiet sun detection and analysis by Mondal et al. And using machine learning for detection and characterization of winks. Weak impulsive, I forget the rest of the acronym because it's like 1:30 in the morning, my apologies. Basically, there have been heaps of solar papers coming out of the SHI group. Just to give you a couple of examples of the improvement in calibration. Here you go from just some basic self-cal all through different advanced stages of self-cal to final MWA wavelength images of the sun, which are just a mile away from the initial data quality, and you can get some exquisite data quality out of these pipelines, detailed by Kansabanik et al. I'm a polarization person at heart, so seeing polarized emission, in this case circular polarization from the sun, is also extremely cool to see in one of Kansabanik et al.'s other papers from this year. And you'll see more on the MWA solar results later today in talks from a whole host of excellent scientists. So tune in, seriously tune in, it's going to be amazing. And also on the heliospheric and ionospheric side of things, there's a paper from Angelica Waszewski and collaborators, which has been published, which I mentioned briefly as being submitted in a few months ago, detailing the use of scintillating sources for studying ionospheric scintillation rather than interplanetary scintillation. And Angie will give us all of the details later today as well, so tune in for that talk. So that's about the end of what I wanted to say on the science front. I also wanted to mention some awards that have been awarded in the last few months, because it's something that I touched on in my talk 6 months ago, and I realized we've been getting a few more awards recently, so I wanted to highlight these and say massive congratulations. So firstly, Kat was jointly named WA Science Student of the Year a few months ago for her work on peak spectrum sources. So massive congratulations to Kat. And also recently at the Women in Technology WA Awards, we had massive success from Natasha Hurley-Walker, named Shining Star Award in the STEM Academia and Research category, and our very own project officer, Mia Walker, who was named Shining Star in the category of Sales and Marketing and Business Support for her absolutely integral role in supporting MWA project operations. So well done, Natasha, well done, Mia, and also well done for Kat giving a keynote speech at that conference as well for the Include Her campaign. So as it says at the end of this screenshot, which is taken directly from the MWA website, congratulations to everyone involved. Congratulations, everyone. Really well-deserved recognition for all of your hard work. So to summarize, we've passed 10,000 citations in the last 6 months, which is great. Who's going to submit our 300th MWA paper? It's a competition. I will throw down that gauntlet. Who's going to submit it? Get on it. We've had heaps of science results across the full range of science themes, and tune into the rest of the meeting to get the details from the people who are actually doing the work, not just these high-level summaries from me. And we've had a few awards in the last few months, so big recognition for those who make the MWA the massive success that it is. Congratulations. As Stephen has mentioned, on the road to phase 3, we realizing a full 256 tile array and looking forward to some of the cool things that have been mentioned on the path to SKA. It's a great time to be part of the MWA collaboration, so all eyes are on 2023 for the next set of massive science outcomes. If you want to know more about MWA science or have any queries about policies or data or any of that stuff, then please feel free to email me or get in touch via my socials. And I will say thanks for listening and take questions.
Thank you so much, Chris. I always love your summaries, bringing together all of the incredible outputs from our astronomers. And I'm definitely biased, but I'm sure we're all proud to be such a productive collaboration. We don't have any questions in the chat yet. There's a couple of comments from Natasha applauding some of the beautiful images and the results that you've shown, and that she's always happy to see GLEAM data being put to good use. And I think we can all agree on that.
Absolutely.
Yes. So if there's no hands up, we're a little bit early, but that's okay. I see Kath is online. I will hand over to the next session chair, Ridhima Nanaki, for the EOR session. Thanks, everyone.
Thank you, Mia.
Thanks again, Chris.
Thank you, Mia. Good morning, everyone. Okay, so thank you, Chris and Stephen, for the nice update. So now kicking off with our science, we are going to start with Kat, who's going to give us an overview on the epoch of ionization. So Kat, take it away.
Thank you, Ridhima. Can you see my slides?
Oh, yeah. Can see your slides.
Great, thank you. Good morning, good afternoon, good evening. My name is Kathryn Trott, and I'm the current spokesperson for the Epoch of Reionization collaboration. So I'm going to give a whirlwind tour of some of the results from the past 12 months, including a few that weren't shown by Chris, but there's also some results that we're not showing here. So this is really only a short talk. As Stephen mentioned, and also Phil mentioned, what was previously known as the Murchison Radio Astronomy Observatory has a new name that's been gifted to us by the Puja Majee, and I've put it here in my slides, and I encourage everyone else to use it as much as possible as well. Okay, so just as a reminder, within the MWA membership, the collaboration spans a large number of countries, and I'll be showing results from researchers in a number of these countries today. So just as a reminder for everybody, what we're looking for here are the brightness temperature fluctuations in the 21 centimetre signal from the first billion years of the universe, and specifically from the period between 500 million and 1 billion years after the Big Bang. Those brightness temperature fluctuations encode the astrophysics of the birth of the first sources in the universe, and they tell us about the density field, the ionization of the intergalactic medium, and also the radiation properties of the intergalactic medium. And so there's a wealth of information that we can extract from this signal. However, it is very weak, and it's embedded within a lot of much brighter foregrounds and systematics that are associated with our instrument. And so getting to the actual mapping, the tomography of the 21 centimetre signal is something that we'll be looking to do with the SKA in the future. And with the MWA, we are principally looking at statistical metrics to be able to extract information about this early period of the universe. So globally, there are a number of experiments that are exploring this first billion years of the universe. Some of them are exploring the cosmic dawn, the time of the birth of the first stars at higher redshifts. But the primary interferometers that I'll mention today, LOFAR, HERA and MWA, work between redshifts sort of 6 and 12 nominally, moving all the way towards the end of reionization, which we expect to be at about redshift 5.2 or 5.3. There's a lot of other experiments, smaller ones here that are working in different spaces, but LOFAR, HERA and the MWA are the ones that are primarily doing the power spectrum, the statistical measurement of this period of the universe. LOFAR and the MWA are very similar telescopes. They're general purpose instruments. They are aperture arrays that have mostly non-redundant baselines, but LOFAR also has very long baselines compared with the MWA. HERA is an experiment itself, in the sense that the telescope is designed specifically to do this particular experiment, and it's tuned very much for that. And so it observes the sky in a different way, and therefore there are pros and cons as to what comes out of HERA versus LOFAR and MWA, and this is all really good lessons for us. So over the last 3 years, there's been a suite of results in this statistical metrics kind of space, and I'm just going to place them here without going into too much detail about them, but they span redshift space, and they also span sort of different techniques. And on the right there is the maps that we published this year that Chris mentioned, but I won't speak to anymore. So where's LOFAR? LOFAR produced its last results in 2020. And in fact, in the same week that the MWA collaboration published a paper looking at limits between redshift 6 and 9, LOFAR published some limits at slightly higher redshift at 9.1 from 141 hours of data. And at that redshift, that's a very, very competitive limit. And with that, they were able to exclude some physical models of the early universe that didn't match with the power spectrum. And effectively what happens is when you have a very cold IgM and you ionize it, you get a very high power spectrum signal. And so if we don't observe a very high power spectrum signal, then that can rule out those sort of cold reionization models. The MWA at the same time was able to do a very similar type of astrophysical analysis and rule out very similar parameter space. HERA published some work in 2021, but I really want to talk about the work that they published this year in 2022. And this was a very deep limit at redshift 10.4, so we're now moving it to a higher redshift. And I'll just make the quote from their abstract. The intergalactic medium must have been heated above the adiabatic cooling limit at least as early as redshift 10.4. And interestingly, with these results, what they've been able to do is rule out some much more physically plausible models for the evolution of the early universe. And so we are starting to push into this parameter space where we're nailing down what's happening in the early universe, even if we don't have a detection yet. All right, so here's a suite of new work from the EOR collaboration in no particular order. So Chris already mentioned this, and so I won't go into a lot of detail, but the plot on the right-hand side here that's showing this common mode systematic that Kolopanis et al. Found in the reanalysis of Wenyang Li's phase 2 data. What you're seeing here, and this is a bit of a complicated plot, but this is delay space, and we're looking at particular baseline along LST. And what you would expect to see is that the phase of this signal jumps around a lot, which is what you can see in these sort of modes here. But there are some places, like you see this particular delay mode here, where the phase of that delay spectrum is really constant. It's not varying very much at all. And that's really unphysical. There's something happening in the system there, probably some sort of mutual coupling between on the very short baselines, but that can lead to this negative power spectrum systematic. And so this is now something we need to be really careful of in our analysis, particularly when we're using the short baselines. Mike Walensky, who's a former student of Miguel's at UW, has a paper that he's about to submit using his SINS, which looks for, is a technique to look for RFI in our data and either excise it or just remove that observation altogether. And he's been doing some deep analysis with SINS and looking at the impact on the power spectrum. This plot here is showing that by removing RFI contaminated data, we do better in the EOR window, which is this yellow box that you can see here. But interestingly, we're finding that SINS is not finding everything, and there's some really ultra-faint RFI that SINS cannot detect that is still really affecting our power spectrum. So that's some ongoing work, and that paper will be out soon. Our colleagues at Shanghai Astronomical Observatory, Kathy Zheng and her group, and Kathy gave me this slide, thank you. Kathy's been using the MWA results to try to understand where we should be looking for EOR with SKA low. So we're going to do some deep pointings, and she's using the MWA information to be able to help to design that experiment of the future. And there's also a couple of 2022B proposals that were put forward before that semester from the same group to look at some other interesting ways of accessing the 21 centimetre signal at high redshift. Tepe Minoda, one of our Japanese colleagues, has been doing some more theoretical work to use an independent component analysis to try and take the maps that we have and separate out the foregrounds from the EOR signal. So this is application of some work that had previously been done in intensity mapping at lower redshift. And you can see some early results here where he's making some good inroads into how we can apply that to our data. Nicole Barry, who's a Forrest Fellow here at Curtin University, has made this lovely GIF. And I know that she showed this at the previous project meeting, but she has others that are like this now. And really what you're seeing here is on the horizon, the galaxy coming in and out, and all of these side lobes that you can see coming through are the harmonics of the galaxy. And so even though it's on the horizon and we care about the field in the middle, we do see that contamination all the way through. And so really we need to ensure that we're mapping the whole sky and really treating the whole sky. And of course, we do have pointings where the galaxy is set, and we do find that those pointings behave better in the power spectrum space. Again, a little bit more on the theoretical front, but will be applied to data. This is work from Jaden Cook, who is a PhD student here at Curtin University, along with Brad Gregg and Jack Line. And what he's looking at is the third order statistics. So the skew spectrum, as opposed to the power spectrum, which has different information and different systematics embedded within it. So he's starting with some very large simulations designed for the MWA of the 21 centimetre signal with foregrounds put on top of them to look at the different characteristics of the foregrounds and the 21 centimetre signal in the skew spectrum space. And of course, there's also been a significant amount of effort over the last few years put by Chris Jordan in particular, but also Dev Null on the new calibration software called Hyperdrive. And I'm happy to report that this is close to being ready for public access and public use by the collaboration and beyond that. The direction independent calibration is working really well. It uses the FEE-B model. It uses GLEAM with lobes on top of it for the best sky model that we currently have. It's very simple to use, and the work that Chris and Dev are doing at the moment is getting the ionospheric peeling and also the full peeling working, and that's really close to being working for that public release. Dev's going to talk a little bit more about Hyperdrive and some of the work we've been doing with it, so I won't speak too much more to that, but that's a really significant achievement. So Redeemer, who is our session chair, has been using Hyperdrive to look at a large amount of our data. So these are a few thousand observations of our data, and she has designed 18 independent data quality metrics that have been applied to all of those observations. With the view to trying to identify clusters of different types of observations that we have that have different characteristics, and then looking at what the characteristics of those are in our power spectrum. So that work is ongoing. Again, Dev is going to speak a little bit more to this, so I'm not going to go into a lot more detail about it, but we're expecting to have quite significant results out of this in the next 12 months. So I'll just close by saying that we're looking towards phase 3 for the MWA. We're really excited about the new digital receivers. And even though initially they won't be on all of the tiles, there will be baselines that will be specifically from 2 tiles that have the new receivers. And we're quite excited to have that much cleaner spectral characteristics of the signal and not have those coarse channel harmonics that we see in our data. Moving forward, we'll be using some of the sophisticated end-to-end simulation package that Jack Line has developed called Woden. We're using that quite extensively to be able to put very realistic errors into our data and see how they show up in our power spectrum as a way of really understanding that the methods that we're using are as clean as possible and we're not unnecessarily introducing spectral structure. And I will close there. Thanks, Redeemer.
Thank you, Kat. Any questions? Let me check. Online, there seems to be no questions so far. Okay, just clapping of hands. So no question. We are early on schedule, so feel free to ask any question. Okay, while we are waiting for somebody to raise their hand, I have a question, Kat. So you mentioned that about SINs, like Mike Wilensky is working on a second round of SINs to actually detect faint RFI, and also related to the horizon, the RFIs that we saw on horizon from Nicole. Do you think that the second round of SINs will be able to detect this type of RFIs that are found on the horizon?
That's a good question. I'm not sure that Mike is developing a second version of SINs. What he was finding was, as a function of pointing, the RFI clean data showed systematics that were very characteristic of seeing RFI from the western horizon. So the western pointings were showing more contamination than the eastern pointings, even though these were data sets that SINs had said were all clean. So that's why he's proposing that there is faint RFI that we're seeing from the western horizon looking towards Geraldton, but possibly also Perth, and that was the cause of this particular systematic. But I don't know if there are plans to be able, with SINs, to be able to actually detect that at the moment. I think it is actually very faint.
I see. Okay, thank you, Kat. Okay, given we have no question online, so we'll move to our next speaker, who is Zhenghao, who's going to talk on an end-to-end simulation for scale 1.
Thank you. Can you hear me?
Yes, we can hear you.
And can you see this slide here?
Yes, you can see a slide
Yes.
as well.
Thank you. So I am Zhenghao Zhu from the Shanghai Astronomical Observatory, and I'm glad here today to have the chance to give a report on our work on the simulations for the SKA1 low observations. So when the cosmic microwave background pass through the neutral hydrogen on the epoch realizations, the brightness temperature would be changed due to the hyperfine structure of the neutral hydrogen. So this change on the brightness temperature is called the EOR signal that we want to detect. This is also the main one of the main scientific goal of the SKA low and also the MWA project. Well, however, if we want to detect such a signal, we need first to get rid of the strong foreground as well as all the systematics lying before the signal. So to check if we finally get the correct signal of the correct EOR signal, one of the way is to perform realistic simulations and then do all the pipelines on such simulations, and to see if we can recover the input cosmological 21 centimeter signal. And so this is why we want to do such end-to-end simulations. Now, my report can be divided into 3 parts. The first part, I would like to introduce how we build the sky map implemented by the software FG21 sim, and then simulate the observations using the OSCAR software, and the sky map built in the first section, and finally a little discussion on the simulated result. So the always, of course, the strongest foreground is always the galactic cyclotron emission at the low frequency band. We assume that the cyclotron emission follows a power law distributions, and we take the reprocess the Hamilton map as the reference, and then take the spectral index from the literature that is calculated using the observations on the different frequency band. And then we add the small scale fluctuations using Gaussian random fields whose angular power spectrum is extrapolated from the Hamilton map. The IDEC of the center of our simulation is set to be 0 and -27, which corresponding to a higher galactic latitude. That means the cyclotron, the galactic emission is relatively lower. The figure on the right shows our simulated cyclotron emissions from 110 to the 120 megahertz. And we consider the polarization of the cyclotron emission. The figure here shows the Stokes Q and U component, the fraction of the Stokes Q and U component that is measured by the WMAP 9-year observations. This is a result from the RK band. We just take the fraction and then multiply it to the sky map that get in the previous slide to get our Stokes Q and U component for the cyclotron emission. Now is the galactic free emission. This is implemented already in the FG21 theme. Well, first we have the H alpha survey data, which is collected for the depth observation, and then the free emission can be simply get using the relation between the H alpha and the free emission due to their common origins. As for the extragalactic point source, we use the simulation result from the Wheelman et al. In these simulations, we have 3 types of the point source. One is the star-forming and the starburst galaxies, and the radioquiet agents, and also the FR1 and FR2 agents. The figure on the bottom panel shows the simulated point source from 110 and 120 megahertz. So the last component of the foreground is the radio halo, which is also implemented in the FG21 theme. In brief, we first get the merge history of the galaxy clusters from the PS theory, and then solving the Fokker-Planck equation to get the spectrum of the high energy electrons, and then calculate radiation by assuming some magnetic field. And the result is shown in the top panel of the right figure. And for the EUR signal, we use the data, the public data of the EUS project, who have their own embodied simulations, and then use the 21 centimeter fast to get the result. And this shown on the bottom panel of the right figure for the 110 and to the 120 megahertz. Now we have all the sky maps. We want to do the simulations. Here we adopt the SKA-4 array configurations as well as the antenna response. The SKA low array have 512 stations, and each of the station has 256 the log normal antennas, as illustrated in the figure on the left. For the table on the right shows the anticipated performance for the SKA1 low, and consider the computational source we have in hand. This is the our simulation criteria. We can see that although we are not able to do a full frequency range simulations for the SKA1 low, but our FOV as well as the resolutions are good enough to perform the data analysis. For the instrumental and observational effects, we first add thermal noise. And the noise level is given according to the SKA memo, as shown in the figure on the left. The corresponding integration time is shown on the figure on the right, and the bandwidth is 100 kilohertz. Such thermal noise is this thermal noise level we added is several times to 1 order of magnitude lower than the EOR signal we are using. And apart from the thermal noise, we also consider effect of the ionosphere. We are using a very simple model, a very simple 2-layer model to represent the ionosphere. And one layer is moving at 150 kilometer per hour, and the other is moving at half of the first layer. As we can see in the figure on the right, the value on each pixel corresponding to actually corresponding to a phase change for the signal coming through this certain pixel. Besides the ionosphere, we also add the gain and the phase error for the for each antenna, and such error level will corresponding to an RMS noise that is lower than the thermal noise we are using. Well, given all the sky maps and the observation effects we are considering, we finally have the simulated dirty map. Of course, the OSCAR software only gives the measurement set of the or as its results. These dirty maps are calculated using WSClean, given us using W stacking reader and the breaks weighting. The figure from left to right is the simulated galactic foreground, including cyclotron and free emission. The extragalactic foreground, including the point source and the radio halo. And the right figure shows the simulated EUR signal. Now some discussion of our simulated result. The first one is regarding to the smoothness of the spectrum. Well, as we know that many component separation methods they are relied on the spectral smoothness of the foreground, which is actually it is true for the sky map as shown in the top panel of the right figure. It is a very true spectrum, but it is no longer the case for the dirty map. As shown in the middle panel, we can see the fluctuation of the foreground is comparable to the EUR signal. The fluctuation of the EUR signal shown in the at the bottom panel of the right figure. So that means we need a very good deconvolution method to the dirty map, and then we also need to be very careful when using the spectral smoothness assumption on the real observation data. And another thing is for the EUR window. We can see from the 2-dimensional power spectrum of the top panel, that is for the sky maps. We can see that the power of the EUR inside the EUR window is actually do larger than the foreground component, actually in some area, but this is no longer the case for the dirty maps. That means the using the EUR window alone is not good enough to get the EUR signal. We also need to consider the deconvolution method as well as the component separation method together to get the to detect the EUR signal as we decide And some this is our future plans as for the next step. Well, first we always want to updating the sky map by adding the radio relics, adding other foreground components such as the radio relics, and also updating the EUR simulations as well as the point source simulations by taking the lensing effect into account. And we want to consider more instrumental effects such as the radio frequency interference and also the side lobes. And of course, if we have more computational results, we want to do the simulations with higher resolutions and more frequency range. And finally, we want to we're trying to develop a data calibration pipeline to perform on the simulated measurement set, just to see if we can recover our input 21 centimeter signal. So I will stop here and thanks for listening. Comments are welcome.
Thank you, Zhenghao. Any question online? Okay, I don't see any hands raised. So no question. So let's thank our speakers and Zhenghao again for the nice talk. Thank you.
Thanks.
So our next and last speaker for this session is Null, who's going to talk on systematics and where to find them. And to Dave.
Hey folks, just checking you can hear me.
Yes, we can hear you.
All right, and can you see my slides?
Perfect.
Great.
Yes.
And Redeemer, can you interrupt me if there's any kind of issues with the bandwidth or anything? And I'd be able to turn off my camera just in case we have any bandwidth issues, but it should be okay.
Sure, I'll do that.
Okay, thanks. Hey everyone, my name is Null. My pronouns are they, them, and I'm a software engineer at ICRA Curtin, working with the MWA EUR group, as well as the MWA operations team and the Australian SKA Regional Centre. Before I begin, I'd like to acknowledge the traditional owners of the lands where we meet and operate our telescope. Gulgamanu, aka the MWA, and the Inyaramana Ilgari Bundara, aka the MRO, are on the lands of the Wajju Yamaji people, and I'm coming to you from Boorloo, Perth, which is on the lands of the Whadjuk Noongar people. I pay my respects to their elders past and present and emerging, and extend my deepest gratitudes to the custodians of this land for sharing their sky with us. As we all know, the MWA is an incredible feat of engineering that has provided petabytes of observations for a wide range of science group over the last decade, despite an environment that is not particularly hospitable to our sensitive electronics. Here's a recent example of one of the many encounters we've had with the local fauna. In this instance, tile 107 was in the way of one Campbell's favourite dustbed. The MWA operations team has invested significant effort in building systems to detect and prevent these kinds of issues from impacting the quality of MWA observations. My recent work with the MWA EOR team expands on these systems with advanced statistical and signal processing techniques to detect additional data quality issues. I'm sharing these techniques here because many of them are applicable to other science groups, regardless of the software stack you choose to reduce your data with. For brevity, I'll be using a broad definition of the word systematics, which covers everything from intermittent instrument faults to RFI or data quality issues with unknown sources. I'll be presenting several kinds of systematics that we've uncovered in this work, but I'd like to emphasize that these are rare exceptions which do not represent typical MWA data. It is, however, important to have a good understanding of the kinds of data quality issues that you might encounter so that you can ensure you have mitigations in place. The work presented in this talk is the culmination of efforts from a long list of people, but I'd especially like to highlight contributions of the MWA EOR pipeline team. The problem of detecting systematics in radio astronomy signal chains is nothing new. especially within the EOR group. This is something that Trott and others in the EOR collaboration have been working on for quite some time. Things really kicked off for us when Redeem and Anarchy joined us earlier this year, implementing several advanced statistical and signal processing techniques that have been instrumental in this recent work. While this was happening, Chris Jordan was battling the dragons of direction-dependent calibration that I talked about in the last project meeting, and I'm glad to announce that we've recently emerged victorious against one of those dragons. The details on ionospheric subtraction will be coming to a future release of Hyperdrive very soon. My job was to connect the dots with a pipeline that would handle the intricacies of gathering large volumes of observations from the MWA archive, processing these through various QA stages, and wrangling the data into Pawsey's Acacia object store for convenient upstream processing. We've been able to apply these QA techniques to thousands of MWA EOR observations in a relatively short window, thanks in no small part to the flexibility of Nextflow and Chris Jordan's tireless work on improving the performance and reliability of the Hyperdrive calibration suite. Here's an overview of a typical MWA visibility signal chain, some potential sources of systematics, and I'll go through the strategies used by the monitor and control system to detect systematics, as well as some strategies, some new strategies that we've added with the MWA EOR pipeline. So we've already talked a bit about the damage that local fauna can inflict on our dipoles, but the cables going to the receiver and the fibers going to the correlator are also subject to extreme environmental conditions. The M&C is constantly collecting various kinds of telemetry like PPDs and temperature from all corners of the instrument. A test is scheduled at the start of each day showing the power received when enabling one dipole at a time in the beamformer. There's also a pipeline to generate direction-independent calibration solutions for calibrator observations. These test results are made available to everyone through web services and are used to inform which tiles need attention from the team on site. We'll show that RMS analysis of autocorrelations is a great way of finding badly behaved tiles that might not get picked up by these processes. We'll also show that we can improve calibration accuracy by calibrating observations directly with 4,000 sources instead of using a single calibrator. Calibrating this way with this many sources used to be prohibitively expensive, but thanks to Hyperdrive, which makes use of CUDA, that is no longer the case if you have a GPU. Despite being in one of the world's best radio quiet zones, the MWA is so sensitive that it can detect radio interference from hundreds of kilometers away. AOFlagger does a pretty good job of detecting some of this RFI, and the flag files it produces are made available through ASVO for most observations. We found that SINs can detect some of the faint RFI that isn't detected by AOFlagger, but as you'll see, there's plenty of RFI that isn't detected by either tool, which is why we have to move on to more advanced methods that we'll talk about in detail later. RFI can of course leave its mark in calibration solutions, but we also see it in images and delay spectra. For completeness, I'll show some examples from the very early days of the legacy correlator system where the receiver could sometimes be configured incorrectly. This might seem a little unfair to focus on bugs that we fixed a long time ago, but observations from these early days are still relevant to science and are being looked at on a regular basis. As I mentioned, there are several useful diagnostic tools available on MWA web services. Some of these make use of something called a PPD. Basically, that's the integrated power seen by inch input to the receiver on all channels. From web services, you can get a plot of the median PPD over all tiles grouped over each 12-hour interval. You can also get the PPD for each PPD plot for each tile. This is a movie of the PPDs for each night over several consecutive days. So you can also obtain the results of each day's dipole tests. This is a movie of the dipole tests for one tile that would sometimes be fine, but other times had issues. We're still not sure exactly what's wrong with this tile, but it's now been flagged, so it won't cause any issues for you. There's a wealth of information to be found in these in the results of the calibrator pipeline. We'll get into how to interpret these later as well. Let's talk about some of the diagnostic tools that we've used in this work. If we take the autocorrelation visibility values, throwing away any tiles, channels, and time steps that we would normally flag based on the information from the metadata database or metafits, then plot the RMS amplitude of each tile at each frequency, then we get something that looks like this when everything is going okay. These are a bit like taking a slice out of the PPD plots you can get from web services, but with extra steps on the signal chain like polyphase, like the polyphase filter bank and fine channelization. What we're looking for are tiles that are much louder or quieter than the others, as we found that these can sometimes cause issues later in analysis. And that's what these outliers look like. You might also see discontinuities between coarse channels, which indicates a discrepancy between the digital gains provided in the metafits and those actually used by the receiver. These discontinuities shouldn't be a big concern if you're calibrating each channel independently, like Hyperdrive does. But if you're doing any kind of spectral regularization of calibration solutions across coarse channel boundaries, you might want to look out for these. Here's an example of a range of observations where some unflagged tiles appear to be flatlining, and others appear much brighter than the rest. When we try and image these, we find that we get better results when we flag out the outlier tiles. If we want to find these tiles automatically, we can gather the total RMS for each tile and flag any tiles with an RMS more than 3 sigma outside the mean. Those circles there are tiles that Redeemer's QA script has managed to find where they've been flatlining or have been too loud. We do expect some variance in the amplitudes of tiles, especially between different cable flavors. So you might want to adjust this threshold if you're getting too many false positives. What's weird is that these flat lines look fine on the PPDs, which indicates that the problem might be somewhere after the coarse channelizer. Another important diagnostic tool is the calibration solutions plot. This shows us how the phases and gains of change over frequency for each antenna and polarization. Hyperdrive can generate these plots for many different calibration solution formats. If the calibration went well, we could usually end up with nice flat phases, phase ramps, and flat but fuzzy gain curves. The red and the blue lines are the YY and XX polarizations, and if a tile is already flagged or a solution could not be found, it'll show up as gray. So in this example, we've gone ahead and flagged any tiles that failed the auto RMS test. But other diagnostics that I'll get into later are showing that there's still something wrong. A close inspection of the calibration solution shows that tiles 27, 41, and 42 are not calibrating well, based on the weird oscillating phases and how their gains are completely blown out. On the left, I've highlighted the auto RMS of these tiles in yellow, and they look fine. Yet when we flag these out, we get much better results. But how would you automate detecting something like this? Redeemer found that you could easily spot these antennas in a plot of the variance of the gain of each antenna's calibration solution over all frequencies. This tactic has been used to find all kinds of tiles that would otherwise have impacted our results. Here's an example we found that was probably a fault in one of the fibers going from receiver 4. Remember that there are 3 fibers going from each receiver to the correlator, carrying 8 coarse channels each. Another example found a test observation that accidentally ended up in our collection, where a single dipole called RFI pole was connected up with all the others. Thankfully, this test was able to find this issue. Another powerful diagnostic tool is imaging. Here we're looking at the images of 3 polarizations, XX, YY, and Stokes V. Positive flux is colored in red and negative flux is colored in blue. Redeemer's QA metrics makes use of these images to measure various different polarimetric properties that we can use for further QA. What we noticed when we did this is that some images would have these weird stripes floating across them, but only in one polarization. To figure out what was going on, we had to zoom out a little bit. This is the same set of observations, but we've changed the imaging settings to look at the entire sky. Now we can see the source of this striping. So what you can see is there's 2 RFI sources on the southern hemisphere, and you can kind of see like some stripes emanating out from them. This is because these are only showing up in the XX polarization because the RFI is the XX polarization is more sensitive to RFI in the northern southern hemispheres because that's because this polarization has a greater collecting area as it's facing because the broadside is facing the source of the emission. We can see a similar effect happen on the western horizon, which is the right of this image, where the galactic plane is setting. This is only picked up in the YY and a little bit in the V, because, and you can also see that the galactic plane is kind of echoing through the image. There's a lot more that I wanted to talk about here. Dr. John Morgan and Dr. Samuel McSweeney have been helping with a thanks, Mia, have been helping with this a way of detecting this RFI by looking at each angle. Sorry, but I had to leave. This was probably going to have to be another talk because there is so much ongoing work going with this. So another thing you can do with images is stack them together. Here I've imaged groups of observations from the same night together because we haven't, because we haven't deconvolved, we get a lot of image leakage into QU and V and XY. There's a lot going on here, but the main takeaway is that there's a lot of movement in the diffuse structure that we wouldn't expect from galactic synchrotron emission alone. This is an area of ongoing investigation, but we think that the XY phase calibration might be needed to help straighten things out. Now, this wouldn't be an EOR talk without mentioning power spectra, so I'll do my best to give a quick overview on how these work in the context of using them for diagnostics. If you've done imaging, you may be familiar with the fact that a dirty image at a given frequency is the 2D spatial Fourier transform of gridded visibilities. If instead you take a Fourier transform along frequency and sprinkle in a little cosmology, what you end up with is a power spectrum. Power spectra are an important tool in EOR science as they contain a lot of information about the spectral structure containing visibilities. The problem is you don't get the same granularity as you do with the other diagnostic tools I mentioned, because you need to gather several observations together to get good UV coverage. An alternative to power spectra is the delay spectra. Instead of gridding in UV space, a delay spectra grids visibilities by baseline length. This gives us the ability to compare the spectral structure of individual images. It's also much faster to compute. This is another way that we can see RFI that doesn't show up in those all-sky images. And the plots for this range of observations shows that we still have a lot of work to do in detecting this RFI. Thanks to Jack Lyon for providing the code for these plots. So there's a couple of key things that we've used to design this pipeline. The most important principle, I think, is to automate everything. So that's why you see a lot of these plots where I've been able to turn them into a video. I did this by using FFmpeg as one of the last stages in the pipeline, just to gather every plot that we do for every observation and just turn them into a movie. This is really cool because you get this kind of extra dimension to your data where you are able to compare previous time steps with the next. You can't really get the same thing by looking at a plot that a 2D plot that would be suitable for printing in a paper or something. But it does give you a lot of insight, a lot of extra insight. I'm not a farmer or particularly fond of the meat industry, but I really like the idiom cattle, not pets. So if you need to manually tweak individual observations, that's a great opportunity to find out what these observations have in common that causes you to need to tweak them, and automate the fixes in just a more general way. Another really important key part of our philosophy was modular reusable components. So these are, if you design your pipeline, instead of having a single monolithic job that does everything, if you instead break that up into smaller components, you're able to change the resources of the job in a more granular way that allows you to get more advantageous scheduling. So it's much easier to schedule multiple small jobs in the Slurm queue when you're kind of competing with others for use on the supercomputer. It's much easier to get your jobs to run earlier if you break them up into smaller jobs instead of having one big monolithic job. It also means that when one job fails, instead of if a job fails, if a part of a monolithic job fails right at the end of the monolith, then it's going to be harder to handle those errors. You're not going to know which part of the pipeline failed. So this also gives you better error handling. And another thing is you can't make any assumptions about the dimensions of your data. As we add more and more receivers, we're going to have between 10,000 and 32,000 baselines. So things are going to, that means that jobs can take, a factor of three or four times longer, depending on if it's a new observation, a future observation, or a current observation. This is a quick overview of the components of the pipeline. I know it's too small to see the individual jobs, but I'm just wanting to kind of reinforce this philosophy of breaking things down. Like almost each of these processing components that you see in yellow is almost like one line of the equivalent of one line in like a monolithic job. So breaking these up into smaller components allows you to cache the intermediate products between jobs. And it's also allows you to restart, from further on in the pipeline if a job fails. So we were able to achieve all of this, I think, thanks to Nextflow. Like I cannot understate how amazing it has been to use Nextflow. If you take anything from this presentation, you should look into Nextflow because it can really change the way that you do HPC. There's so many advantages of Nextflow. It runs on anything. It abstracts away your execution so that you can either do it, run Singularity on an HPC machine, or you just run it on your laptop for testing. So we used every component that we made that involved Python dependencies or things like that. We made Docker images of these components so that we wouldn't have to worry about installing all of the pipeline, all of the dependencies on the each system that we ran it on. And we were able to run this pipeline on multiple different clusters. This also means that your jobs are idempotent. So that means that if you run it, each time you run it, you're going to get the same outcome. Whereas sometimes your dependencies might get updated on the supercomputer, and otherwise you might actually end up, having a slightly different result when you run the same job. All right, so I'll stop it there. Thanks for coming to my talk, and thanks again to everyone who contributed either directly or by sharing your expertise with me. I picked a lot of people's brains to figure this stuff out. If you don't got an opportunity to ask your question now, my email is open and I'd love to hear from you. Thank you.
Thank you, Dave, for such a nice talk. And I like the way you put it. It's very important to break down our pipeline, and it's very helpful in investigating systematics that are present in our data. And of course, your fascinating movies.
Thanks for doing that.
Thank you so much. Let's see if you have questions online. Right, no hands are raised. Your talk seems to be very clear. Let's see, Natasha is saying something. I raise my hand. Yes, Natasha, you can go ahead if you have a question.
Yeah, thanks. Thanks, Steph. That was very cool. And sorry if I'm a little bit out of it. I'm just recovering from COVID. I did raise my hand, by the way, so I'm not sure if maybe the icon is very small. Anyway, could you go back to the plot with the Q and U of the and V of the diffuse sky structure varying quite rapidly? Yeah, this one. So Q and U, so this large scale structure is pretty close by in our galaxy. So the rotation measure is going to be relatively low. And so the, Q and U are a function of frequency. There's still going to be some rotation measure. So you're going to get some oscillation with frequency. So I guess my question, which is, are these like a single channel? And then I have a comment / question, which is, if they're very low RM, the ionosphere will be also changing that RM. So have you thought about, could this just be the effect of the ionosphere rotation measure?
Yeah. So these images are, what I've done is I used the number of channels as 24. So WS Clean made these images. I used 24 channels and then combined them. WS Clean combines them together. I've used Briggs +1, I think, weighting on this one. So to highlight the diffuse structure instead of the point sources. And yes, the rotation measures are something that I'm very new to me. And I'm not sure if I can. I know that there's a lot of effects, like you have Faraday rotation in the ionosphere and those kind of things, and those could explain some of this stuff. But yes, I think that's a little bit above me. I think I'm still kind of researching this stuff, and but I'm happy to share these videos with you as well. If you want to have a look at these, because it's really fascinating stuff. Like I'm not going to pretend to understand all the stuff that's happening in this.
Yeah, no worries. What I think could be happening is, if you've just stacked Q and U, we've just added all the frequencies together, then you're essentially imaging a rotation measure of 0. And then that's going to be very local media, but the ionosphere will shift the RM of that, like positive and negative. So in each image, you're actually imaging, say, rotation measure 1, rotation measure -1, rotation measure +2, rotation measure 0. And you're just sort of scanning through the local ISM. I'd love it if someone with more polarization experience than I can weigh in on that, but I suspect that's what's happening here. Anyway, I'd love to talk about it more offline.
Cool.
Okay.
We had a question pop up in the chat, but I couldn't see it because I don't have.
Right, I can read it for you, Dave. So
Cool.
It's not really a question. I think it's from Bradley Mayers. So he says, not really a question that needs to be answered online, but I hope that the goal of these kinds of pipeline or test suits is to run it on all of the MWA calibrator observation, etc. I can see it being useful for other teams to have this information available even before they actually start processing their own data.
Yeah, that's something that would be really interesting to do. It's certainly the pipeline is certainly capable of. I've run it on all kinds of observation at different frequencies. The only thing that it doesn't work on now at the moment is when you have a non-contiguous coarse channel calibrate. So I know a lot of the calibrated observations have gaps in the coarse channels. That's something that we're working towards, though. Yeah, it would be really cool to run this on, all the calibrator observations and see what pops out, because those are not particularly large observations, and yeah, it'd be really interesting.
Okay, thank you, Dave. We have a question from Nicole. So Nicole, you can go ahead.
Yeah, hi. Not necessarily a question, but just a comment on the flipping of the images. Since Ruby Byrne isn't online, her diffuse mapping work showed that the diffuse structure was not stable unless you corrected for that XY phase. And that's also going off some of MWAX work in 2017. So the rotation measure certainly can be an aspect, but I think before we make those claims, we have to fix that XY phase.
Yeah. I'm still yet to make it through, you know, a couple of those papers that you've sent me on that topic, but that's definitely what we're going to be looking into in the future. The XY phase cal. It sounds like that's the culprit behind a lot of this.
You have too many things to do at the moment.
Exactly.
We're oversubscribing you for sure.
Okay, and right. So, okay, any more question? We still have time. We are ahead of our schedule. So, any other question? Yeah, we have few comments on the polarization issue on the chat. If you want to read it, you can just check it from Natasha and
I can't read them,
Chris.
but if there is a question there, definitely let me know. I can only see the little preview pop up while I'm sharing, so probably just stop sharing.
Yeah, I think there's no question. It's only some comment that from Natasha about the XY phase. So not yeah. So she says, yeah, we always fix the XY phase in GLEAM-X pipeline. So I forget that not everyone is doing that. Right. Okay. So let's last check if we have hands raised. No hands raised. So thank you, Dave, again. And thank you to all the speakers of this session. And since we are ahead of schedule, so we have a long break and we're going to meet again here at 10 a.m. for the next session. Thank you again, everyone, for your presence and to our awesome speakers.
Okay, I think we can begin our talking. Hi, everyone. I am Aileen Wang, a PhD student from Shanghai Astronomical. I'm very honored to have the opportunity to serve the MWA. Next, Chenoa will introduce the GEG session overview. Welcome, Chenoa.
Thank you. Hi, everybody. I am the chair of the MWA Galactic and Extragalactic Science Working Group. And so I'm going to give a bit of an update on some of the results that we've had this year and some of the ongoing projects. So the GEG science group is actually broken up into 6 different science teams, and we cover a wide variety of different topics and different sciences. And so I'm going to give a brief overview of some of the work that's going for each of these teams. Over the last year, because I didn't provide an update 6 months ago, there have been 19 GEG related publications in 2022, and 5 publications were using proprietary data. And as you can see here in the bar graph, that there's been a broad span of science as well. To start off with the spectral line group, one of the major advances, I guess, in the last year has been that axions, dark matter particles, might be best found at lower radio frequencies. And so there's been a huge push to use both MWA and LOFAR to do this work. And there's a couple different projects that are ongoing with this, including some other projects that are going to be coming up. And I've been working with a PhD student in Amsterdam for the last couple of years. That is work that's continuing as well. There's a couple of projects now with the MWA to look for high redshifted H1 in various different sources that have been selected through GLEAM or other catalogs.
We're continuing to do some SETI work. In particular, we published this year some SETI work towards the galactic center at 150 megahertz. And then there's radio recombination line work that comes and goes as well. Recently, well, in February, I moved to the United States, and as part of that, there was a tremendous amount of interest to actually hear more about the MWA. So I have given a number of talks, been on a number of YouTube podcasts, and had some articles that were written as well. And it's been an interesting development because people don't know the MWA as well here, and there has been some interest to understand more about how do you access data, and I've been working with some of the teams for some of that. As part of our ongoing publications for SETI, and I believe also Danny will be talking about some new work that will be emerging for MWA and SETI in the future. We've been doing a number of different surveys to try to set limits on the low frequency side because there hasn't been much work in this phase space. There's a recent PhD student that started working on some low frequency using the GLOW station, which is the German LOFAR station. But still, this is fairly new and emerging. For the MWA H1, for some of the work that is being led by Nick Seymour, they've been looking for this high redshifted H1 and have been awarded additional time to continue to look for this, and they're getting quite low limits, and they're very excited about what are the prospects of this work going forward in the future. And in particular, a former summer student, which will be a future PhD student, will continue to work on this. And I think this will be particularly exciting with some of the new correlator modes. For radio galaxies, so some exciting stuff has been that Kathryn Ross finished her PhD thesis on understanding the nature of variable sources with the MWA, and Ben Quincy, if not submitted already, will be very shortly submitting his PhD thesis also on MWA stuff on forging a new statistical understanding of dying radio galaxies. So very exciting for them and exciting for the MWA to have more PhD students that have finished with MW work and go out as postdocs. Nick and Jess have been continuing to work on their high redshift stuff and have been awarded time on other telescopes to do follow-up on these sources. The GLEAM source follow-up work being led also by Jess on doing with some LOFAR as well. Sarah White, who had published the GLEAM-4 sample a while ago, has been working very hard on some follow-up for those observations, including now has a PhD student that is also helping her with that follow-up. Sorry. And as Chris has already mentioned, there were a number of prizes awarded to people that have been doing GEG work over the last year, which is very exciting as well. The Anne Green Prize for the significant accomplishment by a mid-career astronomer that went to Natasha for her work on GLEAM. The VLA Sky Survey, Kathryn Ross gave a very nice presentation on MW work and synergies with VLA, and a Student Scientist of the Year for WA's Premier also went to Kat for her MWA work. For the Forjansky follow-up that's being done on Meerkat of MWA sources, this is some work that Sarah White and a PhD student have been working on. And she's been leading a lot of this work on radiomorphology or densities of the mid-infrared sources, which made it difficult to identify the correct host galaxies originally. With the Meerkat snapshot images of 6 to 7 arcsecond resolution, they reveal these beautiful morphologies, such as this Z-shaped radio galaxy in the left-hand image. Its helical or corkscrew-like structure can be explained by the idea of a radio jet axis that is being perturbed by some external force, leading to a precession. On the right, their student is also comparing the positional offsets between the brightness-weighted center of the radio emission and the position of the host galaxy. The red data points represent previous identification. The blue data points represent new identifications via Meerkat. But also note that the scales are linear within the black square, but switch to log scale after that. As they followed up with the more unusual source morphologies, it is unsurprising the host galaxy identifications show a more pronounced offset than we had seen for the remainder of the sample. This demonstrates a degree of error that could be multi-wavelength analysis if users simply cross-match catalogs based on radio positions rather than host galaxy positions. Some other work that's being done was one of the papers published this year by Ben Quincy, and this was a paper I found particularly interesting. And to highlight some of this results, they had investigated a new technique to constrain the energetics of remnant radio galaxies based on the backflow of their low plasma. This work used a global set of telescopes across a wide range of frequencies, including the MWA, to observe radio galaxy J2253-34. From this work, they proposed two new attributes to quantify the aging of low plasma, including how much the backflow approaches the core and the surface brightness of the lobe near the core relative to the peak brightness. They also develop a publicly available Python package called SynchroFit to fit models to radio data, which they encourage people to start using. Some other work in the radio galaxy group, there's a continuation of these, looking for these extremely high redshifted sources and some mid redshift source. And in Broderick et al. 2022, they defined a sample of 53 high redshifted radio galaxies candidates using a new selection technique based on spectral steepness and curvature in GLEAM. This sample includes the team's Z equals 5.55 discovery, GLEAM J0856 from their pilot study, which was also previously published in 2020. They followed up the same with the VLT using near-infrared K-band imaging to detect the host galaxy and each radio source. And the results of this observing campaign are shown in the figure, where 150 megahertz radio flux density has been plotted as a function of the K-band flux density for Broderick et al. Sample, which is currently known as about Z equals 3, or through Z greater than 3 radio galaxy. The key point of interest from the plots is that the 9 sources from Broderick et al. Sample enclosed in the blue box. These prime targets are particularly interesting because they have very faint K-band flux densities, and in most cases, extreme radio and near-infrared flux densities of greater 10 to the 5. Thus, their properties are similar to the 3 known Z is greater than 5 powerful radio galaxies, as well as another powerful radio galaxy at Z equals 4.88. So they've had ALMA time, and they're looking forward to observing these in more detail. For polarimetry, Zhang has been working very hard on finishing up the initial work for the MWAX. MWAX was a survey that was done in Auxiliary to GLEAM, mostly led by Chris Riseley, and Zhang has been taking over this MWAX and particularly working on finishing up the first field, which was the release of the GLEAM-X continuum. She's actively working on this catalog and has found some very interesting results so far. And here's an example image of some of this work she has done. In particular, she is finding M-dwarf detected MWAX sources, as shown as one example here. Now, this is a source that was found in over 8 continuous channel 169 GLEAM-X observations, as shown in the light curve. Each data point represents a 2-minute channel 169 observation, but GLEAM-X was looping through multiple bands and they didn't see the flares in other bands. They have gotten observations 40 hours on ATCA. They haven't had a chance to process that data yet, but they're hoping that they can detect the flare again as well. For nearby galaxies, the most major piece of work was something that's in publication or in review at the moment, and it's this work by Tetsumo. And in this paper, The authors study 18 star-forming galaxies and study the low-frequency emission correlation and infrared changes over the 20 frequency bands in GLEAM, and they focus on the radio to infrared ratio, determined that the emission from the MWA frequencies up to 1500 megahertz follows a single power law model and found a slope consistent with previous work. They conclude that their results are promising on the small sample, but a larger GLEAM-X and RAC sample will allow them to draw even better conclusions. For the galaxies and cosmic web, a few of these things have already been brought up by Chris Riseley, where they've been working on this active imaging of Abell 3667 and doing the joint deconvolution with phase 1 and phase 2 data. There's also Dan Hu from that has gotten some nice mosaics of her diffuse radio sources and groups, as well as some other joint deconvolution tests that are going on. There was another study by Mohini, which is studying diffuse radio emissions from a sample of galaxy clusters having well-resolved Amy and Planck data. And here's some example images of some of her work here. They're trying to find some non-thermal emissions in the clusters having well-resolved Amy and Planck data. Here are some of the results from the MWA for the clusters processed so far. And the green squares at the center of the images are clustered core positions identified from Amy radio telescope. And the X's and plus symbols indicate the radio galaxies in the line of sight identified using Amy. Some clusters do not show diffuse non-thermal emission at the cores, but this needs further investigation. For galactic continuum, there are some exciting upcoming projects, as well as some other stuff that has been recently finished off. So Hongchen Su's thesis for mapping the galaxy in 3D using observations of H2 regions was accepted for graduation recently. And the data that Natasha will be talking about for the transient survey, she also put to use in combining in the continuum, and has a PhD student that's working on the supernova remnants. And so we look forward to seeing how those results play out. And then for surveys, there are 3 projects that are kind of led by GEG members, even though some of them are large projects that are observatory projects. GLEAM-X will be coming up soon. Gold and the Midas survey should be getting underway fairly soon. That's everything for me. Feel free to reach out if I don't get a chance to answer questions today. Thank you very much.
Thank you, Chenoa. Very impressed talking. Any hands up? Oh, any hands up? Okay, I check it. Okay, Natasha have a question in the chat. New PhD is Sylvia. Who's there? Okay. Yeah, Taiwan has a question. Please go on.
Chenoa, there's a slight switch is fast. That I didn't follow the progress on the high redshift galaxy H1 absorption. Can you repeat it, or can you explain the
Yeah, so
the slide that is H1 absorption. Yeah, exactly there.
Yeah, so I think this is work that's being led by Nick and a few others as part of this. I think that this was one of the examples that they have generated so far, processing some data, and they've working on finalizing a pipeline and started. I think they have a source selection and already have some data and have been awarded more data for this type of work. I don't have much more of an update than that. This is what Nick has given me.
Okay, thank you.
Okay, if there are no more questions, okay, we have to move on to the next speaker. Thanks, Chenoa. Thank you very much. So, Tamsyn will bring his presentation of refining the 200 MHz local radio luminosity function. Hey, Tamsyn, are you here?
Yep, can you hear me okay?
Oh, yeah, sorry, it's she.
That's okay. I'll just share my screen. Can you see my slides okay?
Yeah, it's perfect.
Great. Okay, well, hello everybody. I'm Tamsyn and I'm currently a master's student at UWA, but I'm not going to be talking about my master's project today. Instead, I'm going to be talking about some work that I started back when I was a summer student with Nick Seymour at Curtin, which is refining the 200 MHz local radio luminosity function. So I'll start with a bit of background on radio galaxies. So for our study, we've split our sources into star-forming galaxies and active galactic nuclei. And the radio emission from both of these comes from synchrotron emission. However, the synchrotron emission has a very different origin for the two. So in star-forming galaxies, this is from cosmic rays being accelerated by supernova shocks, gyrating in the large-scale galactic magnetic fields. On the other hand, for AGN, it's from the relativistic charged particles in jets accelerating from close to the accretion disk around the supermassive black holes. And this radio emission off extends well beyond the host galaxy in extended lobes, as you can see in this image here. So the local radio luminosity function is the number density of radio galaxies per luminosity bin at 200 MHz in our case. And it's really important because an accurate measure of the local luminosity function is a basic prerequisite to studying the evolution of a population of sources. So previously, the local radio luminosity function has been well studied at 1.4 GHz, but for our purposes, we've been building off the work of Franz and al. 2021, who studied the luminosity function at 200 MHz. Lowering the frequency to 200 MHz allows radio loud AGN to be selected independently of the orientation of the jet axis. And low frequency surveys can also reveal past activity that's not evident at the high frequencies. Our data primarily made use of the GLEAM-60FGS catalogue that was created by Franz and al. I'm sure everybody here knows that GLEAM was done with MWA, and this catalogue uses a combination of the extragalactic data release and the South Galactic Pole data release. And then this was cross-matched with 60FGS, which is a spectroscopic survey. Additionally, we've also used some RACS data, so that's the Rapid ASCAP Continuum Survey, and we're using data release 1. And we use that to do the look at radio morphology of the sources for classification purposes. And we've also used a couple of infrared surveys, so that's including IRAS and WISE. There are 4 key things that we've done differently to previous studies. Firstly, we've imposed a stricter upper redshift limit of 0.1, whereas previous studies were using 0.3. We've also included 3 groups of previously excluded sources, so what we've called our A-team radio sources, the Magellanic Clouds, and some sources from the GLEAM or Jansky survey. We've also introduced 2 new methods of classification, so determining whether our radio sources are star-forming galaxies or AGN. So in addition to the optical spectral lines, we've also using the radio morphology and the far infrared radio correlation to confirm or refine that radio source classification. And finally, we are using a different method to calculate the radio luminosity function, and that is the method of Page and Carrera. So our first difference was that new upper redshift limit. So in the GLEAM-60FGF catalogue that we're using from Franz and al., we've got 1,590 sources going all the way up to a redshift of 0.3. When we cut our redshift off at 0.1, we are left with 1,220 sources. And we're using this smaller redshift range because the radioluminosity function is known to evolve rapidly over time. So by using a lower maximum redshift, the local radioluminosity function that is produced will give us a more accurate representation of the present epoch. Next, we've got our additional sources. So first up are the A-team sources. These are 4 bright, very well studied radio loud AGN. And we do this to ensure that we're still able to sample the bright end of the radio luminosity function, despite decreasing our survey volume to that lower redshift limit. Next up, we've got the Magellanic Clouds. These are both star-forming galaxies, and similarly, they provide additional data, but for the low luminosity end of the radio luminosity function. And then finally, we've got 15 additional sources from the GLEAM-Jansky survey. 2 of these are star-forming galaxies, and the other 13 are AGN. So when the GLEAM 60FGS catalogue was created, a 50 arcsecond cross-match radius was used, but that missed some of these more extended sources, which is why we've included them back in here. Our next change was to the method of classification. So the previous study relied on the optical spectral lines to classify the radio galaxies into star-forming galaxies, or one of these 3 types of AGN shown here. This method works pretty well. However, a source's optical spectrum is not necessarily directly correlated to its radio properties. So, for example, it's possible that you could have a radio loud AGN with a low accretion rate having a host with optical emission lines that are dominated by the indicators of star-forming galaxies. So this is why we thought it was pretty important that we check the classification with some other methods. So consequently, we let the classification by the optical spectra remain as long as it was not contradicted by either of the next 2 methods. So next up is the radio morphology. So we were using the WAX images to examine this. And we came up with 12 different categories here. So if the source was compact, extended, or lacked data, so that's that first column here, then we left the optical spectral classification alone. However, if it was in one or more of the AGN categories, then if needed, the classification was allowed to be overruled. And for this, it's important to recognise that that standard double lobe picture of an AGN that I showed in my first slide can be distorted in several ways, including but not limited to episodic activities. That's where we get the triples and quadruples, black hole spin precessions, so you get some S-shaped ones like this, and many of the other reasons. This process also allowed us to get a few statistics on our population. We found that 6.67% were bent, 1.32 were S-shaped, and 4.2% were one-sided. Our final classification method was to use the far infrared radio correlation. So the radio and far infrared emission of the source is correlated when they both arise from star formation processes, and so are related to that underlying star formation rate. So any star-forming source that was more than 2 standard deviations above this ratio was reclassified as an AGN. Now, across both methods, so that's including the radio morphology and the far infrared radio correlation, there were 26 sources that were initially classified as star-forming galaxies from their optical spectra that we reclassified as AGN. The final difference between our study and previously ones done was our method of calculating the luminosity function. So previous studies were using the 1/Vmax method from Schmidt 1968. And in this case, Vmax is the maximum volume within which the ith galaxy can satisfy the sample selection criteria. For us, we're using the Page and Carrera method. In this, the volume is the integral over the luminosity range of the bin and the volume enclosed between the maximum and minimum redshift. And this has 2 main advantages, which is why we've decided to use it. Firstly, it more accurately determines the volume available to the sources when a detection limit passes through the luminosity bin. And secondly, it allows Poisson statistics to be used to calculate the uncertainties. So now I'll present to you some of the results that we have made, some key results that we've got. So these are the local radio luminosity functions split up into star-forming galaxies in the blue and AGN in the red. We fit a Schechter function to the star-forming galaxy luminosity function, and a double power law to the AGN one. In the yellow is the results from Franz and al. 2021. And you can see that overall, the radio luminosity functions for the star-forming galaxies and the AGN are similar to before, but there are slight changes at the bright and faint ends. And these ends are still quite affected by small numbers, which hamper accurate measurements. And you can see these are the data points with the largest error bars. Next, we split the AGN up by their accretion rate. So we used W1, W2 color for this, as it can be a proxy for hot dust, and so it can be used to measure the accretion rate. When we had W1, W2 color less than 0.5, the AGN formed the low accretion rate population. For these, the accretion disk is thicker and the jets can form more easily. On the other hand, when we have W1, W2 color greater than 0.5, these formed our higher accretion rate population. And in these sources, they typically have accretion disks that are thin, as the accretion is efficient. So it makes sense that when you look at our histogram, you see that there are many more slowly accreting sources in the sample, as many AGN with high accretion rates do not produce enough radio emission to be detected. Then finally, we split the AGN by black hole mass. And so you can see we've done it into 4 categories here. From this, we learnt that the lowest mass black holes, that's the red curve, are in radio galaxies of any luminosity. They span all of them. On the other hand, though, the higher mass black holes, so that's this purple one here, only appear in the radio galaxies in the middle luminosity range. They're limited to this region here. We also did a little bit of analysis on the AGN population. So here is the mid-infrared luminosity against the radioluminosity, as well as the accretion rate. So the mid-infrared luminosity was determined at a rest wavelength of 5 micrometers, assuming a power law between the W2, W3 flux densities. And then the accretion rate was calculated from the mid-infrared luminosity, and hence you can see why they've got very similar features. We've coloured it by the W1, W2 values, as we split the AGN up by that before. So for the main sample, the light pink is the low W1, W2 value, and the purple is the high value. And you can see there is this clear split here, and so it shows that it is a reasonable measure of accretion rate with comparison to our new measure of accretion rate. We also showed the Eddington accretion rate. And when doing this, we found that only a small fraction of our sources, so only around 15%, were found to have high Eddington accretion rates, so above 0.01. We also fit this with some theoretical tracks that related jet power to Eddington accretion, just to see how that compared with our points. And for this, jet power is a function of the black hole mass, the Eddington accretion rate, and the black hole spin. So in summary, we produced a local radioluminosity function at 200 megahertz up to a redshift of 0.1 by building off the work of Franz and al. 2021. And we split our luminosity function by source type, so star-forming galaxies and AGN, and then further split the AGN by accretion rate from the W1, W2 color and black hole mass. There were 4 main improvements that we made compared to previous studies. These were imposing an upper redshift limit of 0.1, including additional sources, that was the A-team, the Magellanic Clouds, and the GLEAM-Jansky sources. We introduced 2 new methods of classification, so on top of the optical spectral lines, we also compared with the radio morphology and the far infrared radio correlation. And then finally, we were using the Page and Carrera method to calculate the RLF. Overall, the radioluminosity functions were similar to before, with slight changes at the bright and faint ends where small numbers were still hampering our accurate measurements. And so at the moment, we're in the process of turning all these results into a paper, so keep an eye out for that. And thank you for listening, everyone.
Thank you, Tamsyn. Very nice presentation. Any hands up? Any comments? Yeah, Tamsyn, I have I'm very interested in your morphological classification, and do you have used any tools to help with the morphological classification?
Sorry, can you repeat the question?
Do you have used any tools to help your classification?
Any tools to help the classification?
Yes, just do you have used any application or something?
No, so this was a big part of my summer project, was going through all the RAX images and looking at it by eye and determining the classifications, because obviously radio galaxies are not designed to fit into the 9 or 12 boxes that we've created. So a lot of them were like in between, and so they had to have two, that was across 2 of the categories. But no, we didn't develop any tools or any automated process of doing this. It was done by hand.
Okay, how many sources in your sample? How many sources in your sample?
So there was 1,200-ish sources in the sample, but there wasn't data available for all of them. But it was a lot, but it was done over a long period of time, so it wasn't all done at once.
Wow, great job, great job. Yes, we have actually we have choose about use AI to do something like this, to do the classification. We can maybe we can discussion privately. Yeah, I can share my some experience to you. Yeah, I have some choose for you.
Yeah, that would be great. Thank you.
Yeah, you're welcome. Okay, so due to the time limitation, if there are no more questions or no more comments, we will move on to the next speaker. Okay, Kat, are you here? Kat will bring us the GLEAM-X. Where are we at what's next?
Yes, hi. I'll just start sharing my my slides. Coming up, hopefully. Yes, okay. Can everyone hear me fine?
Yeah, it's good.
Cool. I'm weirdly using like 2 different systems, so hopefully it works fine. Hi everyone. Yes, so I'll just give an update today about the GLEAM-X survey, or the Galactic and Extragalactic All-Sky MWA Extended Survey. I'll start. This is obviously Natasha's sort of PI project, but I have recently come on in the last couple of months, taking over from Tim Galvin as sort of the main data crunching and processing person. So I'm going through all the data and really churning through everything to get this survey out. So today I'll give a bit of an update of where we are and what the next steps are, but also highlighting some of the cool science that we can be doing with GLEAM-X. And so if you are interested in anything, feel free to get in contact with me and we can look at possible connections between how GLEAM-X can be used with your science as well. Right. So just a bit of a quick summary. I'm not going to spend too much time on the details because I think it's been covered in previous MWA project meetings. But the GLEAM-X strategy is very similar to GLEAM, so that they are very comparable, obviously. But the observations for GLEAM-X have had 3 separate sort of phases of observation in 2018, 2019, and 2020. Covering all the deck strips from south from +30 of deck and covering sort of the entire RA span there. And the frequency coverage will be pretty much exactly the same as GLEAM-X, so from 72 to 230 megahertz with those individual subbands as well. So we have a lot of data to be getting through as well, which is really exciting. And there will be polarization and RM synthesis is all there, so very exciting. Just a bit of a comparison compared to GLEAM. I do want to highlight first and foremost the GLEAM-X pipeline. If anyone is using it for processing their data with MWA, we've recently migrated it from Tim's GitHub. So if you're using that one and checking for the updates there, that one is now depreciated. So there is its own GitHub organization page for GLEAM-X, where we'll be putting all the updates to our processing pipeline, and any fun tools that we develop will be put on that GitHub, not Tim's or anywhere else. So at least it's all kind of put together and easy to find, hopefully. But just in case anyone is using the old one, that is where you can find it now. So just a quick update compared to GLEAM. So we're using multi-scale clean now due to some work with Stefan. And you can see just in that sort of GIF down at the bottom right that the extended emission sort of fades away a little bit, but those point sources look delightful. We're doing some primary beam correction using the FE primary beam model now to correct for all of those flux density calibration RMS business. Okay, this is really the big issue at the moment. So as we're heading into solar maximum, the ionosphere is becoming more and more relevant. I'll touch on this a bit later as well. We are currently running by default FITSWARP, which corrects the source positions as they move compared to our sort of comparison catalog of NBSS and SUMS. So this ionosphere, as it's really turbulent, can shift the apparent position of the sources. And this GIF, you can kind of see that it can get quite dynamic. So within a 2-minute snapshot, sources can be moving in very different directions. And sometimes it can be fairly uniform, but different from obs IDs just before it as well. So this is definitely a really important step in making sure that our sources are where we intend them to be. But it's also very interesting to see the effects of the ionosphere. So we are working with the NRL, the Navy Radio Lab, I think that's what it is, Research Lab in the USA for analysis of the ionosphere as well. But yes, I'll go into a bit more of that later. But once we've kind of got these lovely snapshot images, we've corrected the source positions, we're adding them all together, stacking them up to make these giant mosaics covering, broad regions of the sky. So this is for each of their 84 nights, and then we'll sort of add them all up together as well to make the sort of big main one as well. So then for each night, we have individual mosaics for each of the roughly 8 megahertz subband or subchannel, and as well as the main combined multi-frequency synthesis one, that's about 30 megahertz bandwidth. So that's a lot of mosaics and a lot of data, and it's delightful. It's a good problem to have of having a lot of data, but it does mean a lot of that sort of intermediate data that's even larger. So putting it all in this mosaics, we get the kind of final product and cut down a bit on all of the data needed, and it's sort of got everything that we need in the mosaics. In terms of the actual quality of the mosaics, they are delightful. So we're looking at really low RMS noise, particularly compared to GLEAM. You can see there, certainly at the higher frequencies, they're around 200 megahertz. We're getting around like 1 millijansky per beam RMS noise, which is really lovely. And you can just see how that's changing per frequency in the GIF on the right there for each of those roughly 8 megahertz mosaics across the different frequencies. Right, so what do we see in terms of the sources within these mosaics? The absolute vast majority of sources are just a classic power law. This is really comforting because that's exactly what we should be expecting at the MWA frequencies. So the vast majority of things will just be these typical AGN with a steep spectrum. Perhaps for me, I'm most excited by those sources down on the bottom left here with a lovely peak in their spectrum. That was what my PhD work was on. These sources, I think, are particularly interesting, and it's also very exciting that we can actually sample that peak within the GLEAM-X data as well and within the MWA bandwidth. So that's also very exciting. So we are doing some spectral modeling. You can see, obviously, if we're just fitting a power law for those peak spectrum ones, that's not necessarily the greatest fit. So I will hopefully be also doing something related to those peak spectrum sources, trying to identify them as well. Good news is that this is all really consistent with GLEAM, so it's not like we're seeing all of a sudden the entire radio sky has changed dramatically, because that would be very concerning. So this is all very good news. Okay, so what are we up to right now? So there has been the data release 1 has already been published and is out. I'll show where you can find that later on. But what about data release 2? Well, we're in the process of processing at the moment. We've already covered around 10,000 square degrees and finding so many sources. I did laugh seeing this just kind of quick image background. I have clearly been processing so much data that I actually could immediately tell you where we are. I don't know if anyone else has noticed the very iconic source towards the bottom left there, but we've got Fornax A down here. So I just found that nice that I could immediately see just from looking at so many images of beautiful GLEAM-X data. Okay, so what is data release 2 covering? So data release 1 is in the sort of orange there, carrying sort of a narrower deck strip, and we're looking to broaden that at the moment. That black box is what has been processed, but data release 2 will extend that to higher and lower decks so that we're covering everything south of 30 for that RA range. At the moment, we're just going through what has been processed, make sure that it is good before making those final mosaics and also extending to the higher and lower declinations. One of the issues that I did mention is the ionosphere. This is particularly an issue at the lower bands, which is more sensitive to the ionosphere. And in particular, you can see here from within a 2-minute snapshot, we see this kind of positive and negative butterfly shape. So that's because there is this direction-dependent relationship with the ionosphere. And seeing this effect within the 2-minute snapshot can mean that that 2-minute snapshot itself, once we've added it all together across time, can blur out these images and blur out the sources and really make them quite broadened and fuzzy, which is obviously not what we want. So at the moment, we're doing a lot of QA on the impact of the ionosphere and whether or not it's worth solving a lot of it and trying to delve deeper and save it, or do we just cut our losses? I will say that that's us trying to figure out how bad it is to cut. If you are interested in the actual ionosphere and learning from it, you can see Angie's talk later today because she is actually interested in the ionosphere and what we can learn from it. I am more interested in how bad it was and whether it's ruined everything. So just a quick look at one of our sort of diagnostic plots that was helped develop by Brandon, one of the PhD students in the GLEAM-X team. So this is looking at the integrated flux density over the peak flux density for like really nice, compact, lovely, well-behaving sources. So on a good night where we see minimal ionospheric effects, as we go through the night on the x-axis there for OBS-ID, these should be fairly flat. The integrated flux density over the peak flux density for all the sources in each OBS-ID shouldn't really change that much over the night. So there might be a bit of a scatter, but overall everything should be behaving nicely. This is an example of a good night. There's maybe a couple here and there that have shuffled around a bit, but on the whole, everything's behaving quite nicely. Compared to this night, you can see there's actually quite a bit more scatter between the across the night, particularly at the beginning part of the night. We get quite a big peak here, and right at the peak as well. The scatter of the integrated flux over peak flux for sources within that OBS-ID snapshot varies wildly as well. So it sort of suggests that it got really turbulent for a bit there and then kind of calmed back down again. You can also see towards the end there, it does get a bit more scattered and ratty. And what's most noticeable as well is that at these lower frequencies, so channel 69 is where we see this most pronounced. So again, the ionosphere being sort of most sensitive at those lower frequencies, or we're most sensitive to the ionosphere at those frequencies. So this is sort of the QI that we're doing at the moment just to see what's going on. All right, so despite that, already we're seeing some pretty interesting results. So as I mentioned, Brandon, one of the PhD students who's just started, is looking at a lot of cosmology within GLEAM-X. I will not attempt to describe this in too much detail. I am definitely not a cosmologist, but we can actually see the cosmological structure. So this angular correlation function relating to the sort of clustering and distribution of galaxies. I won't say much more about it other than it's doing what we expect and things are going well. So that's pretty exciting as well. That already we're seeing a lot of very exciting results. So what does that mean moving forward? Well, we have already done the initial data release. That was DR1 of that other region I showed earlier. And we're currently doing the processing for the next data release that will hopefully be submitted mid next year. So that really just depends on how quick I am at processing all of this and churning it out. But at the moment, everything seems to be on track, and hopefully we'll get an internal data release pretty early. But if you are looking at particular sources or areas of the sky that you think GLEAM-X could be really useful, and you are just too impatient feel free to get in touch. There's every chance that I can have a little sort of focus on that area and put it as a higher priority to get that data to you as well. So feel free to reach out if you are looking for GLEAM-X, and we can work something out, I'm sure. Despite that, what do we see as well? What's going on? Well, with the galactic plane, I mentioned earlier, or we saw in that little GIF, the extended and resolved diffuse emission, we kind of lose some of the sensitivity with that due to the configuration of the MWA, but there is perhaps a really great option of doing the short baselines of GLEAM as well as the sort of GLEAM-X data as well, so that we can actually get back a lot of that extended structure as well. And that will be really great, particularly the galactic plane for those supernova remnants and big extended structures. And so Sylvia is a PhD student that's just started. We'll be working on a lot of this as well. So this is also a very exciting space. And gosh, I'm very jealous of these incredibly beautiful images as someone who often works with just unresolved fuzzy blobs. So that's very nice. Already we're seeing some very exciting results as well. So this new type of transient event that we've got this ultra long transient that is about 19 minutes, I think from memory, of, what's the word I'm thinking of? Period, thank you, Sammy. 19-minute period. So this is Natasha's work and the team for that in the Nature paper that came out earlier this year, which is really, really exciting, and I think highlights that there's a lot of science that we don't necessarily know about or know that we're going to find. This is the perfect example of that. Again, I won't go into too much detail because Natasha is giving a talk tomorrow about interesting transient things, so I won't steal any of the thunder there. For polarization, so Zhang has been doing some incredible work here as well. So you can see in this GIF, as you change the rotation measure, you start to see these compact sources popping out as well in the different rotation measures. So it's really exciting as well, and POGS-X looks like we'll see some very interesting results of the sources, the polarized sources in the sky, and in particular a bit of a focus on a very extended, delicious source. In my opinion, it looks lovely. We can see the Stokes eye, but also the rotation measure of this extended structure. You can see the difference there for the different lobes. So very exciting to see the possibilities of these resolved structures with the increased resolution of GLEAM-X compared to GLEAM. So hopefully there's more of this to come as well. As well for the circular, for Stokes V, we're detecting known things like the known pulsar on the left there, so that's comforting. We're finding the things we expect to see, but also there can be some leakage, or maybe it's an AGN double, who's to say? So again, there's a lot of really interesting things for this polarization. I think there's a lot to uncover here that we don't necessarily know what we're going to find. In terms of the data for GLEAM-X, so there is a lot of it, as I hinted, definitely, particularly with those raw visibilities of 2 petabytes in the archive is a lot of data. And that also means like a lot to churn through. So thank goodness for Pawsey, and in particular Cetonics coming back online. That's where we'll be focusing a lot of our processing. And we have, thankfully, a lot of live storage with the Nimbus instance, and can store a lot of the images, the metadata, and the stuff that we really need to be able to create these wonderful mosaics. But also if we have this intermediary products as well, we're keeping that accessible as well. So if you are interested in those intermediate things, again, feel free to reach out. Very exciting that the data release 1 you can actually access in Data Central already, so you can put in your RA and deck and find whatever magical source you want to be looking at. I actually did this recently. It was very exciting to see it there sort of live. And if you are interested, there's a link down there for the PASA data store for the DR1 as well. Right, so what about these science prospects? I dabbled in a few highlights there, but I think it's pretty clear as well already from this project meeting that we're still seeing a lot of incredible science coming out from GLEAM. So it's pretty amazing to think of the long-term science that we can be getting from GLEAM-X as well. So I'll focus on my favorite, the peak spectrum and curve spectrum sources. I did a lot of work on their spectral variability using GLEAM. So I think it's very exciting to be able to start to see these fainter peak spectrum sources because of GLEAM-X having that higher sensitivity, and potentially looking at how these sources are evolving between GLEAM-X. There's a lot of possibilities there as well. But in sort of these broader categories, the transients and variables, again, we're already discovering new types of variables, so that's pretty exciting. And we're starting to see these large surveys where in the southern sky, for once, I guess, we can start to compare over time with these other surveys, because we now are actually having a lot of large scale, covering a lot of the sky surveys over time that we can compare to. So that's very exciting, but we can also start to see these short-term transients as well. And in terms of these radio galaxies, so I won't go into too much detail. Again, it was kind of covered a bit by Chenoa in the GEG update, but there's a lot covering the whole AGN life cycle, from very young to very old, from Quichi's work on radio galaxy life cycles, but also work in star-forming galaxies as well, and in this galactic plane, getting some new supernova remnants, and hopefully more with GLEAM-X as well, that we can discover as well. So a lot of very exciting things on the horizon with GLEAM-X. So to summarize, as I mentioned, the data release 1 is already out and about. You can use it, and I highly recommend having a little peek at some pretty exciting stuff there. And data release 2 is underway well and truly, and hopefully will be out and about as well in 2023, halfway through 2023, should everything go to plan. But this is definitely a really important survey, particularly SKA era coming in. I don't know if I assume everyone's seen in the news that we've now officially cut the ribbon in terms of building on site for SKA low. So these sorts of surveys with GLEAM-X will be very exciting and very important for understanding what we can expect to see with SKA and comparisons. But yeah, there's a huge range of science that's possible here. I have mentioned, if you are really impatient, feel free to get in touch, and I'm sure we can work out a way for you to get your hands on some data as well if it's useful. But thank you. I will take any questions. Yeah.
Thank you, Kat. Very exciting talking. So yeah, Toya has a question. Yeah, please go on.
From the experience of the data release 1 and the data release 2, could you remark on what's the mean sensitivity of the GLEAM-X, and what's the biggest source of the flux density uncertainty?
I can't say too much for GLEAM, the data release 2 at the moment. We haven't really made the final mosaics to do a comparison of that yet. I imagine it will be very similar to data release 1. I mean, that was the whole reason we chose that region for DR1, was so that it was pretty representative of what we would be dealing with in the next data release. So I would hazard that it would be very similar, but I don't have the numbers off the top of my head at the moment.
I could just jump in there, Kat. Sorry, Tao. Yeah, the RMS is really comparable. So it's about a millijansky per beam. There's some areas at the moment, which is why we're doing more QA, where we're not happy with the appearance of the sources. Like, they are more blurred at the lower frequencies, which implies the ionosphere is up to no good. So we're working on that. But at the highest frequencies, which is what Kat was showing at the back of one of those slides, that blurring is really minimized, and yeah, the data are about a millijansky per beam. So that's the RMS. Obviously, in terms of your source finding, what we do is a 4 sigma source find, but then we cut at 5 sigma. One of the things we found when we were doing the QA for GLEAM-X, and it's in the data release 1 paper. Yeah, sorry, not this slide, Kat, but anyway. One of the things we found, yeah, this one. Yeah. One of the things we found that I thought was actually quite interesting is when we compared the flux density scales of GLEAM-X and GLEAM, they are in extremely good agreement, you know, down to a percent or so, above a flux density of about, I'm gonna do this by memory, about 100 millijanskis. And as we went below that, we started to see a difference in the flux density scale, which gave us quite a worry for some time until we realized it was Eddington bias in GLEAM. So we've noted this in data release 1. It's not a huge effect. It's sort of a 5 to 10% at the faintest end of GLEAM. But anyway, the fact that we could pick this out, you know, was quite impressive. It does mean that as you go down to the very, very faintest end of GLEAM-X, the same effect will be in play. There'll be a slight Eddington bias. However, one could conceivably now that we've sort of shown that this method does produce that bias, you could actually correct for that. So the details are all in the data release 1 paper, if you're interested in those very, very fine flux density scale questions.
Thank you for the detailed description.
Thanks, Natasha.
Thank you, Natasha. So any hands up? Any questions? Okay, if there are no more questions or comments, thank you, Cass, again. So thank you, all the speakers. So now is another session, so Chenoa will host the next session. Yeah, Chenoa, please.
Thank you. So our next one, we're going to go into some more overview talks of the instrument, and we'll be starting off with Randall talking about engineering updates and receivers. Randall, you all set?
Yeah, hi, thanks, Chenoa. Can you hear me okay?
Yeah, I can hear you.
All right, let's see if I can work out how to share this correct screen. That could be it. How's that one?
Yep, it's all good. Thanks, Randall.
Great. Well, I wasn't actually expecting to present in this meeting, but this is, I'm going to be presenting the digital receiver update on behalf of Yajun, who unfortunately had an emergency yesterday and couldn't present today. So these are his slides. Yeah, my best wishes go out to Yajun and his family. I hope that all is well. So the background of this system, I think, really starts back to the carefree days of 2019, when Stephen initiated a collaboration with SHAO to start work on a new receiver for MWA. And this progressed through to the middle of 2020, where a formal proposal was submitted as part of SHAO's phase 3 contribution to MWA. And the proposal really, we wanted to encode the high-level specifications and deal with or address some of the shortcomings of the original receivers that Stephen talked about this morning, that we know and love and have served us well for a decade, but did have some shortcomings. So deal with those. Basically, improve everything. Get rid of the things that weren't so great, and also importantly, have the ability to have an oversampled PFB in the future. This is one of the long-standing problems with MWA, and also had the ability to grab. Have a voltage ring buffer of the raw data, which can be used for science cases that need that sort of nanosecond scale time resolution of the actual raw voltages coming off the tiles. So these are sort of it's a summary of the high level requirements that were encoded into that document. So the receiver consists, I've got some pictures in the next slide, but it consists of an ASC, which is analog signal conditioning board. This is the thing that amplifies and filters the signal suitable for digitization by the digital systems. The ADC is the analog to digital converter. and the FPGA is the field programmable gate array, which is the digital system that actually creates the course channels within the MWA and does all of the bookkeeping and shepherding of the data to get it out onto the network and further downstream. And the board that was chosen is nice. It's sort of an integrated board that has the sampler, the ADC, the digital logic, a small single board computer for control and so on. And this was packaged by SHAO up into a shielded enclosure that could become part of the larger receiver design. The firmware basically contains all of the functionality that we would expect with the improvements that I just sort of talked about before. We can run the filter bank in a compatibility mode to match the current system, or a oversampled mode for the future. The data come out importantly on a standard network connections with standard protocols, which just make it seamlessly easy to plug it into the downstream systems. This is a big change from the previous design. We also included some more monitoring and control statistics on the quality of the data, so a bit better, I guess, yeah, monitoring the statistics of the incoming data so that we can make sure that it's optimized in the sense of running the analog to digital converters at some sort of optimal level. Yeah, so these systems contain a small single board computer. So this runs Linux just as basically as the control interface, and all of the interface is actually presented just as a really simple web. I think it's a REST type interface for all of the monitor and control of this system. So that makes it really quite easy to deal with, and is also largely compatible with the new interface, web-based interfaces that we're using for the NI-based receivers. So here are some nice pictures of the bits and pieces and them all packaged together. So this is the actual ADC and FPGA board. I think they're based on Xilinx processors, packaged up into a nice shielded container, because obviously the RFI suppression is very important on site, especially for things that are out into the field. So that's all nicely packaged up. And into the final receiver box, we have the digital part of the system, which is this here. So ADC, remember, is the analog to digital converter. And then this is the analog part of the system. So the ASC is the analog signal conditioning. So the raw signals come in from the tiles, are filtered and had some sort of a gain applied to them, and then digitized and then off downstream. So the prototype receivers, you can see the two of them were made over the last, I guess, about 12 to 18 months. And you can see them nicely packaged up into the enclosures here. Just the interfaces on these. On the front, we have some just USB, just for really low level debugging if required, and of course the obligatory light, blinking light. But the main interfaces are the signals that come from the tiles. So these are the RF signals from the tiles, clock and timing information, of course. The main data output come on the 10 gigabit links, and then there's also a 1 gigabit link for the monitor and control. Okay, so the status is that, yeah, over the last, I guess, 12 months, most of the work has been on detailed verification of these receivers. The compatibility mode is completely finished and is the most well-tested part of this. It is completely compatible with the existing ROI receivers. We have 24 channels out, each 1.28 megahertz wide, exactly the same as the existing ones, except with eight bits of quantization. So actually more precisely, or is that the right word? More correctly quantized instead of the 5 bits that come out of the existing ones. These go straight onto the network, as I said. So this is straight into the main MWA data network that goes down to the correlator. As I mentioned before, the MNC is all straight through a very, very simple web interface. So this is very easy to connect and control through the MWA's monitoring control system. There is a new feature, which is the ring buffer that can cache the raw voltages for roughly a second. And then we have a mode to be able to trigger that stopping the ring buffer and trickling that out over time. So this, I've got a photo actually at the end. There's a photo, but this is now on its way to us here at Curtin. So a bunch of tests have been done in the lab. I'm going to actually break out these images here because I think they're worth expanding on a little bit more. But briefly, I'll just say that Jake Jones here from Curtin, part of the technical team, has really led the effort in doing all of the verification. The SHAO team set up the system in a lab at SHAO with full remote access. So there's the receivers, signal generators, a control and capture computer, so that we could completely control the signal generator and capture the data and do all of these remote tests. So it's been a really good team effort here. So I'll expand on each of these plots here. So I'll just go on this. So the first one, of course, is to make sure that the PFB is doing what we expect it to do. It may sound a bit silly, but this is actually a really, really critical part of the signal processing of the system. And we need to make sure that this is working exactly as we want. So this is a result of testing a swept signal source that runs across frequency and measuring the result of this, the total power as a function of the frequency. And you can see that this matches up exactly the way it's supposed to. The little bit of quantization here is nothing worth worrying about. And this test actually originally did find a problem, which is great. This is why we do it. And now now it all matches up perfectly. This was a test of the ring buffer. I'm pretty sure that this plot, what it's showing is an expected discontinuity in the voltages when the ring buffer stopped. So this is where we've put in a pure sine wave into the system and captured all of the voltages, and then when triggering the ring buffer, we get a break here. But otherwise, it shows a perfectly continuous sine wave. So that's looking good. The next one is looking at just the correlated signal. So having some sort of correlated noise source put into multiple inputs and correlating them. And that's the core business for the radio telescope, obviously. And that is also, of course, looking really good. So this is capturing and then offline correlating. And I think this is sort of related to a test that Jake presented, I guess it would have been a year ago, possibly at this meeting, on long integrations with the system. So this is a test where the data were captured and integrated, and I think here a small correction or a correction was made for the shape of the coarse channel bandpass and then integrated together. And so this is the result of a 30-minute long integration. So we can see in the compatibility mode of the system, there's still artifacts at the coarse channel edges just because of the way that the filter rolls off. But it's worth noting that these are really at the sort of 1% level, not even 1%, less than 1% level here. So this is in dB, and this is 0.01 dB. So really small, and basically showing us that this is working as well as it can in compatibility mode when we apply a correction for the course channel shape. Okay, so this is, I think, ongoing work. Jake and Yajun are working on implementing and testing the oversampled PFB mode. So Jake has provided the firmware for that. We're also looking at, in the future versions, expanding the range of gain or attenuation that can be applied in the analog signal conditioners. And this is to be able to support, in principle, some of the longest baseline coaxial cable tiles of the MWA. This, the specifications of the receiver originally, it was going to be envisioned to only be connected to RF over fiber tiles, which have a much more modest range of gains that we need to support. But anyway, that's fine. So in the future versions, the expanded gain range will give us a lot more flexibility. And Yajun and the folks at SHAO have also been looking at increasing potentially the number of output course channels that can be generated by the system. There's actually a bit of spare capacity in the FPGA and networking, and in principle they can go up to 32 output channels instead of the 24 that we have now. So I guess that'd be something like a 40 megahertz worth of simultaneous bandwidth rather than the 30 megahertz that we have now. Okay, so this is the last slide. This is Yajun saying thanks to the MWA team, and I, on behalf of MWA, I say thanks very much to Yajun and the SHAO team. It's been really good working with them, and things have progressed really well, especially through some difficult times over the last couple of years. This is a photo that Yajun just sent on Monday, which is the version 1 receiver, nicely packaged up into a nice container that is on its way to us now. So we're really looking forward to receiving that one and getting it into the lab here and out to site and connected to the sky next year. So exciting times. Thanks for everyone, and I hope I presented this as well as Yajun was hoping, and I'll stop there and take any questions.
Thank you very much, Randall. Does anybody have any questions, either for the chat or put your hands up? Yes, can't wait till V1 arrives, Kat says. Okay. If somebody thinks of a question later, you can pop it in the chat and Randall can answer it later. Thank you very much, Randall.
No worries.
So
Thanks.
next up we have Greg to give us an archive update.
Hey Chenoa, can you hear me? Is my video coming through okay?
Yep, both are good.
All right, I'll just share my slides. Hopefully that's come through now.
It is, it's all good, thanks.
Cool, okay, thanks a lot. Yeah, hello everyone. My name is Greg Sleap. I'm the MWA data manager, and I'm going to be talking to you about all things data archive and systems and give you an update. It's only a very short talk, but I've got quite a bit to go through, so I'm going to go pretty fast, but feel free to ask me questions at the end. So first, I just want to start by acknowledging the traditional owners of the land on which I'm presenting to you today. It's the Bangarang people of the Oberoi Nation, and pay my respects to elders past and present. So in this talk, I'm going to be talking to you about the archive volume and where we're at, ARDC data collections, a recap on the data retention policy and how that's being implemented, a new project you've probably never heard of, which is the download log project, and also just an update on software and systems in general, and perhaps a secret weapon. So firstly, where we're sitting at the moment with the archive is that we have used about 8.5 petabytes for the 2022 A season. So that puts us with just under 5 petabytes remaining in the archive. So you can see on this chart across there to the right-hand side, the last couple of quarters have had quite a bit of ingest, so that's to be expected from this semester. And so we've ingested both into Acacia, which is Pawsey's disk system, and also Banksia, which is their new tape system. And both methods have been working pretty well. So we've got just under 10% of the archive free, and that means we'll be basically finishing off the last bits of 2022A and still have room for some DDT requests to the director, and which puts us pretty much in a reasonable position for the next semester coming up. So the impact of getting a new semester in and how much data we have to delete will hopefully be quite minimal. But a lot of it all depends on the amount of proposals that come through in the next semester. So this is just a summary just of the last 6 months, and as you can see, we've had some pretty big months. The September month pretty much set an MWA record. I don't think we've ever ingested over 2 petabytes in a single month, so yay us. And that I think also gives us, Natasha is saying, sorry, it's okay, you're forgiven. That's what it's there for. So I think it gives us quite a bit of confidence that that we can actually step up things like ingest as the number of tiles and receivers goes up, and we can keep up with it. So that's a testament to the MWAX system and the archiving systems, and also Pawsey for being able to handle it. So next is just onto the ARDC data collections. I touched on this last time, where the ARDC, which is an Australian institution to sort of help manage big research data sets, they put forward a project called Collections of National Significance, where we had basically applied for 3 MWA collections to be part of that program, and we were successful. So we basically were awarded that for the EOR raw data for 2014-2015, the GLEAM survey, so that's the original GLEAM survey, plus the first 2 years of the SMART survey. So that has been successful, and you can read more about that on the ASVO website, where we've listed the collections there. The MWA ASVO now provides a search criteria for the collections, so you can see which OBS IDs are included. And the final part of this project is for Pawsey to, I guess, purchase and install the 2.5 petabytes storage in the Acacia system that we will be, I guess, bookkeeping as a ring-fence storage for these collections. So in all reality, they are sitting there on the disk at the moment, but it's just that they'll be giving us additional capacity so that we don't need to consider these 2.5 petabytes for any deletion requests. There are potentially 2 new collections which we may get through the program as well. So they're up for consideration with the ARDC panel at the moment. And if that happens, then we'll basically get another 2 years of the SMART survey stashed away and ring-fence storage for that. And also Natasha Hurley-Walker has also put forward a proposal for keeping as much of the galactic plane data from the MWA as possible, because that's the rich hunting ground for transients and unknown objects. So just to recap on the data retention policy, I won't go through this whole list, but I guess just to remind ourselves, that we'll be, I guess, making use of the data retention policy prior to each upcoming season if required. So obviously we don't want to delete any data that we don't need to, and we'll be working out based on the proposals that come into the TAC exactly how much space we have in the archive and if we need to make any room for the new semester. The most important part, which is what I've highlighted here and is a focus on some of the other slides that I've got later on, is that the delete list that will be considered is going to be based on age, but also utility. And so Chris Riseley, our principal scientist, is going to be the main decider of utility and age and what is the least impactful data that we can remove in order to make room for the next semester's observations. And so, as I mentioned before, we'll start the first delete cycle before the 2023 A season starts. So as part of the decisions that the principal scientist needs to make in order to work out what can be deleted, we realized that we needed to provide the principal scientist with as much information as possible. And one of the most important things that we hadn't had up until now is a comprehensive database, I guess, of all of the downloads of all of the obs-IDs that have happened throughout MWA's history. So we have, for the last 3 months, we've had a new student intern with us, Nahal Rasti, and she's been working with Harry on this project where we're basically going through the 1 terabyte or so of logs from the 3 or 4 various systems over the years that have been used to track downloads of MWA data. So the bottom left chart there is just showing what we expected to find in terms of coverage based on the different systems and logs that we have available to us. And the chart over on the right-hand side is just a heat map showing one of those things, which is the NGAS logs. And the each cell in there is basically a single day from a year and how many downloads occurred on that day. So as you can see, we've got a few gaps in there, and that's a source of investigation as well. But we believe that by the time we finish the project, we'll have a pretty comprehensive database which will cover the majority of the history of the MWA. So this will be useful information for the principal scientist, and it will also be added to our TAP service so that if you want, you could actually go and see how many times a particular OBS ID has been downloaded. And this could potentially provide insights which you haven't really thought of yet. So it's another useful bit of information or metadata that we have. Just onto the, I guess, system side of things. So there's a lot of stuff going on with PAWSI at the moment during December and January that we'll need to be aware of because it affects the MWA ASVO. So we've got December maintenance this Thursday the 15th, so that's next week. And then just a few short days later, then the Astro file system is being rebuilt. So during that time, the MWA ASVO will be offline. So the end date of that outage is meant to be no later than Tuesday, 3rd of January, but it may end earlier. That Astro rebuild is an essential bit of maintenance that PAWSI needs to do for system stability. I know a lot of PAWSI users will already know all about that, but if you're not a PAWSI user, then yes, then this file system is used both by scientists, but also by the ASVO system itself, which is why the ASVO is affected during that time. There's also a high voltage shutdown where the whole of PAWSI gets turned off for the weekend. And then there's the usual regular monthly maintenance. So I'd say if in doubt and you're unsure of what's happening when, check Pawsey's website. They're pretty much the instigators of all of these outages that I've mentioned, but we will also have the same information through the ASVO Twitter, so at MWA_ASVO, and also via the MWA users Slack channel. This is my kitchen sink slide. I apologize if there is a prize going for the ugliest slide. I think I won it right here. But the main thing here is to sort of go through the fact there's lots of various things going on that's in our purview, and by our, I guess that's myself and the wider ops team, where we're very involved. So we're working with AARNet to better understand and manage large-scale transfers of MWA data out of Pawsey. This is something that's going to be occurring more and more in time, and AARNet are very keen to work with us to make things flow more smoothly, and also AARNet have a self-interest there as well to basically make sure that when there are big transfers and things that they don't incur costs or anything where they don't need to. So they can make changes behind the scenes as to how data is routed either within Australia, but also throughout the wider sort of research network infrastructure around the world, of which AARNet are a part. We're also working with Curtin IT.
3 minutes, Greg. 3 minutes.
Thanks, Chenoa. We're also working with Curtin IT to further harden our services against cyber attacks and decrease our surface area. The MWA Wiki will be migrating to the Atlassian Cloud Wiki product in 2023. We don't have much choice in that. They're discontinuing the self-hosted product. We're also going to be migrating away from the Mailman 3 mailing list product as well, because the support for the systems that we have in place has become deprecated. So we'll be doing something about that and simplifying onboarding and sign-on to MWA services. I'll be providing more information about all of that as time happens. ASVO and Beerley will be supporting picket fence observations in a much better way than they do at the moment. We're going there's some other things that have happened just in the last 6 months or so, is work on improving handling some of the RI receiver and EDT card glitches that occur, and a lot of incremental enhancements to MWAX involving Randall and Ian and other members of the MWAX team, dealing with how we handle different values of T for the number of tiles, better health and better management, and M&C. So there's also a whole heap of things going on for ASVO and the TAP service. I won't go through all of those things, but basically we're just adding a lot more metadata, data quality metrics. Harry is starting to work on the design of the migration of the MWA ASVO to the new Cetonics cluster at Pawsey. We're basically going to be doing the delete request user interface as well, supporting the data retention policy. Harry's taken over and tested and completed the delete code, so the code that will actually do the delete in all of our systems, and is optimizing that with Pawsey. We're also improving the tools that Chris Riseley will be using to find candidates to delete, so that'll be including the download information, but also other data quality metrics, and a secret weapon to be launched to increase our success in the battle against increasing data rates, which is, you guessed it, Fringe-stopping. I'm not going to talk about this at all because I've run out of time as well, but this is in Luke's talk coming up next, and I think it's going to be one of the strongest weapons we have against the increasing data rates. And if you're a Captain Marvel fan, you'll understand. And that's it from me. So thanks very much.
Thanks, Greg. Does anybody have a quick question for Greg? Ramesh.
Hi, Greg. Thanks for that. I have a sort of a clarification question about this utility-based data retention, which sounded like I know there will be some changes compared to what was sort of mentioned in the previous project meetings. So if I understand right, those requests will have to be, I mean, originally the plan was they have to be like made periodically to renew the data retention. And I'm just wondering if I assume that this might still be the case, but if that is the case, how often we are supposed to expected to do that? And secondly, would that be like a project-based kind of a thing, or would it make sense to do like a coordination within the group and make a single request? Because lots of projects have like sort of dependencies, you know, amongst themselves.
Yeah, thanks for your question, Ramesh. So I guess the first answer is that we're doing this at the beginning of each semester or before each semester starts. So that way we're only looking at how much data we need to remove in order to make that semester fit. So that's that. If and yes, and so when the principal scientist goes and gathers the list of things that they believe should be deleted, that list will go to the collaboration for a 4-week review. During that 4 weeks, you have the opportunity to say, hang on, nah, this data is really important to me. Please retain it for this round of deletes. And you'll do that by applying to the director, who will then you know, work with you and the principal scientist to understand what that is. And if it's approved, which I'm sure it would be, if there's you know, good science to be had in there, then it will get a reprieve for this time. And in theory, it is up for potentially being on the list next time. However, Chris, you know, will be also maintaining notes of this sort of stuff and would probably avoid it next time as well if it's something that that he knows a team is working on. So I think that's in a way, it makes it a bit tricky to sort of, I guess, predict what this process is going to end up producing in terms of the list. But I think the good thing about it is that there's a human brain in there that is actually helping make sane decisions and logical decisions about what is not useful data anymore. And I think if you can put a case forward that the data is useful, there's no reason to want to delete it or touch it or anything like that. So
thanks. Yeah, that helps to clarify the point. Yes, thanks.
Yeah, and I think one thing I didn't really I think emphasize enough in my previous slides was just that that download information is going to be a good starting point as well, but it's not the be all and end all for Chris when he's looking through what can be deleted. It'll just be one aspect of it. So if a whole bunch or an entire project has basically not been downloaded at all, it could either mean that there's no interest in it, or it could also mean that the team that or the PIs and the teams that actually put that forward, maybe they just haven't had the time and the resources and the students to work on that data yet. So it is a double-edged sword, and that's where Chris Riseley's knowledge and experience as a principal scientist will hopefully help make this a good process.
Thanks, Greg. We need to move on. But thank you very much for the information. That was very helpful. So next up, we have Luke to talk about this fringe-stopping secret weapon. Greg, can you stop sharing your slides, please? Thank you.
There it is. Hey guys.
Hello.
Sorry, I WebEx thing. That
It's all good. Yep, it's all good. Thank you, Luke. You're good to start when you're ready.
Yeah. For anyone who I haven't met before, I work for the last guy, Greg, operations team. Coming soon.
Luke, we're only hearing about 1 every 10 words that you're saying.
Oh, shit. Okay. All right. Like breaking up or?
Yeah, like it just completely cuts out and then all of a sudden a word will pop up. So.
All right. What about now?
It sounds fine now. Yep.
Okay. So coming soon, the MWAX correlator will offer fringe stopping as an optional observation mode for the MWA. It replaces the geometric corrections performed after the fact by downstream software like the excellent Beerly package, with the advantage that a high degree of time and spectral averaging can be achieved without the decorrelation these parameters would otherwise incur. Result is smaller files, which may facilitate bigger observations. We're all very keen to make it available for science starting early in the new year, though I can't give you a certain date. I'd just like to show you a little about what it is, how it works, and that it works, I guess. You may be familiar with the idea, like low light photography, radio astronomy requires long exposures, and from our earthbound vantage point, celestial objects are moving targets. Radio telescope experiences the Earth's rotation as signals going in and out of phase, which more than smearing the image diminishes it. Phase is the physical quantity which a correlator correlates. Decorrelated signals tend to cancel out somewhat when we integrate them over time, more than a second or two, yielding visibilities with reduced magnitude. So far, the best way of dealing with this has been to keep integration times and channel widths small. Downstream tools like BLE calculate discrepancy and correct the phases in a routine step for ingesting MWA data. But it can only do that with as much resolution as you give it. At half-second intervals, the corrections typically work well. At 8-second time steps, they rarely do. So this mode is comparatively infrequently used despite an enormous factor of 16 difference in the file size, and the likelihood that longer averaging is in fact desired for working with a final product. It's more common to ask for half-second steps from the correlator and average them later with Beerley and to get the data with the appropriate corrections at the smaller footprint that people might be after. It makes sense to do this kind of work in the correlator because it's operating with a sub-millisecond resolution, and an equivalent correction in the correlator context can be applied with fine granularity, making those long integration times and wide channel widths usable. We implemented a little differently though. Downstream tools for working with visibilities apply adjustments to baselines. Our Fringe-stopping implementation applies them directly to each individual signal path, phasing up with the nominal array center by introducing a variable delay. That's what the little animation on my first slide was. And there's no tile here at the array center, by the way, given that it is 373 meters underground. When a fringe-stopping observation is scheduled, the MWA scheduling software uses AstroPy to calculate the expected as-al drift during the observation period and populates a new table in the metafits file specifying the pointing direction at 4-second intervals. Fringe-stopping engine proper begins in our UDP voltage capture software using the metafits data to calculate a path length difference for each tile relative to the array center, and subsequently a time delay. Delay is interpolated quadratically between the 4-second reference points and sampled at 1600 points for an 8-second sub-observation corresponding to a 5-millisecond FFT block in the correlator. The values are stored in a table in the subfile for processing in the correlator. Our unit of time in MWAX is the sample, which at a sample rate of 1.28 megahertz works out to be about 0.7 microseconds. Delays are typically in the range of plus or minus 20 samples, and we represent them with 32-bit floats, which we found to be sufficient, targeting something on the order of microsample or picosecond resolution, something like that, which we found to be just sufficient based on some experiments where smaller numbers, 16-bit ints, were not enough. We applied delays in 2 stages, literally then figuratively, I guess. We call it whole sample and fractional sample delay components. You'll see why I say literally and figuratively, because in the first place, we take the whole number part of the delay, which could be, say, 5 samples, and insert a literal delay into that signal chain. So we will hold up that stream of data by 5 samples to make it line up with the other sources. The remainder, the fractional part, is then written into a big table in the sub-observation file where it can be found by the correlator and applied as a phase rotation, implemented as a complex phase after the FFT step. So, all right, we'll get to looking at some results in a second. When the whole sample delay is applied, it causes information to physically shift around in the subfile, and for teams who might be using these for commensal research, it might not be ideal to have fringe stopping on. So to facilitate being able to toggle it, we've included extra information in the sub-observation files so that whole sample delays, if they are applied, can be changed, removed, or customized to repoint the antenna after they're made. There's a command line tool called Subtool available on GitHub, which can help you with that. Now, since BLE is the gold standard for how these geometric corrections are to be applied, given that it's widely used and trusted, we set out to validate that we could produce essentially identical or better results to BLE in with fringe stopping enabled. And that turned out to be a little bit tricky after we got the really big problems out of the way. Radio astronomy data tends to be anywhere from a little bit to really quite noisy, and although we expect fringe stopping and BLE's corrections to be the same, we don't necessarily expect their noise to look exactly the same. So we had to come up with a simpler way of comparing them. And so what we ended up with is these raw correction plots. This one's showing how BLE corrects phase over time for some source. So for these tests, we modified sub-observation files to replace the voltage data for all RF sources with the voltage data for one of them. Thus, the contents would be perfectly correlated at every frequency band, at every instant in time. And we could create 2 copies of these and run one through a BLE-like process and the other through a fringe stopping-like one. Both of them applied what they thought the intended, what the correct differences should be to the data, and we can then see that in the plots that come out. They should look identical, and indeed they do look identical. So that was a pretty encouraging first thing to get at, but it's one thing to convince ourselves with contrived data, and another thing to get it running. So that's what we've been doing over the last couple of weeks, really. The entire fringe stopping apparatus now is it's in the correlator. It's available for testing. It's not for me to say whether you can use it or not, but in principle, you can ask Andrew to schedule a fringe stopping observation, and the data comes to you as it normally would through ASVO. What we've got here are some interesting plots showing how things can change with longer observation times. There's actually 2 pictures here. It's kind of hard to tell. The one on the right is showing how the decorrelation can cause the strength of the visibilities we get out to actually diminish due to decorrelation. We have these each row in these pictures is a different baseline. The columns are increasing integration times, and we're plotting the amplitude for fringe stopping, which is the blue dots, and BLE's corrections, which is the yellow dots. And we can see that, as we might expect with longer integration times, really starts to look a lot worse. It doesn't have enough data at that stage to be able to produce good quality correlations. But we can with fringe stopping, so that's nice and that's encouraging. Have some more pictures here for some of the recent fringe stopping observations. One from the sun where we can see nice flat phases all over the place. We've got one that is kind of messy, but it's messy in both cases for Sen A, and in general, I could bring up any number of these, but they also seem to say the same thing. At this stage, we're hoping to get some sort of sign off for deployment in the early new year, and I'm sure we will get the word out to you when we do. All right, I won't keep you from lunch any longer. I think that's it for me. Thanks, guys.
Thank you very much, Luke. Does anybody have any questions for Luke? I see a lot of applause, so apparently people are very excited. What are some of the, I guess I'll have a question is, what are some of the greatest challenges of implementing this? Or do you foresee any in particular?
It was an adventure. See, I don't come from an astronomy background. I just brought my enthusiasm, and it's a a sink or swim kind of situation. I think there were times when we were really, I felt like I was almost doubting my sanity. I was going between being completely sure that we had something understood and we were on the same page to we're on completely different pages, and and no one understands why it's not working. It took a long time to get here.
Randall comments that they definitely threw you in the deep end.
I asked.
Enthusiasm is good though. Nice done. Any other questions? If not, I'll hand it back over to Mia. Thank you very much, Luke, and thank you for the speakers in this section.
Cheers.
Thanks, Chenoa. Yes, Luke, if you could stop sharing your screen, perfect. We will go for a lunch break and we will reconvene in just under an hour. So at 1 p.m. West Australian time, or whatever that is around the world. I'll put up another timer in a second. Okay, thanks everyone, and enjoy your lunch or dinner or break or whatever it is.
Hello, everyone. I assume since it's 1, we can start start up the project meeting again. So welcome to the first session for solar. First up, we have apologies from Divya, sorry. He is unfortunately caught up and he won't be able to give the first talk. So we have kindly got Devojyoti to come in and give us the solar science for the MWA status and plans update. So if you want to share your screen, we'll start off.
It is not in full screen, right? Just a second. Okay, don't know why. Can you see it is full screen?
We still see it as the edit version, so you can start full screen if you'd like.
Just a second. Yeah, I think it is fine now, right?
Yes, it's perfect.
Yeah. Okay, thank you. So I will be presenting on behalf of Divya because he's traveling, so he cannot present its talk. So this is mostly about the update about the SHI collaboration of the MWA. So here are the list of people involved in the SHI collaborations. There are lots of PhD students and some project students, and also some familiar names. And the currently some people who are currently now involved with the SHI collaborations are marked in the black. And we also have some commercial entities called ThoughtWorks in collaboration with our SHI group to work on. Okay, so in recent, currently SHI group is mostly focusing on these different areas of sciences. So first off, so these are ranging from the weak impulsive quiet sun emissions, then to polarimetric imaging pipeline for the solar observations, to the type 3, type 2 radio burst and space weather, and also the waves and quasi-periodic pulsations. And you will heard about all of most of this from the next few talks of this and the next session. And I will not go into details of these topics, and you will heard that from the next speakers. Other than those I have mentioned in the last slide, there are some new interesting work that we just dived into. So for example, one is the puzzle of the linear polarization from the solar active emissions, and why it is puzzle that I will talk in the next slide. And recently also we our solar the SHI collaboration also jumped into the some engineering commissioning with the of the solar observation with SK mid precursor MIRCAT, and we are now also preparing for developing the softwares and relevant computational facilities for preparing large-scale solar imaging from the huge amount of solar observations with the MWA that we have. Now, but just to give a brief overview of why it is interesting and at the same point is challenging for solar radio emissions, and why the MWA is well suited for that. So what you can see in this figure is the distribution of brightness temperatures for different kinds of solar radio emissions at the MWA observing frequencies. And you can see the brightness temperature can go from about 10 to the power 4 Kelvin to about 10 to the power of 13, 14 Kelvin. And also the polarization fraction, circular polarization fraction mostly is also varying from less than about 1% for quiet sun to about almost 100% in case of the different solar radio bursts. And not only that, in the bottom panel, the dynamic spectrum of these different kinds of emissions are shown, which shows different spectrotemporal structures. And also the for quiet sun and coronal mass ejections, they also show different different emissions at different spatial scales. So to probe all these things at the same point, we need high fidelity and high dynamic range spectropolarimetric snapshot imaging. And for this reason, the MWA is obviously a well-suited instrument. Now I move to the puzzle I was talking about the linear polarization from the active solar emissions. So from our early testing of the polarimetric pipeline of pair curves, we found that there are signatures of the linear polarization from the active solar emissions. And there are several reasons to believe that these are not coming from the instrumental origin, and that you will see from the next talk by Soham Dey and Puja Majee. But at the about 1960s and 1970s, here are some claims about this linear polarization in solar burst. But after that, due to the uncertainty of the calibration and the instrumental properties of those early days instrument, there are several criticism about those observations. And after 1970s and so on, people just thought that linear polarization is not expected from the solar emissions due to several reasons. For example, if any linear polarization is originating from the solar radio sources, that could be depolarized only within the source region itself, and also the Faraday rotation and the scattering due to the coronal inhomogeneities can wash out the linear polarization. And this is one paper in 1972 that actually put the last pin on the coffin, that we don't expect any linear polarization from any kind of solar radio burst at low solar radio emissions at low frequencies. And after that, solar community just stayed on this assumption, and most of the instrumental calibration for solar observations are based on this assumption. So this actually biased all the studies in some way, and even some very recent studies also assume this that we don't expect the linear polarization at all. But with the pair curves, in the pair curves, we are not assuming such kind of any bias from the solar perspective. We are performing the robust calibration, and which robust polarization calibration, which now allowing us to find the signatures of the linear polarization. Now, the next step is to, because this is a very controversial topic in the solar community, so to overcome any kind of skepticism, we now perform some coordinated MWA and GMRT observations in last cycle, and at the 120 GMRT observes at 125 to 50 megahertz using the GMRT band 2. And we have about 12 hours of handful of good data, and we also found good epochs where there are lots of solar activity and non-thermal emissions are present. But at the same time, the geometry polarimetry at these frequencies are not being explored and not very routine. So it is also a challenge for us to do that. And the main goal is that if we can find the linear polarized emission from the simultaneous observation of MWA and GMRT at the same frequency, same time, then we can sure that these emissions are from not from any instrumental origin, and these are coming from the solar emissions directly. So that will that will convince ourselves that these emissions are not from any instrumental origin. And then the questions will arise to explain the presence of the linear polarization. And one of the mechanisms could be when the circularly polarized emission is passing through the coronal plasma, there could be the Faraday conversion, and that could lead to some conversion from the circular polarization to the linear polarization, and that could lead to the generation of this linear polarization. But this is just a preliminary step. But if we can convincingly proved with the MWA GMRT observation. So that will open a brand new space for investigation using this linearly polarized emissions, ranging from coronal magnetic fields, propagation effects, directivity of emissions, and even the emission mechanism itself. Now, I will switch the gear to some other thing that related to the something about the MeerKAT. So at the although we can probe a large amount of large phase space using the low frequency observation, there are certain limitations. So at the MWA band, we are mostly at this frequency regime where we can probe the coronal heights from about 0.1 solar radii and so. So, but at this frequency, the resolution and is a big problem. And also, if we have an instrument with higher resolution, then still we have limited by the coronal scattering problem. So there is it is hard to unambiguously identify the counterparts of this radio emission in the higher energy bands like the extreme ultraviolet and X-ray bands. And to remove this unambiguity, we need to move at some higher frequencies. For that, MeerKAT is an ideal opportunity. And the MeerKAT observes at this frequency regime about 580 megahertz to about 1 gigahertz and so on. And it's also a good UV coverage and lots of new sites we can expect at this frequency. So to enable that, we have recently started an engineering commissioning of the solar observations. And also we hopefully carry forward this experience with the MeerKAT to the SCAP because that will allow us to simultaneous MWA and SCAP observations, and also the large field of view of the SCAP will help, and also the large number of background sources is useful for the heliospheric studies. So just to give a brief what is the status about the MeerKAT here. So this is kind of the first solar image with the MeerKAT we obtained at 1 gigahertz with 26 kilohertz resolution. And we can see the radio emissions from this part of the solar corona, and there are some active emissions also present. And with the engineering team, we have now carefully identified the suitable attenuation level we need for the MeerKAT solar observations. And we found that all the antennas almost the attenuation of attenuator are almost close to each other for all the antennas, but that exactly not at the not providing the expected attenuation value, but it also had a spectral shape. But we found that these observations and the engineering observations we just recently performed is a good starting point for the MeerKAT. Now, now I will move to another topic where we are now progressing is a NASA-based proposal to build a dataset for AI/ML applications. So it's called the Heliophysics Artificial Intelligence or Machine Learning Ready Data (HARD), and the PI is the MIT hashtag. And so the good data set for this is the full spectroscopic snapshot solar images from the MWA, because that has a lot of spectrotemporal and spatial structures, and so that is a good data set for this proposal. And the workhorse for this we need actually to image a large amount of MWA solar observation, and we all have hashtag VLB HPC more than 1,000 cores for that purpose. Now, just to give our overall plan how we can do this proposal in the reality, that from the MWA archive we want to do that sticking at the POSI, and then using the Birley we want to reduce want to do a channel averaging that will reduce the data volume, and then download that at the haystack. And then we do the imaging using the pair curves on the haystack, and that the solar images and the metadata will be kept at the haystack. But to available that data to the global solar community, we plan to use the virtual solar observatory, which actually keep all the metadata, and any person from the community can request this data to the virtual solar observatory that can give the link to the archive, and that data can be brought to the solar community in that way. So this is just a preliminary plan we have. Now, to explore the possibilities of downloading all the healthy MWA solar fringe-stop data, we now plan to do that at the MIT Haystack MIT Haystack, and also irrespective of, we already have that facility, so that is irrespective of the outcome of the AI/ML NASA proposal. And also recently the NCRA becomes a part planning for a set up a prototype of the Indian regional SK data center. So we also want to propose that to use to download the data at NCRA and to process. Now, in terms of that, we have some feature request and some possibility to explore, that is to deal with the non-contiguous data in the ASVO interface using Billy, that they already told that is in the to-do list. And another thing is important, that if we can extract some specified source channels from the contiguous bandwidth dataset, because sometimes we actually don't need to look at the full 30 megahertz data, and we just only need to focus on some particular course channel. So if we can do that, then the data download overload will reduce. Now, this is the near-term plans presented in 2021 in project meeting. So this ranges from the tools and techniques developments from the different science opportunities, and also engaging with the SK India Consortium for SK Regional Data Center. And at the end of 2022, we are now standing here. This green boxes shows the projects that have completed completely. So for the wings, we have done lots of work, but there are some VCS observations done to study the wing non-thermal emissions. That's still not done, but it is in our plate. We also have some coordinated observation with different space-based observatories for Solar Chandrayaan-2 mission and also the Parker Solar Probe Solar Orbiter. But those data we still need to look at, but all other projects are completed in this last year. And these are the list of publications which are accepted in the last in 2022, and these are the someone related to wings, that weak impulsive non-thermal emissions, and these are the papers related to the PARCers, that is the polarimetric pipeline, and there is one paper with relevant to the AI/ML applications and also related to the wings also, and these two papers are now in the under review. So we have a good number of publications in last year with good works from the SHAO collaboration members. Now I will bring to the summary that we exploring the interesting parts of the solar radio physics and chosen to be well matched with the strengths of the MWA, that is the spectroscopic snapshot imaging capability of the MWA. And our investments in building a powerful set of tools and techniques are now paying off. So we have in a good state of doing this to focus more on the science part, and slowly growing and variable capable science team working with the MWA solar data. And so many, just I presented some of the listed projects that we are currently working on and in our plate, but there are many interesting science projects lined up. So we expected to do that in the coming year. So stay tuned on that. And obviously, we now also start exploring the solar science with the SK mid precursor, that the MIRCAT, that is obviously important for the solar physics and to enable because that will essentially needed for the SK mid operations of the solar physics community. And obviously, at the end, we want to thank the MWA team for their effort and for helping us all the time for doing the observations and all the technical difficulties and so on. So with that, I end here, and I'm happy to take any questions. Thank you.
Wonderful. Thank you so much for that talk. That was great. So we did have one question in chat from Mia. Is it also a possibility to process the data for the NASA proposal at Pawsey instead of the Haystack HPC?
Right. So the pipeline we developed pair cards is now kind of suitable for deployable in any kind of HPC environment. So the point is that for that that we also think about to do that in the POSI, and but the means the large number of members for the SHA collaboration is mostly from the non-Australian group. So we also want to engage with the members from the Australian people, Australian institutes like John and other people. So obviously we are in the plan of that.
Fantastic. And we also have a question from Ramesh, if Ramesh wants to.
Yeah, so my question is probably pretty basic. So you mentioned these plans to sort out the polarization issue by doing simultaneous observation between MWA and GMRT at low frequencies. I'm just trying to understand, is the main puzzle, if I understand right, you had one slide that showed that the circular polarization of solar bursts can be anywhere from a few percent to 100%. Then you mentioned that at very low frequencies, there is no polarization. So is this particular result, is this all coming from low frequencies, or, so this is, my question is around, that where is that circular polarization things are coming from? Is it a primarily low frequency result or other studies of solar burst?
No, so this figure is showing the range of polarization only at the low frequency, not at the high frequencies.
So this is not MWA result?
No, not the MWA results, but it is the expected polarization fraction at the MWA frequency, not at the high frequency. It is about 100 megahertz frequency just reporting. So this is from the all previous studies. So this is just to give a sense how much that can vary. And that depends on the what type of emission you are looking. So for example, different types of radio burst, that is mostly the non-thermal emissions. For that, we generally expect high polarization. And that is why we also try to look at the GMRT data, whether there are some non-thermal emissions are present or not. And we found a good number of data set where we have that non-thermal emissions are present.
Okay, so the most important purpose here is just to compare circular polarization between these two telescopes, right? That's the main thing.
And not the circular polarization. The main puzzle is in the linear polarization, because circular polarization people generally expect from the solar observations, but the linear polarization people don't expect from the solar radio burst, because they will be burst out due to the coronal Faraday rotation and so on. So the main purpose is to look at the linear polarization, but since we have the full polarimetric data, obviously we will also compare the circular polarization. So this is the full polar comparison, not just circular, not linear.
Okay, thanks.
Wonderful. If there's any more questions, raise your hands or forever hold your peace, or at least you can contact after the talk. So let's thank Devojyoti again for his wonderful overview. You'll be hearing from him again in the next session. So now we'll start with Surajit talking about detecting and characterizing weak radio emissions from the quiet solar corona. So if you want to start sharing your screen.
So can you see my screen? Hello, can you see my screen?
Yes. Yes, we can see your screen. You can start your presentation.
Hello, everyone. So today I'm talking about detecting and characterizing weak radio emissions from the quiet solar corona. Devojyoti had just now introduced the term WINGs. So those are what we call these emissions now, which are short form for weak, impulsive, narrowband quiet sun emissions. Before going to those terms, let us start with a brief introduction. And even before that, let me first thank my collaborators here that contributed to this work. So now, as I mentioned in the title, I said these are the emissions from the quiet solar corona. Now, let's first talk about what are active sun and what is the quiet sun. So active regions are mainly regions which have very strong magnetic field, where the magnetic field can vary from several hundred to 1,000 Gauss. So here I have shown a magnetogram of the sun, and inside red circles you see these structures, which are the regions of the strong magnetic field. And these regions are the source of explosive events like flares, coronal mass ejections, etc. So there are lots of dynamics from these active regions. Anything outside these active regions is more or less the quiet sun. And the question is it really quiet? Now, of course, the answer is no, as I mentioned that in the title itself that there are these dynamics. Now, here I give an example of a very well publicized dynamics in the quiet solar corona. So this image is taken from the solar orbiter in the E174 angstrom. So this is the part which has been zoomed here, and you see these small brightenings here and there. Here is one, here is one. So these are the small brightenings which are now called campfires because they resemble that sort of thing. Now, if you zoom into that, you will really see that they are not present, they are not persistent, but they are quite dynamic, which is evident from here to here. Within 2 minutes, it just brightened up. Then you see some sort of plasma motion towards this direction. Many things happening there. Here is the magnetogram of this region. Now, the solar corona is entirely magnetized. The photosphere is entirely magnetized. Depending on the sensitivity, you can see magnetic field even in the quiet sun. But the main difference in active sun, as I mentioned, is the magnetic field is much higher in active regions compared to the quiet sun. Now here you can see there is this positive flux and negative flux. So the negative flux is shown in black and the positive flux is shown in white. Now if you see closely, you will see that the positive flux is slowly decreasing, and they have quantified that here. They have calculated the total positive flux in this white box here, and as you can see that during this time period the positive flux is continuously decreasing. Now this suggests that there may be some sort of magnetic reconnection processes happening here, and all this is just an example of this sort of events. There are lots of these dynamic events happening in the quiet sun have been observed in the extreme ultraviolet and X-ray bands, and these are generally depowered by magnetic reconnections. The question we ask is, can these small-scale reconnections happening in the solar corona also accelerate particles? If yes, can we observe their non-thermal signatures? Also, if these reconnections are indeed accelerating particles, can we quantify the non-thermal energy associated with these accelerated particles? Now, related to these questions, in 2020 we published a work with using data from the MWA, where we presented for the first time evidence for ubiquitous non-thermal emissions from the quiet solar corona. So here I show two figures from the paper where they plotted the histogram of the normalized flux of the sun. So what I mean normalized flux, for every pixel I subtract the flux from the pixel from the median flux for the pixel along the time axis. So I will choose one pixel and take the median along the time, and I subtract the median from the pixel value at that time and then divide by the median itself. So that is my delta F by F here. Now, for a purely thermal distribution, since we expect that the residual after subtracting the median, we should see more or less small fluctuations, and the fluctuation strength will depend on the coronal temperature so we expect some sort of a Gaussian distribution. But here we clearly see that there is a power law tail in histogram. Now this is not expected from a thermal emission. Additionally, if we get the temporal width distribution from the events which lie on this power law tail, if we see that these events are extremely impulsive in nature. Most of these events have temporal widths of half a second, which was the MW time resolution at that time. And on the other hand, the temporal time scales of the corona is order of a minute or so. So this essentially means that all these emissions which we are observing here, they are non-thermal in nature. Here I show and overlay the radio contours on top of an UV image. So this is the active region, but here see these isolated sources here. There are no apparent large-scale structure on the sun in these locations, and they're also impulsive in nature. So these are the sorts of structures we are observing on this power law tail here. Now, in this figure, we have shown the fractional occupancy distribution. By fractional occupancy, I mean for what fraction of observing time do we detect these sort of events at that region. Now, we have this blank region is basically the region where this active region is located, and we have ignored that from this work here. Now, but other than that, we have also ignored the limbs here because there can be effects of scattering as well. But wherever we have actually used the data to identify these emissions, we find that indeed there are these non-thermal emissions present in those regions. So based on that, we for the first time showed that there are these non-thermal emissions which are ubiquitous in the quiet solar corona. As I mentioned earlier, we named them weak impulsive narrowband quiet sun emissions, or short wings. We hypothesized that these emissions are produced because multiple small-scale reconnections are happening throughout the solar corona. Now, those small-scale reconnections accelerate electrons, which can then emit plasma emission. Now, due to the importance of this result, the fact that non-thermal particles can be present throughout the solar corona, we also wanted to understand it in more detail, and we wanted to reproduce our results in different data sets. There were several follow-up studies done for this, and here are some examples which I have given here. Now, one such study, we observed the sun during a much more quieter day than the ones earlier. On this day, there was no active region. There was no X-ray or radio in the entire day, so extremely quiet. And still, when we also improved our analysis from the last time, and the imaging RMS was lower, we did the artifacts in the image were also much lower. And in this condition, we also found that yes, we can detect these sort of impulse emissions. And here again, I show the fractional occupancy distribution just like I showed earlier. And we again see that these emissions are really ubiquitous in nature. So here I have just showed again a contour of a wings on the sun. So just that they are really very compact and localized sorts of emission. Now we can also find that the temporal, they are very short-lived, and most of them have a lifetime of 0.5 second. Is again the instrumental resolution. But there are also some interesting differences which we found. So in this new data set, if we again with histogram of this normalized flux delta F by F, and we put a threshold on, let's say we only will say detection if we if the delta F is larger than 3 sigma, we get this sort of a log normal distribution which is seen here. However, in the earlier work, we found this power law tail, and which is not observed here. Now, this flat part is mostly coming because of completeness issues, which I can talk later. But the most interesting thing is the fact that in earlier work, we found these events which have delta F by F much larger than 1. It can even go to 8, 9 or so. On the other hand, in this data, even when we have much better calibration, imaging artifacts is much lower, we don't see these high delta F by F events. So why don't we see them? On more investigation, we found that these events between 1 to 10, they actually are clustered around the active region. So which is shown in this red, they are clustered around the active region. On the other hand, the wings which have delta F by F less than 1, there is everywhere. In earlier work, we actually had taken some steps to exclude regions which are affected by the emission from the active region. Now, we right now cannot say whether they are actually real emissions in this, and the real active region is somehow influencing the emissions at those regions, that the magnetic field is more complex than the active region, and that's why we are seeing more reconnections there. That's a possibility, which is a physical reason. Or there can be some artifacts which we really don't understand, because we tried our best to eliminate any artifacts from the active region, but this is result. But if we exclude these regions and make the histogram from these blue regions only, we see this sort of histogram which is much more closely resembling the histogram which we see with the new data, which is at a much more quieter time. Now, it's also possible that as the solar activity increases, we see a transition of the histogram from a log normal distribution to a power law distribution. Now, if that is true as well, we do not know. We need to do more studies across solar activity to understand these things. So there are many unsolved questions here regarding wings. Now, but again, another work which
2 minutes, Surajit, 2 minutes left.
Thank you. Another work which we have done is based on we have used machine learning algorithm to improve our detection strategies. So this algorithm can directly detect the wings in the image plane and characterize their morphology using fitted 2D Gaussians. So here is an example of 3 sources which are identified, and you can really see that the distributions are extremely peaked in nature. So, slide. So we hypothesize that these are the weaker cousins of type 3 radio bursts. Now, type 3 radio bursts have classical signature, which is that they drift from higher frequency to lower frequencies. Now, in general, we found that wings are extremely narrowband in nature, but in one instance, Surajit Mondal in 2022 could see this sort of a standard drift signature. So at least in one instance, we are confident that these sort of wings emission are really caused by plasma emission, and they are the weaker cousins of the well-studied type 3 radio bursts. So yeah, quantifying these energetics are very hard, again because they are coherent in nature. There are some estimations based on several assumptions, but they are highly not well constrained. And if we can detect and model the Gardner emission from these transients, we can do a much better estimate. So the Devojyoti said that we are trying to use Meerkat data, and hopefully it will happen. But right now I have used the VLA data to do one such work. So it is the overlay of the VLA data at 4 frequencies on the AIA, and I have modeled the spectrum. The bandwidths are not that great; it's very small, but that's the best we could do at that point. And estimate the non-thermal energy of 10 to 26 args. So to conclude, through multiple works, we demonstrated that non-thermal radio emissions are ubiquitous in solar corona. The emissions are most probably produced due to electrons accelerated in small-scale magnetic connections, so they can be indirect evidence of nanoflares as well. And the energetics suggests that the non-thermal energy associated with these events should be taken into account for calculating the total coronal energy budget. Thank you.
Wonderful. Thank you for that talk, Surajit. Do we have any questions? Mark.
Oh, hi, Surajit. Thank you for your talk. That's very interesting. I have a question about the non-thermal nature. So when you plot the contours of the radio emission over like an AIA image, as you did earlier, I think one can clearly see that from the AIA image, there's a lot of structuring within the beam size. And there's no reason to believe that the plasma there is isothermal. So if you consider multi-thermal plasma, is it more consistent with the emission that you're seeing, and do you characterize that as then non-monothermal instead of non-thermal?
So actually, the main evidence for the non-thermal nature is coming from their temporal bits.
Yep.
So even if I completely agree with you that there is lots of structures in the AIA and it is definitely is not isothermal. But the fact is these structures are very dynamic actually, and if you see here again, most of them have it's of what 0.5 second. Even if we take the maximum 5-6 seconds, is still way smaller than the time scales which you observe in case of thermal signatures, which can be order minute. So that is why this is actually the main evidence behind saying that it is non-thermal in nature. Additionally, for most of these events, we find that they're extremely narrow band in nature. Those two things are the key reason why they are. We say that they're non-thermal in origin. Additionally, if you see this structure here, so I cannot show right now. Devojyoti showed one image. So if it was thermal signature, then they have followed the exact similar contour structure as in the AIA. And one mirrored image Devojyoti showed just earlier, it had similar contours. But here, this sort of very compact source is again not expected from just the thermal emission.
Angie, I don't want to take up the time, but I can have a follow-on question.
No, there's time. You can have a follow-up question.
I think when I talk about non-therm, I mean, yeah, there's the background which looks like it doesn't change, but then the corona is changing all the time at the scales that we're looking here. So and in terms of like alphanic timescales over some distances of maybe a megameter or two, it could easily be, a few seconds or less. So I think it's very dynamic.
So you talked about the Albany timescales, but the thermal signals are changing not in Albany timescale, but in thermal timescale. Thermal timescale is order minute. Anything which you need to just increase or decrease the temperature, that will take order minute. The Albany timescale is small, I agree, but the free emission cannot make this, because free emission will change in the thermal timescale.
Okay, yeah, we can discuss that another time. Thank you.
So let's thank Surajit one more time for the wonderful talk. And now we have Soham looking at a polymetric study of type 3 solar radio bursts. So you can start sharing your screen whenever you're ready.
Yeah, can you see my screen?
Yes, we can. It's all good.
Yeah, thank you. So I'll be talking about our first detailed polarimetric study of type 3 solar radio burst using MWA. A brief outline of my talk will be, first I'll discuss about what type 3 bursts are, how they are originated and their observational properties. Then Devojyoti introduced us to that we should not expect linear polarization from any radio emission from the sun, but we have convincing evidences of imaging detection of linear polarization from this burst, and I'll talk about that. Then I'll talk about the temporal evolution of the type 3 sources and the relationship between the linear and circular polarization from these sources, and then I'll summarize. So starting with the radio emissions from the solar corona, we know that the solar corona is made up of hot magnetized plasma, and most of the observed coronal phenomena are driven by the solar magnetic field. Mainly, one phenomena which drives the non-thermal process is due to the magnetic reconnection, which is that when magnetic field lines which are in opposite sense come close together, they self-organize, they break and reconnect into lower energy state, which leads to an impulsive release of the stored magnetic energy into kinetic energy. And thus this releases the jets of energetic particles through the solar corona. And as these energetic particles move through the solar corona, we get non-thermal radio emissions via different emission mechanisms. So coming to the type 3 solar radio bursts, it occurs when when semi-relativistic electron beams are traveling along open magnetic field lines, and it occurs via plasma emission mechanism. So when an electron beam and its velocity distribution has a bump on tail instability, it can produce Langmuir waves, and it decays to produce radio waves at the local plasma frequency, and it's harmonic. So the plasma frequency depends on the number density of the solar corona, and we know that as we get outer from the solar corona, the number density decreases. So if we look at the dynamic spectra, we get this kind of structures for the solar radio burst. So it starts at a higher frequencies, and then moves drifts rapidly to lower frequencies. And the drift rate is around 50 megahertz per second at 100 megahertz. So they appear as a vertical stripe in the dynamic spectra, and observationally it has been seen that type 3 bursts have very high brightness temperature, and it ranges from 10 to the 7 to 10 to the 12 Kelvin. Coming to the polarization properties of type 3 burst, theoretically the fundamental emission from this burst is expected to 100% circularly polarized. But if you look at this plot in the right, that it is a histogram of the different circular polarized emission from the type 3 burst, and this study was done for around 800 type 3 bursts, and it was seen that although you expect close to 100% circularly polarized emission from this burst, the mean lies at around say 35%. So there is a discrepancy from what we expect and what we are observationally getting. Sometimes the polarization is very low. Also, there are no evidence and expectation of linear polarization from the solar radio emission at these frequencies. I'll talk about it in the next slide in detail. But a thing to note here is that most of the radio polarimetry studies that were done are based on the non-imaging dynamic spectra. So we do not have, any information on the source location of the size from these studies. So coming to the linear polarization from the solar burst. So as Devojyoti was explaining, that from theoretical point of view, any linear polarization, even if it was present, should be washed out due to the large differential Faraday rotation in the solar corona. But from a scientific point of view, the detection of linear polarization is of immense importance because it can be used to constrain the emission mechanism, get an idea about the magnetic field in the solar corona, and many other things. So many attempts have been made to detect linear polarization from solar bursts, and in the early days there were some positive results. There were some positive detections, but soon it was established that that the linear polarization that the people were getting in the early days were more due to instrumental effects and was not coming from the source. But now, since we are capable of doing imaging analysis, of spectropolarimetric imaging analysis, so we have strong evidences to suggest that the linear polarization is not from instrumental origin, but is from the radio wave we are getting, which is incident on the telescope itself. So on the left is the Stokes-I dynamic spectra of a group of type 3 solar bursts. Each vertical stripe is a type 3 burst. And on the right is the dynamic spectra of the Stokes-Q fraction. So the main concern of instrumental effect of polarimetric observation is that the leakage from Stokes-I to other parameters. So, so here you can see that in the Stokes-Q fraction plot, there are structures present. There are various structures present. So if it was a simple case of leakage from Stokes-I to Stokes-Q fraction, we should not be getting a structure in the dynamic spectra. What will be happening is that since the Stokes-Q will be say a percentage of Stokes-I, if we take the fraction, whatever will be there, we'll be getting a constant plot. But you can see that there are structures present, and also there. So, for example, if you take this time, you can see that the Stokes-Q fraction is lesser, but at these frequencies where the Stokes-I is higher, is lower, the Stokes-Q fraction is higher. So there are some few things different from the Stokes-I in the Stokes-Q fraction plots. So this suggests that the structures that the Stokes-Q fraction variation we are getting is intrinsic. So here I will be talking about two bursts from this time range and from this time range. Before coming to that, I have used pair curves, which has been developed by Devojyoti to get high fidelity, high dynamic range spectropolarimetric snapshot images, and we get evidence for linear polarization from the image itself also. So as you can see, that at the same time, on the left is the Stokes-I intensity map, and on the right is the linear polarization intensity map. And from now on, I will call the linear polarization intensity as P. So you can see that at the same time and at the same frequency, there is one source present in the Stokes-I image, while there are two sources which are present in Stokes in P. So if we were getting it from leakage, what will be happening is that we will be getting a scaled copy of, say, Stokes-I to P. But you can see that when there is one structure at the same time and at the same frequency, there might be two structures present in the linear polarization intensity map. So it suggests that it is not a simple case of leakage. Also, then we have also plotted the linear polarization fraction map, and we expect the polarization fraction to be constant over the image if the determining factor is leakage. But what is really happening is that the stroke size, say the peak of stroke size is not coinciding with the peak of the linear polarization intensity map. And so if we, and they are varying sizes also. So if we just plot the fraction map of the fraction of the linear polarization fraction, we are getting, say, a map which is not constant. So since the linear polarization fraction varies across the source, we are more or less convinced that the detected linear polarization is not coming from leakage. Also, we have computed the stroke psi to P leakage before and after type 3 burst, and it was less than 3%, while the linear polarization fraction we are getting is around 20% maximum here. So coming to the temporal evolution of the first group of burst I was talking about. So as I was talking earlier, that we expect that the circular polarization to be very high, and we do not expect any linear polarization. But as you can see from this plot, the blue ones is the stroke psi, peak brightness temperature. The red ones is the linear polarization intensity, and the green ones are the circular polarization intensity. So you can notice that not only we are detecting linear polarization in this case, the linear polarization intensity is actually 4 times higher than the circular polarization. So, and if you look at the area of this of the sources in different stroke plane, you can see that the circular the Stokes V source has a lower area than compared to Stokes I and P. However, it is for other time it is not true, and for many of the time the circular polarized source has lower area, but for other times they might be of the similar area. Then on the left we have plotted the polarization fraction with the time. The red the red markers show the linear polarization fraction, and the green ones is the circular polarization fraction. And if you look at it, we can see there seems to be it seems that the linear polarization fraction and the circular polarization fractions are anti-correlated. So whenever there is an increase in the linear polarization fraction, there is a decrease in the circular polarization fraction, and vice versa. Then we wanted to check that if that is a case for all other frequencies for this burst, and we see here I have plotted the normalized cross correlation with frequency. The cross correlation were computed by taking the mean of the circular polarization fraction and subtracted, and same was done with the linear polarization fraction, and their cross correlations were computed. And you can see that this seem to be anti-correlated over the entire frequency range. And on the bottom panel, it is the average for all the frequencies, and it seems that the circular and the linear polarization fractions show significant anti-correlation. Now I'll come to the second burst, in which the degree of polarization was low. So there we are getting, on the right is the Stokes I in blue, the V and the linear V is in green and the P is in red. And you see that the I have chosen this one to show because there the degree of polarization was low. And you can see that from the plot on the left that the polarization fraction, the polarization intensity for the circular also and the linear are comparable. So coming to the polarization fraction plot in the left, you can see that the circular polarization fraction and the linear polarization fraction seem to be correlated in this case. On the right, you can see that the cross correlation coefficient is really large for this second burst. So for one case, we are getting that the linear and circular correlation fraction is anti-correlated. For some other time, we are getting that the circular and linear correlation fractions are completely correlated. And for other time, we are noticing that different things between these strong correlation and anti-correlations. So we are getting very different relations between the circular correlation fraction and linear correlation fractions for different bursts. So to summarize, there is a well-established discrepancy between the observed and theoretical circular correlation fraction for type 3 radio bursts. We expect the circular correlation fraction to be very high, but the observed circular correlation is low. We have conducted the first detailed full stocks imaging studies of a group of type 3 bursts, and we have the first convincing imaging detection of linearly polarized emission from this burst. And the observed linear and circular correlation fractions for different groups of type 3 bursts show a large variety in their behavior. And the variations in circular and linear correlation fractions show a range of correlations between them, ranging all the way from being correlated to being anti-correlated. Thank you. I'll take questions now.
Wonderful. Thank you so much, Soham. So we have one question from Surajit.
Yeah. Hi, Soham. Thank you for this interesting talk. So I have a question. So you showed in your one of your slides that the linear polarization shows structure within the source, and that there were two sources, right?
Yeah.
Yeah. So in the temporal and in the temporal variations of Stokes P, which source did you use, or is it the full source?
No. We only, for these cases, we only, so what I did was that I fitted only when there was one source present. So for this kind of complicated things, I did not take two sources.
So you did not use these times.
Yeah. Also, so the plot I was showing in that, so it is in the say early phase when the type 3 burst was starting. So
okay.
So actually, so this is the time. So this is 6:13:02.25. At this time, it is the time when the type 3 bursts were starting to happen. So there was signatures in the Stokes image that the type 3 burst has started. But if you look at the linear polarization intensity, in those images at those time, so it has not started yet. So and there was an underlying type 1 noise storm that was going on, and there were two sources that were present in those type 1 noise storm. And in the linear polarization intensity, we were getting signatures of those of the type 1 noise storm. So after after 1 second or so, so this was dominated by the type 3 burst. So we were getting a single source after that. So it is just at the starting of the type 3 burst.
Okay. Thank you.
Thank you.
If there isn't any more questions, I don't think there is any in chat. No hands. We'll thank Soham again for a wonderful talk about type 3 radio bursts. And now we'll move on to Puja, who is going to be giving us a talk about type 2 solar radio bursts.
Thank you.
So you can start your slides whenever you're ready.
Okay. So it seems like I'm not able to share the screen. No, I can't.
Is there an error popping up, or maybe it's because Soham was still sharing his screen when he first started? I believe he is not anymore.
No, it's not allowing me. Can you help me with this?
I believe unless Soham is still sharing his screen, I think it's all done. You just have to click share at the bottom of the screen.
And then
And share either your whole window or your whole screen.
Open system preferences. It's not showing anything.
You see multiple options. You may have to go for the main screen, or just go, the one which shows
It's
the tab
not
screen.
showing me that. It's
The
just
share
showing me.
button.
Oh. Okay, so no. So sorry.
It's okay.
No,
We have
so
plenty
I'm
of time.
using Mac.
So if you're just on the WebEx call, is there just no share button at the bottom of the call?
So there is a share button, and then it's showing open system preferences, and then it is not showing anything after that.
Hi Puja, Devojyoti, can I share and then you can go over the top?
Yeah. So you just
Then I
so
can
this is the you can share, please.
Wonderful. I can see your
I
can see Devojyoti's screen. So take it away.
Yeah. So then I need to every time tell you that change the thing. Okay, fine. Okay. So hello everyone. This is Puja Majee, and today I'm going to talk about the first detailed polarimetric study of a type 2 solar radio burst with the Murchison Widefield Array, and this work has been done in collaboration with Divya, Oberoi, Devojyoti Kansabanik, and Soham Dey. So first I'll start by introducing the type 2 solar radio burst. So next slide. Yeah. So type 2 bursts are plasma emissions which are produced from magnetohydrodynamic shocks, and these shocks can be driven by solar eruptive events such as flares, coronal mass ejections, and so on. Here in this diagram, you can see this are the dynamic spectrum of various solar radio bursts, where the green ones are showing the type 2 emissions. Now, observations have shown that these type 2 emissions appears in few megahertz bandwidth, and this shows a slow drift from higher to lower frequencies at a rate of 0.1 to 0.4 megahertz per second. Whereas these emissions can appear in a fundamental and harmonic level of the local plasma frequencies. So the lower one is the fundamental emission, and the upper green one is the harmonic emission. So studies have also shown that 60% of the coronal type 2 burst shows this kind of structures, whereas the fundamental shows emission which is weaker than the harmonic one. Now each of these two structures shows substructures. Now please change the next slide. Now when these substructures appears in multiple branches, these are called as multiple lanes. Now the frequency difference ratio between these substructures are irregular. Whereas when these substructures appears in two distinct branches, they are called as band splitting. And now there are different interpretations behind what can give rise to this emission length. And for that, let's look at the image. where the green curve is the shock front, and which is being produced from a solar eruptive event, which is here the CME, and the blue and red circles are the radio emissions. So when the emissions are from distinct region of a shock front, they can give rise to multiple lanes. And whereas in case of band splitting, there are two widely accepted interpretations, one of which says that if the one of which is similar to the previous one, whereas the next one says that if there are the two emission lanes can come out from the upstream and downstream region of the shock front, now which is shown here in the box. Now according to these interpretations, the two radio sources should be closely spaced, whereas according to the previous one, the two radio sources may be far apart from each other. Now most of the evidences in literature are, there are more evidences in literature towards the upstream downstream shock scenario, whereas there are very few for the previous interpretation. And one thing to notice is that most of these interpretations are based on non-imaging studies. Therefore, to get the information about the location of these radio sources, imaging studies are important. Next slide. Now the question arises why polarimetric studies of this type 2 burst are important. Now, type 2 solar radio bursts are associated with one of the strongest solar eruptive events, which can influence the space weather. Now, these eruptive events are governed by magnetic field, coronal magnetic field, and polarization studies of polarization properties of these solar radio emissions can give a lot of information about the coronal magnetic field. And not only that, the polarization properties can also gives us insight about the underlying emission mechanism. Therefore, the more detailed and precise measurements you make, the more accurate constants you can put onto the theoretical models that are describing this emission mechanism. Therefore, these polarimetric studies of this burst are important. Next slide. Now, in literature, there are a number of reports regarding the polarization properties of this type 2 burst, ranging from no polarizations to very strong polarization. So early studies have shown that these emissions are unpolarized or weakly polarized. Now lately there are several studies which have shown that the harmonic emission exhibits weaker polarizations, and in a study by Hariharan et al, they found it around 5 to 10%. But these are all most of these are all from non-imaging studies. Whereas one of the few imaging studies by Alexander Kiss et al, they found that the circular polarizations is higher in case of harmonic, whereas it is around 35% in case of fundamental, which is weaker. Now, but as Devojyoti and Soham has already discussed, that so far people accepted that linear polarizations will be washed out from the, we will not get any information about the linear polarization, and therefore in literature no linear polarization has been reported so far. Now, instruments like MWA and its robust dedicated pipelines such as PairCurves have enhanced our capability to do the solar polarimetric imaging with a high fidelity and high dynamic range. Now, PairCurves can provide full strokes images, and using this capability, we have carried out a detailed polarimetric study of this type 2 burst. Now, next slide. Now, this type 2 burst was observed by Learmonth spectrograph on 28th of September 2014, and this particular event has also been observed by MWA. Here, this dynamic spectrum is made by the Learmonth data, where the upper emission is the harmonic one and the lower emission is the fundamental one. And here, this 6 narrow rectangles are the 6 spectral bands of each 2.56 megahertz in which the MWA has observed this burst. Now, the duration of this burst was around 10 minutes. Next slide. Now, this particular event has already been studied by Bhuiyan et al. In 2022, sorry. And so here the upper panel is the layer mount dynamic spectrum, and the lower panel shows the dynamic spectrum, the zoomed in version of the rectangles, which I have already shown you. So here what they have done, that they have assumed that this harmonic emission is showing band splitting, and according that they have pointed two radio emissions along the two emission lanes. Here the circles are the radio sources corresponding to the upper lane, whereas the triangles are the radio sources corresponding to the lower lane, and the straight lines are connecting the two radio sources at a time, and the colors are getting deeper with time. So with Stokes eye imaging, they have found out the location of these radio sources, and they overlaid those information on the ratio image of this event with AIA, and they found that the two radio sources which are at a single timestamp, they are far apart from each other, and not only that, they are also moving in different direction with different speeds. Now, this particular result is not consistent with the most favored interpretations of upstream and downstream SOC scenario. Therefore, this particular event is very interesting candidate to be explored. And we have done the polarization, we have studied the polarization properties of this particular event. And along with that, we have also investigated whether this harmonic emission is showing band splitting or not. Next slide. Now here are the results. So in a study by Vrishnak et al., they have used some criteria to identify band splitting. So they said if the two lanes are showing synchronized frequency evolution, and if the intensity fluctuations are similar, then we can call them as band splitting. So here in the left panel, you can see gradient plot of flux densities. And here the color bar shows the gradient of flux density with time, whereas the blue color is showing the negative gradient, and the red color is showing the positive gradient. So therefore, whenever there is a transition from positive to negative, that means there is a peak. So here, as you can see, that there are multiple places where you can see there are in multiple places there are transitions from red to blue. So again, to get a closer view of this, we have used the MWA and took the same approach. So this is the MWA dynamic spectrum corresponding to one spectral band, and the below one is its gradient plot. So where you can also see that there are multiple places where the red to blue transitions are happening. So therefore, it shows that this particular harmonic emission does not show band splitting, rather it shows something complicated. Now next slide. Now here are the Stokes images. So this is the Stokes eye images with a dynamic range of 3000 at a frequency of 132.1 megahertz and at a time when the type 2 is taking place. Now this red circle is the optical sun, whereas the contours are at 20, 40, 60, 80 and 100 times of the RMS. And I have used the same thing for all of the images that I'm going to show now. So to get information about this particular source, so this is the type 2 source, and to get information about this, we have treated it with 2D elliptical Gaussian. And the next slide, we found that the dynamic spectrum with the fitted flux densities, this is pretty similar to the non-imaging dynamic spectrum with an uncertainty of this has an uncertainty which is less than 6%. Now the lower panel shows the variation of flux density with time for two different frequencies, where you can see that there are multiple peaks in the there are multiple fluctuations with time, and the smallest fluctuation here is larger than 15 times of the uncertainty. Therefore, these fluctuations are real, and it tells us that there are multiple lanes present. Now, what can give rise to this kind of multiple lanes? So the one possibility can be that there are different parts in the shock front, which are giving rise to this lane. And in that case, the radio sources will be far apart from each other. And the study by Bhuya et al., they have also, their results are also consistent with our result. Now please change the slide. Now here, these are the Stokes Q and U images where these show a different, various interesting morphologies where this in the Stokes Q image, there is a positive and negative component adjacent in the place where there was a brighter source in Stokes I. And also in the same position, there is a brighter component in the Stokes Q. And all of these have a detection which is 80 times, which is higher than 80 times of the RMS. Now this Stokes and Q and U represent the linear polarization. And using these two images, we have also find out the P image, which represents the linear polarized intensity. And we found that there are value detection, which is 80 times larger than the RMS. Now this is a pretty high detection of linear polarization. And also one thing to notice is that the fractional leakage in these images is less than 0.5%, and this is consistent with all the images in time and frequencies. Now the next thing. Now we have also fitted that a source, linearly polarized source with elliptical Gaussian, and we found that the flux, and here the dynamics, it is showing the dynamic spectrum of the flux densities from the fitted parameters, and the lower panel showing the fractional linear polarization. So here you can see that the fractional linear polarization ranges from 2 to 4%, and the uncertainty here is less than 0.1%. And as we have already said multiple evidences about why we can rely on this linear polarization, I want to add another thing here is that the fluctuations with time here are very rapid, whereas the fluctuation, the fractional leakage itself is consistent with time. So this fluctuations in this fractional linear polarization can't arise due to any instrumental effects. Therefore, these are reliable. Now, please change the slide. Now we have also tried to find out the Stokes V images, and here we have
2 minutes, Puja, 2 minutes.
Yeah, fine. So here we can see a number of morphologies where we have also seen the positive and negative component adjacent to each other, but in this case the sources are not well fitted by elliptical Gaussian, and therefore we took a different approach. We found only the flux densities for these images. Change the next slide. So here we found that the flux densities corresponding to the negative component are higher, almost 2 times higher than the flux densities corresponding to the positive component. We have also seen that fractional circular polarization in case of the negative component is less than 5%, whereas that is less than 2% in case of positive component. So the negative component shows more fractional circular polarization. Next slide. Now we have also seen also tried to investigate what is the size of these Stokes images. So here this dynamic spectrum shows the deconvolved source size with respect to the PSF of these images, and we found that the deconvolved size is 1.2 to 2 times larger than the PSF. And we have also found that this deconvolved source size is changing with frequency. So higher the frequency, lower the size of the Stokes image, Stokes source. Now next slide. Now to summarize my talk, in spite of being known since more than decades, and in spite of being associated to most energetic events, these type 2s are yet not well understood. And in this analysis, in this work, we have found that this type 2 doesn't show band splitting, rather it shows multiple lanes. Whereas we also found that the circular polarization for negative components are more, which is less than 5%, than the positive component, which is less than 2%. Now, based on several evidences, we have also found that we found a reliable detection of linear polarization of 2 to 4% in case of this type 2 burst, and this is probably the first time we are detecting any linear polarization in type 2 radio burst. Now we have also seen the fractional in the fractional linear or circular polarization, the fluctuations are more than the fluctuations in flux densities with time. And along with that, we have also seen the source size of the Stokes source is changing with frequency. Now, all these results are leading to several questions that we need to answer later. Thank you.
Wonderful. Thank you so much for the talk. Do we have any questions? Yes, Ramesh.
So that's a really interesting talk. I was quite intrigued by your very low leakage measurements, and I was a bit curious because it's a lot less than what we are used to in a few different contexts, including pulsar measurements. So is this something to do with your snapshot imaging of a very bright source, or you are doing something because of which you have a much better handle on the leakage? In one of your slides, you said 0.5% or less as like leakage in circular.
Yeah. So for that, though the instrument has a higher leakage, but as we have already as we have already the model, we can find out, like, we can minimize our leakage. And also, as pair curves is also this is the pair curve which can give us a residual leakage which is around less than 0.1%. So this is because of that, because pair curve is capable of minimizing that leakage to this low range.
Okay, thanks. I should probably read up the paper at some point.
Yeah.
Thanks.
Thank you.
Wonderful. Thank you so much. Do we have any other questions? I do not see any more hands up, and I believe nothing in chat. So let's thank Puja again for the wonderful talk, and I'll hand back off to Mia.
Thanks, Angie, and thank you everyone for the first solar session. That was a really good round of talks, and we will be having another short break for 20 minutes until 2:50 p.m. West Australian time. If anyone would like to check that they can share their slides, I'm more than happy to run through that now with anyone, not just from the next session, but for tomorrow as well, considering we're going to hit the ground running tomorrow. Other than that, see you back in 20 minutes.
I might just check, Mia, if I can share my slides. I think I should be able to, but best if we check.
Go for it.
I mean, if you can see them, that's all good. That's all we need to know.
Can do.
Fantastic. Wonderful. Thanks so much for that.
Welcome back, everyone, to this session of MWA Presentation 2022. So our first speaker I am Ash, this is Venus. We will be chairing this session today. So our first speaker is Devojyoti Kansabanik, and Devojyoti will be talking about recent developments in space weather research with spectropolarimetric imaging using MWA. So Devojyoti, whenever ready.
Okay, so you can see my screen, right?
Yeah.
Yeah, okay, thank you. So hello everyone, I will be talking about some recent developments with the space weather research with the spectropolarimetric imaging with the MWA. And so there are, so in terms of this, what we actually means by space weather? Space weather is determined by the different kinds of magnetic eruptions from the sun. So what you can see in this figure that there are large eruptions of plasma from the sun. Those are mostly called the coronal mass ejections. And also there is a continuous stream of plasma flowing from the sun called solar wind. And when both of them, this magnetized plasma interact with the magnetosphere of the Earth, it can cause magnetic reconnection, and the energetic particles then can enter into the Earth atmosphere, and that can lead to the problems to modern day technologies. So hence we need to understand this the environment in the space that is determined by the sun and these different kinds of eruptive activities. Now, what are the main two physical parameters that are essential or important in terms of the space weather? One is the magnetic field, because that determines, and not only the magnetic field strength, also the magnetic field direction. Because depending on that, it will cause a magnetic reconnection with the Earth's magnetosphere, and that can inject the energetic particles to the Earth's atmosphere. And the second thing is that itself the energetic particles and their energy distribution and so on. Now, the main problem is that there are several observations are done at different wavelengths, but to understand, to measure the magnetic fields and these energetic particles using the remote sensing observations are very challenging and in different other wavelengths. But at the radio wavelengths, since the radio emissions are produced by this generally by these energetic particles, and also the emission is affected by the magnetic field, these two physical parameters can well probed by the radio observations. So in terms of the observables, there are these four kind of observables that generally used for the space weather studies. One is the solar radio burst, particularly type 2 and type 4 radio bursts. And using the ground-based observation, we can use this this radio burst to understand the CME shocks at the core, and also the energetic particles and magnetic field distribution at there. And this we can use up to the 1.5 of solar radii and so on. But if we now move to the higher frequency, higher coronal heights, generally the electron density becomes low and the plasma frequency goes to the low frequency, and due to the ionospheric cutoff, those cannot be observed from the ground. But at this frequency, we can observe the thermal or gyrosynchronous emission from the CME emitting plasma that we call the radio CMEs. And using this technique, we can detect the magnetic field and the energetic particles and other some plasma parameters of this coronal mass ejections up to 10 solar radii. After that, in the heliospheric space, to measure the magnetic field and the electron distribution and electron density, inhomogeneity, and so on, we generally people use the interplanetary scintillation. And to measure the magnetic field, we need the Faraday rotation measurements of the background linearly polarized radio sources. So all these observables combinedly can provide a picture of the magnetic field and the energetic particles of the CMEs from at low coronal heights to the heliospheric domain. So this can be done using a single instrument like MWA, because it has a large wide field of view, so you can observe the background sky at the same time, and also the other two radio burst and the radio CMEs at the same time. Now, but in this particular talk, I will be mainly focusing on the radio CMEs and what are the developments we have in the recent times on this to study the radio CMEs. So as I told that the measurement of the magnetic field in the CME entrant plasma are very difficult. Generally, the CMEs are observed using the white light optical images, as you can see in this figure, and that optical image does not carry any information about the vector magnetic field strength. So there are several techniques that have been developed to estimate the magnetic field strength at the CME shock, but those techniques cannot be used to measure the magnetic field inside the CME plasma. For that, we need the spectropolarimetric observations and there are two kinds of technique that can be used to measure this. One is the circular polarization measurements of the thermal emissions, and another is the gyrosynchrotron emission from the CME non-thermal gyrosynchrotron emissions from the mildly relativistic particles entrained in the CME plasma. And the main challenge is that both of these emissions are comparatively very faint, about 10 Jansky or so in the present, and in the presence of the very bright sun, about 10 to the power 4 Jansky or more than that, it is very hard to detect these emissions. So and this radio CME was first detected using the Nancy radio heliograph in 2001 by Bastian et al. So and this was detected from a very fast CME, but there you can see their spectral coverage was not very good. So they tried to fit the spectra using the gyrosynchrotron model, but due to the limited number of spectral coverage, the estimated physical plasma parameters from this study was not robust. But after that, after this first detection, there were only a handful of studies which could manage to detect these radio emissions from the CME. And here I have shown some sample spectra from all of these studies. And the spectra from the current work using the MWA are shown by these magenta points and these green points. And we can see that we are mainly probing at the lower end of the flux density and also at the lower end of the frequency domain. So this is a study did by Mondal et al. 2020, and this is the first detection of the radio emission from the CME using the MWA. And I'm not going into the details of this study here, but where you can see that this extended radio emissions is coming from the overlaid on the white light coronagraph images. And in different PSF size region, they have calculated the spectra and model that using the gyrosynchrotron spectrum. And one of such example spectra is shown here. Their model and this gyrosynchrotron model have a large number of parameters, but since they only have Stokes I spectra and also so they can only fit these 3 parameters, and other plasma parameters and physical parameters are kept constant and some physically motivated values. But why we need polarimetry? Because what you can see in this figure, I have shown this the dependence of the different plasma parameter, dependence of the Stokes I and the Stokes V spectra on different plasma parameters of this gyrosynchrotron model. So there are about 10 such free parameters, and this and you can see that all of these parameters have some dependency on the Stokes I and the Stokes V spectra. And to provide an independent constraints on different parameters and also to break the degeneracy between different parameters, we need an independent set of spectra that we can get from the polarimetric measurements. And also we need to constrain some geometrical parameters of this gyrosynchrotron model that we can do using the multi-vantage point observation using different space steps in the space. Now here I have shown the second detection of the radio CME with the MWA. So here we have detected the radio emission from 2 CMEs. One is propagating northwards, another propagating in the southward. And these are much fainter, these are comparatively fainter radio emissions. And we have, in this case, we have detected this emission up to 8.5 solar radii, which is the detection of this gyrosynchrotron emission from the CME at the highest heliocentric distance till date. And with the availability of the polarization calibration for solar observation, now we could now detect the, we can emit, map the circular polarization. So here you can see the circular polarization map. For the northern CME, we did not detect any circularly polarized emission. Only we have the upper limits. And for the southern CME, over a small region, we have detected the circular polarization. Then we have extracted the spectra for these different PSF size region for both the northern CME and the southern CME. Red regions are the regions where we did the spectral fitting because we have the multiple data points in the spectra. And these green regions, we do not have more than 2 data points. So there we have assumed some, we made some assumption to estimate the plasma parameters. But as I told that we also need to constrain the geometrical parameters using the multi-vantage point observations. So for this particular event, we have the observations from 3 spacecraft from called SOHO, Stereo A and Stereo B. And SOHO is present close to the Earth at the L1 point, and Stereo A and Stereo B was present behind the Earth. And this allows us to perform a 3-dimensional reconstruction of the coronal mass ejection using the Wayth-led observations. And after that, we perform a ray tracing through this 3-dimensional reconstructed CME structure that actually provides us the upper constraint on the line of sight source depth. That was only assumed in the previous study based on some, and they did not have any measurements from the direct from the observations. Now here I've shown the joint spectral fitting of the Stokes I and Stokes B. The top panel shows the Stokes I spectra and the bottom panel shows the Stokes B spectra. Since for the northern region, we only have the upper limits, we have used that to constrain the model. And you can see that both of these, all of these regions are quite well fitted with the gyrosynchrotron model. But to understand the importance of this polarization, I have shown here the posterior distribution of this gyrosynchrotron modeling. And this brown points represents the Stokes I, the posterior modeling of for the Stokes I and V joint fitting, and this red region, blue points represents the Stokes I only fitting, where we did not use the Stokes V spectra. And you can clearly see that even using the upper limits on the Stokes V spectra provides a tighter constraints on different model parameters. Example, the line of sight angle with the magnetic field, and also the magnetic field itself strength, and also the minimum energy cutoff. And not only that, in the previous studies by Mondal et al, they could only fit these 3 parameters. But in these studies, with the availability of the different vantage point measurements and also the Stokes B spectra, we also fitted we could fit these 3 extra parameters of the gyrosynchrotron model. So this now provide a more robust estimation of the plasma parameters than any previous studies with the Stokes I and Stokes V joint modeling. Now this is about the radio CMEs, and now I just briefly talk about the heliospheric Faraday rotation measurements to measure the coronal the heliospheric magnetic field. But the main challenge is that for the halo CMEs, so halo CMEs are the coronal mass ejections which are coming towards the Earth, and that is the main CMEs which are mostly affect the space weather. So we want to observe them. If we want to observe them, we have to observe them in using the large field of view like the MWA, but in the sun in the field of view also. So the main challenge is to detect the very faint background radio sources in the presence of the sun. So towards that goal, we has a first success in the Stokes I only. So what you can see in this figure, the radio sun is present here, and there are lots of background radio sources we have detected down to the flux density of 4 Jansky, and more than about 80 sources are detected at 80 megahertz. And this image is only made over about 2 coarse channels and over a 2 minute of integration. So that is the first step that we can now detect these background radio sources in the presence of the sun. And obviously we now need to go to the linearly polarized emission to detect, and the main challenge is that the flux density of those sources are much more lower than the Stokes I flux density. But there is another opportunity that we can use, that is the galactic diffuse emission. These are quite bright and also linearly polarized. And another important thing is that they are present everywhere. So that will provide the magnetic line of sight magnetic field measurements almost at different points on the sky. But so in the Stokes side, we can now already detected this galactic plane and galactic diffuse emission in the presence of the sun. But again, to use that for the Faraday rotation measurements, the main challenge is to model this linearly polarized galactic diffuse emission at these frequencies very well. Now I will end up with the summary and conclusion. So we are in a good place of the routine measurements and detection of the radio CMEs, and the availability of the polarimetric calibration now makes this method more robust to estimate the plasma parameters of the CMEs. Now we are now moving towards measurement of the Faraday rotation over the rest of the heliosphere that will provide the measurement of the physical parameters of the CME. But there are several challenges that we need to overcome. First is the good linear polarization map of the MWA frequency, MWA sky, and we already probably have some of these because for the POX observations and results. But for the diffuse galactic background, we need proper modeling of the linearly polarized emission. And another major challenge is the precision in the ionospheric Faraday rotation removal. The reason is that you can see in this figure, the Faraday rotation, the rotation measure contributed by the CME and CME at less than 2 degrees much larger, but when you move to the outer heliosphere, it is comparable to the ionospheric Faraday rotation and ionospheric rotation measure and variation in the ionospheric rotation measure. Hence, to detect this rotation measure due to the CME, we need a precise removal of the ionospheric effect, and that is the most challenging part of the Faraday rotation measurements using the MWA and on other low frequency instruments to use that as a tool for space weather and to measure the magnetic fields in the heliosphere of the CME. So with that, I end here and happy to take any questions.
Thank you, Devojyoti, for that wonderful talk. Do we have any questions for Devojyoti?
Can I ask one?
Yep.
Yeah, that's a very interesting talk, but I have a sort of a question and comment on this Faraday rotation contribution from ionosphere. Most of it is basically stemming from partly our own experience of trying to get pulsar rotation measures using MWA, and also some of the work that we have been doing with SKLO stations. So my understanding is that it's very difficult to estimate ionospheric Faraday rotation reliably from whatever the resources you have out there. But at the same time, for something like this particular CME kind of a measurement, I sometimes wonder if it is really critical, because what you are trying to do is like a measure something, a small source that is crossing your line of sight.
Right.
And if that crossing time is like much shorter than the time over which ionospheric Faraday rotation is going to vary, so all that you are interested is like the differential rotation measure. Say, from that perspective, is it really critical to have that super good handle on ionospheric Faraday rotation?
Right, exactly agree with you that we are measuring a transient event which is much more time variable compared to the ionospheric Faraday rotation. And actually your point is right that since people are concerned about the ionospheric Faraday rotation, but we can do the snapshot imaging with the MWA very nicely. So that actually allows us to distinguish between what is coming from the CME due to this quick passage and what is coming from the ionosphere. I completely agree with your comment. Yeah. Great.
Thanks. And I also found your image with the sun in the field very impressive, because
yeah.
I had no idea that you can go down to what sort of RMS we can get with the sun in the field.
Right. So just to give you an idea that so for example, we just take the GLEAM RMS estimation and then scaled up that value to the increase in the thesis, and our image RMS is about only 1.5 times of that value. So we are close to the what we expect from the. Obviously, we cannot reach the GLEAM sensitivity because the thesis is already high because of the presence of the sun. But if we take that into account and what is the estimated, the expected value, and the image RMS is just about 1.5 times of that. Yeah.
Thanks. Yeah, I think that looks more promising than what I was.
Right. And another thing I just wanted to point out. So this observation is at the lowest elevation, about 30 degrees.
Okay.
So where is the sensitivity is it's comparatively bad.
Right. And this is with a phase 2 extended.
No, this is the phase 1.
Oh, okay.
Right.
Thanks.
Okay. Are there any other questions? No raised hands, nothing in the chat. Okay. I think there is no more questions. And our next speaker for this session is Angelica Waszewski. Angie will talk about identification of interplanetary scintillation observation with the Murchison Widefield Array. Angie, whenever you're ready.
Wonderful. So hopefully you can see my screen.
Yeah.
I no longer can see you guys. So hello, my name is Angie. I am a PhD student here at Curtin. And today I'm going to be talking about a little bit of my project or my PhD project in identifying heliospheric transients in IPS MWA observations. So we've heard a lot about the sun in the last few sessions, and we can probably safe to assume that the sun isn't exactly a calm environment. It's pretty turbulent. There's a lot of stuff happening around it and on the surface and in the corona. I'll highlight 3 specific things that kind of pop out to me. Is first, there's streams interacting. So there's different speeds of solar wind. Obviously, it's not going to be all consistent. So when fast and slow solar wind interact, sometimes they can interact close to the corona and they like mix in with each other, but sometimes they can interact far out in interplanetary space where fast solar wind catches up with slow and creates these kind of shock waves in interplanetary space. There's solar flares. So this is when the magnetic field in the corona gets all tangled up, and then it releases that magnetic energy in a beautiful display of a loop shooting out from the sun. And kind of similar and usually related to solar flares, there's coronal mass ejections. These guys are like the big solar storms. Obviously, we've just heard about it in the past talk, where actual parts of the sun, like the actual parts of corona, gets flung out into interplanetary space and can create some issues on Earth if it hits us, such as geomagnetic storms. It messes with our satellites and our circuitry, but does create wonderful auroras. But something that we want to kind of keep an eye on. And clearly from the number of just GIFs that I have, not even just images, we are constantly staring at the sun in pretty much every wavelength that you can think of. I'll highlight a couple. So we have X-ray, we have GOES, which is actually technically a geostationary. It's like an environmental satellite, but it picks up X-ray flux from the sun. We have optical. So mentioned the last talk was stereo. These are white light coronagraph telescopes, which are staring at the sun, pretty much just covering the photosphere, just like in a solar eclipse. So we've got LASCO, which is on SOHO, and we have stereo, like I said. Then, of course, we have radio telescopes staring at the sun, obviously the MWA, as well as ASCAP, and many, many more that I just haven't mentioned here. But the common theme in all of these telescopes, or all of these observatories, is we're looking really closely at the sun. We're looking directly at it because, of course, we're trying to understand how these solar storms, how CMEs or solar flares or whatnot actually happen right next to the corona, how they eject and how they look. And that's great. That's wonderful. That's what we need to know to actually understand these storms. But of course, the distance between the sun and the Earth is quite large. It's actually a significant distance between the two things. So there's a lot of space for these storms to evolve and change and morph during that journey that it has towards Earth. And thankfully, the universe has kind of plopped a wonderful phenomena right into our hands that allows us to actually study solar storms, or at least the solar wind, further out in interplanetary space, and that is interplanetary scintillation, or IPS. So this is when turbulence in the solar wind, or increased turbulence in the solar wind, scatters and jumbles pretty much our signal from far away radio galaxies, and it ends up being beautiful twinkling in the night sky. So this is actually the Orion constellation, but you're probably not going to recognize any of the points that are twinkling here because they're not stars. They're probably distant galaxies and other wonderful things that we can see in the radio that are twinkling away. I hope that GIF is working because it's quite mesmerizing. I just like watching it. So we are scientists, so we like to put a number on things. So that scintillation, for every single source that you saw twinkling in that field of view, we like to define how much it is scintillating by, and specifically its normalized change in scintillation or its scintillation enhancement factor. There's always going to be some baseline level of scintillation for any radio source, just because the solar wind is so constant. But what we're interested in is when it deviates from that norm, when it starts scintillating maybe less, or specifically when it starts scintillating more. So we take its radio sources, observed scintillation for any kind of specific observation, and we divide it by its expected scintillation due to that ambient solar wind, times it by a normalized scintillation index. So this is just pretty much a study of the source, the astrophysical source itself, depending on its size and what percentage of the flux contributes to the scintillation, which gives the sources quiet sky scintillation, and that gives us that change in scintillation that we want. So a change of a change is what I like to say. So what I've done in the beginnings of my PhD is hijacked the IPS survey that one of my supervisors, John Morgan, led, where he took daily observations of the sun at 6 different pointings, and we're looking 30 degrees away from the sun. So we're looking quite far. It's like 0.8 AU. It's like quite far away from the sun, not very close, but you have it actually in the null. And we take it at 6 pointings, sometimes more. So you'll see there's another 5 circles there, just depending on where the sun is up. You can get some more information. But what I've taken is so I did a blind search of 97 of these observations, which span over 49 days. So I was specifically only looking at 2 of those pointings, just to constrain my data set a little bit. So these observations that I'll talk about are actually taken in mid-2019. So for a lot of people, they'll know that sunspot minima. We're expecting not that much action happening. We're not expecting maybe a CME a week, minimized solar flares. It's just not as active. The sun has its moments, of course. Like I said, I looked at 2 pointing directions. I specifically looked at directly east of the sun and southeast. I just went to the west, and I'm looking at a frequency of 162 megahertz. And of course, like I said, a solar elongation of 30 degrees. So our field of view, this is what a typical G-level plot is. So this is 30 degrees across, 30 degrees away from the sun. You see the color bar on the right there is the G-level. So this is the scintillation enhancement factor, like I was saying. If you have a G-level of 1, that means your scintillation is bang on normal. There is nothing really going on. So you'll see in this field, predominantly 1, you have a couple of sources. Maybe on the edges, you start seeing some elevated scintillation or maybe some lowered scintillation. That's obviously the further away you get from the beam. You'll get a little bit more noise as you travel through. But in the center, you can probably see pretty much 1. Then I continued on in my search of the 97 observations, and I get handed this wonderful observation with 2 definitely distinct regions of enhanced scintillation, and another one on the right there. So this is taken on the 4th of August. I made a note of it in my little notebook of yep, this looks like a fun little observation. It has some enhanced regions. This could be something in the solar wind. It's most probably because we're looking at IPS, but I'll jot it down and have a look at it later. So then I clicked next on in my continuous data set, and this is the next observation. So this observation is taken an hour and a half after the previous observation. It's at the other pointing, so we went from southeast to east, and those same 3 enhanced regions of scintillation exist as well. But now if I kind of hopefully flick through, we should be seeing that they're actually moving slightly. They're actually moving radially away from the sun. So that really gives the clue of this is probably something from the sun. This is definitely something in the solar wind that we're seeing, some kind of region of enhanced turbulence. So I rearranged the sources and blurred them a little bit. So now we're in a different coordinate space. We've moved away from RA and DEC, and now we're in phi and epsilon, where phi is degrees away from solar north to the left, anti-clockwise, and epsilon is the degrees away from the sun. So we'll probably start at 30 and then move on. Well, the center of the field will be at 30 degrees away from the sun. And all they've done is plotted those same sources exactly at their G level, just in this new coordinate space, blurred it out just so we can get a really good idea of the actual morphology of the arcs or those enhanced regions of scintillation. And you'll see there are some big bits of yellow on the outskirts. So obviously there is some small sources or a small number of sources that have that high enhanced G level, but you can see that those 3 main regions still very much exist. Now I have a box around this main region, and what we've done is tried to find the plane of sky velocity of these arcs, because like I was saying, it was moving radially away from the sun, but we'd like a number associated with it. And we find that it is moving at 469 kilometers per second with about an error of 23%. So this definitely seems like something that could be traveling in the solar wind. It's bang on solar wind speed. It's not too slow. It's not too fast. It seems like something genuinely in the solar wind. Now, my first thought was, oh my goodness, we've seen a CME, and I got so excited. But I had to think about it logically. I can't just get too excited about these things. So I did a hunt of so many CME catalogs and also just general like solar flare events. Some catalogs mentioned those, but mostly CME catalogs. So Soham has its own. Cactus is the automated CME detection software for Soham, as well as Stereo has its own, and a number of other ones as well. I took the velocity that we assumed, that we calculated, and made an estimated ejection time of, probably like, it's not a week ago. I didn't get ejected a week ago. It was probably a couple hours. It wasn't a couple minutes. And after searching through all those catalogs, looking at ejection time, the actual position angle, so the degrees away from solar north that this event was, the roundabout speed that it would be at, like the velocity it would be at after accelerating. And I wasn't able to actually find a match of this event that we're seeing with a known CME ejection that has been recorded in these catalogs. This doesn't completely discriminate the fact that it's probably not a CME, that it is a CME, but of course we have to think about it logically. We're probably not seeing a CME. What we think it is, or at least we starting to collect evidence for what it could be, is something coming from an active region on the sun, so possibly a coronal hole. It's probably like a stream interaction region, maybe that we're seeing that fast solar wind interacting with that slow solar wind further out in interplanetary space. But the very exciting, another exciting thing is this isn't the only event that we saw. I saw many more of these strange enhanced regions of scintillation. Some of these around about 30 days before this event that we saw. So maybe it's got something to do with the solar rotation. Maybe we're seeing that same active region, but of course I'll have to put a little bit more work into it, a little bit more detective work to see if that's actually what we're seeing. I do have to kind of mention, just before I wrap up, I've been shouted out twice. This meeting of my ionosphere work has been shouted out. So I did some ionospheric scintillation work in my honors. It resulted in a publication, which was very cool. I've now moved on to IPS, but I thought I'd mention it still here. I was looking at the current ways that we determine the activity level or the turbulence level within the ionosphere using refractive shift measurements that were mentioned earlier, and comparing that with ionospheric scintillation with a technique that we use to study IPS. And there is a clear difference between IPS and ionospheric scintillation, sorry. It acts on different sources, but also acts on a very different time scale. As you can see, that ionospheric scintillation is a lot a longer time scale. But what we found is that the current metrics that measure the turbulence level within the ionosphere actually underestimate the small scale variance or the small scale turbulence in the ionosphere by nearly a factor of 4. So we kind of showed that the current metrics that we have, obviously the ionosphere is a very complex system, and we can't just have a simple model to explain it all. We may need different models to explain small scale variance compared to large scale variance in the ionosphere. But we did seem to show that it does follow at least Kolmogorov turbulence, which is good. Our assumption is correct. If you want to know more about it, I do have my wonderful paper that my wonderful supervisors helped me with. So if you're interested, please give it a read. But with that, I shall end it there. Thank you very much.
Thank you, Angie, for that wonderful talk. So does anyone have any questions to Angie?
I'll leave it here. Sorry.
Yeah. I don't see any raised hands. I think that's it.
There is a raised hand from Devojyoti.
Sorry, Ramesh, I didn't get you. What is
I think there is a raised hand from Devojyoti.
Oh, is there?
Yeah.
Oh, yeah.
Yeah, thanks. Nice talk. So I just want to ask that you compared this enhancement with the CME catalog, but did you actually look at the coronagraph data, whether at that particular time, at that particular location, whether there is something flowing or not?
Yeah, I did actually. I looked at using HelioViewer, that fancy website that they have. I actually looked at a couple of those for over that time scale, and it didn't look like anything like actually ejected. They were very much correct. There's definitely not a CME coming out. I don't know if it was a trick of the mind or if I was kind of like willing it into existence. It did seem like there was some kind of movement, like some streamers or some stream interaction region. I don't know. Maybe that was just me hoping for something.
What is the time of this event?
This was the 4th of August. This was at around 5 a.m. UTC time. Now I'm trying to remember the date that we were assuming it was ejected. I think we were assuming that it would be ejected around between the 30th of July to the 1st of August, if I'm remembering that correctly.
Sure.
But yeah, it didn't seem like anything extravagant happened. It seemed quite calm.
Sure. Thank you.
No worries.
Thank you, guys. I think that's it. No more questions to Angie. So moving on, the keynote speaker for today is Atul Mohan. So Atul will be talking about novel insights and discoveries pertaining to weak solar activity with MWA. So Atul, whenever you're ready.
Yeah.
Okay.
Can you see my slides actually?
Yeah, now I can.
Yeah. And I'm audible, right?
Yes, you are.
Yeah, okay. First of all, I would like to thank the organizers for giving me this opportunity. I am Atul. So I am a postdoc fellow at University of Oslo, Roseland Center for Solar Physics. So my talk, I will try to give an overview about the various avenues of research we were doing with regard to weak solar activity using MWA data. So first, I will give a brief introduction about what I mean by coronal tomography with meter wave imaging when during the time of weak solar activity. And then the next part of the talk, I'll talk about the research avenues which we explored, and then end with the conclusions. Okay. Yeah. So as you have already heard, like solar corona is a hot magnetized collisionless plasma, which is at 2 million Kelvin, and it is hence very bright in UV and X-ray, as you can very well see in this image, which is from a UV a highly ionized ion line image, which is sensitive to 2 million Kelvin. But at the same time, the coronal plasma frequencies and the gyro frequencies, when you look at it, it typically falls in the meter wave bands. And by virtue of this, even a very weak perturbations like weak flares or weak active phenomena, which gives rise to high energy particle beams and which trigger various types of plasma instabilities in the corona, lead to a lot of wave and wave particle resonant processes, because the natural frequencies of the corona falls in the meter wave bands. And these resonant processes actually give rise to a lot of coherent meter wave radio burst phenomena, which is often seen in these kind of meter wave images as bright sources which outshine the entire sun, with brightness temperatures of the order of like 10⁹ Kelvin, which is like 1,000 to 10,000 times or even higher than the background sun. So thus the meter wave imaging is actually sensitive to such kind of even faint perturbations. And in this talk, we will see a lot of examples of this kind. And to give keep things in a perspective, so I'll first give a brief introduction to a main coherent emission mechanism in the meter wave bands, which will be useful to follow the rest of the talk for general audience. So as we know, or as you have already seen, there are ubiquitous reconnection events happening across the corona, and they drive a lot of accelerated particle jets across the coronal plasma layers. And these suprathermal electron beams, as they move along the open field lines, as you can see here, they cause what is called two-stream instability, which you can see here. There is this ambient plasma, which is having a Gaussian velocity distribution. And when you inject this high energy beam into that distribution, you create basically what is called a two-stream instability, or in short, inverted population distribution in the ambient plasma. And this inverted population distribution is basically giving rise to something called a situation like a free electron laser, or a free electron maser, if you want to think of, because we have an inverted population here, and it's a classical analog of a lasing mechanism. And this gives rise to coherent bright radio emission at local plasma frequency and its harmonics. And since the densities in the corona is a function of height, so also is the plasma frequency. And so if we can actually in fact track the electron beam across the corona as it traverses across these isodensity layers in the image plane, if you actually observe, or if you make images at different frequencies across the meter wave band. So the radio source flux usually gives you a sense for the beam energy density, because it's the high energy electron beam energy density which leads to the enhanced flux, which trigger the phenomena and which leads to the enhanced coherent flux. And in the image plane, if you look at the size of these radio burst sources, it gives you a sense for the electron beam cross section, and the position angle of the sources typically give you a sense for the sky orientation of the beams. So you can actually track the beam, the electron beam which is traversing across the corona when you make images like these across different frequencies, and also study their variation in the intensities, or the particle energy densities, or the size, which is the cross section of the particle beams, and also the orientation of these beams. Okay, so here my science interest has been primarily towards the weak energy release events. So why weak energy release events? Because weak energy release events or the weak particle acceleration events actually dominate the flare histograms of the sun, if you look at any study till date. So for example, here, this is a flare frequency distribution, what you're seeing for different energy ranges. And you can see that when you go to smaller and smaller flare categories, the occurrence rates are much higher. So even though individual events are much weaker, collectively they contribute much to the heating of the corona. So 37 years of X-ray flare observations have given us the insight that 90% of these flares belong to something called the micro flare category. And if you kind of distribute these flares evenly across the time frame, you can get that typically there is 1 event per hour. But if you look at the radio dynamic spectrum, even during a very weak active period, like in this case, if you look at it, so this was a very weak active period where there was no flare reported, we can still see that there is a lot of activity that is happening, which is seen as this bright emission features spread across the dynamic spectrum. And if you just keep counting this is just 56 events per minute, which is much higher than what you see in X-ray or EV data. So the accelerated particle beams are kind of quite ubiquitous and it's everywhere. So, but what have been the challenges to study these accelerated particle beams or their dynamics and these kind of weak active events? So the main hurdle has been that when you look at the high energy emission of these phenomena, they are usually quite weak because they are thermal emission, and since these events are pretty weak, they don't cause much thermal emission as opposed to the background. Now, so also they get unreported in the various event catalogs in X-ray or EUV. Now, when you come to radio bands, what is the hurdle? So the main hurdle is that they're easy to detect because of their high fluxes, but then often there are multiple events happening simultaneously on the surface of the sun. So it's highly possible that many of these events are not relating to a single activity or an active region on the sun. So you actually need to have imaging at fine spectrotemporal scales to actually isolate each and every single event on the disk of the sun, so that you can actually track individual events selectively on the disk. So for that, since these individual events can vary in fluxes by a factor of 1,000 to 10,000, so you need imaging dynamic ranges of the order of 1,000 or above to actually study individual events in the image plane. So this has been a major hurdle. The imaging sensitivity and the high dynamic range snapshot spectroscopic imaging part. So what we need to better understand these weak active energy release events is basically high dynamic range snapshot spectroscoping imaging capability accompanied by high energy imaging and magnetogram data, and also detailed modeling, so that we get a complete picture about the plasma dynamics and the associated physics. Okay, so thankfully MWA came up, and MWA is the best suited instrument to do this, because we have already seen it produces high dynamic range solar images at a very fine spectrotemporal cadence and across a wide band, which covers pretty much like 1.1 to 2 arson coronal heights across, like giving us a good view about how the transport and dynamics of these energetic particles and this activity happens. Now, this is a example where we did like imaging for 4 minutes of solar observations, and then we made this dynamic spectrum for the sun. So this is the whole sun dynamic spectrum from the MWA, and what you see here is the image of the sun. It's for one snapshot and one spectral channel. And what we did is like we actually can now place regions or like beams, MWA PSFs across different regions of the sun and make dynamic spectrum for each and every individual beam. So what you see here is like the A1, A2, A3, and Q are 4 selected regions on the surface of the sun. And we can now make dynamic spectrum or the flux evolution as a function of frequency and time for each and every region on the surface of the sun, unlike before. Before, we used to mainly be working with these things, which is the whole sun dynamic spectrum. And we didn't have a way to do like high cadence spatially resolved dynamic spectra. So this is what we call these spreads, the spatially resolved dynamic spectra. And you can clearly see that the activity characteristics is quite different from what we see in the whole sun, because the whole sun, it kind of averages the things out, and we miss out a lot of activity which is pertaining to each and every individual regions on the sun. Okay, so now with these tools and techniques in hand, so I'll now get to the research avenues. So first of all, as I said, the spatiotemporal evolution of accelerated particles is what we can naturally explore with the meter wave bands in the MWA, meter wave band snapshot imaging of the MWA. So here it's an example case where we looked at a microflare event. So to just give you a range of energy. So microflare is what is typically like 10 power 26 to 10 power 29x range. So this was a very weak active region transient brightening event in a EUV. If you look in a EUV sun, so this is EUV sun for you for the same during the same event, and this is where the event was happening on the solar disk. And if you zoom in, you can see that there was a brightening here, and there is this radio contours associated with the same event. And what we did is like we made dynamic spectrum, spatially resolved dynamic spectrum for the radio source. As you can see, it was a 2D Gaussian shaped radio source all throughout the event. And the interesting part is like we see the radio source in the pre-flare phase to the post-flare phase. So if you look at the thermal evolution of the region, so we use the X-ray different X-ray spectral line data, and we computed the thermal energy evolution during the event, and this is what you see. So there was this pre-flare phase where things were like flat, and then there was this gradual heating phase and a flare phase. So we see that there was this fine bright emission features at a few 10 power 8 to 10 power 9 Kelvin, or immediately telling you this is coherent emission. And this accelerated particle driven coherent emission was, and that activity was going on even in the pre-flare phase. But we see that in the thermal energy spectrum, it's like pretty flat. And what you see here in the red is actually a frequency averaged flux evolution plot. And what you see in the black here overlaid on that is basically a running mean filter to bring out, which was intended to bring out any kind of variability timescales within the event. And you can see that there are these nice pulsating quasi-periodic pulsations which are underlying there. So which basically tells you that these fine burst-like filaments are not happening like in a random manner. There is some sort of bunching which is happening in them. So there is some sort of periodic excitation of these fine particle acceleration events. So here, this is the same thing. It's the same plot, just that I removed the red plot. So to better show you these QPOs or these bunched particle acceleration episodes. So you can see that the green lines are basically spaced at 30 seconds. And this clearly brings out that there is some sort of a quasi-periodic excitation of these fine bursty filamentary particle acceleration events. And that periodicity is at a period of some sort of 30 seconds. So now we explored like, okay, what are these fine features first of all? So they are, we know that they are coherent emission, so they must be triggered by these particle accelerated beams coming from reconnection events. Now their timescales were a few seconds of the order, and that very well matched with what is the expected collisional damping timescale. So they must be these accelerated particle beams which are damped in the ambient corona and must be dumping energy in, and which is basically giving you this nice microflare activity there. And these, we also estimated the speeds, which are typically like 14 to 17 megameter per second. And from the frequency extents, you can actually assume a density model and then get the typical scales of these acceleration regions or the damping regions of these beams. And that comes to around like 7 to 8.5 megameters. And interestingly, in a recent simulation, this is a purely simulation result here. So this is a coronal loop simulation where they actually, Frogner et al. 2020, they actually looked at the accelerated particle dynamics as well. And they found that the typical scales of these particle dynamics, which you see in these blue strands, are of the order of like 10 megameters, 5 to 10 megameters, which is very much agreeing with what we have from the simulation, from the observations actually. So now coming to the 30-second periodic excitation timescale. So what does that typically mean? To understand that, what we did was a magnetic field extrapolation for the region where the active region transient brightening was happening. This is the X-ray image of the active region transient brightening event seen in EUV. So we did a magnetic field extrapolation of that, or magnetic field analysis, and then we found that in the radio source height, the magnetic fields are typically like of the order of 5 Gauss, which gives you a alpine speed of around 0.4 megameter per second, since corona is magnetically active or magnetically driven. So this should be the typical speeds of dynamics in the system. And this gives you a typical alpine time scale, alpine length scale, given the time scale of 30 seconds to be like 12 megameter. So when you look in the UV images, which give you high spatial resolution, you can see that this is typically the twist scales in the magnetic field loops. So probably there is this dominant twist in your magnetic field loops at these particular scales, and there was some sort of probably a disturbance which was traveling across these twist scales and was giving rise to periodic avalanche of particle acceleration events to dissipate the excess strain which is built up across the twists. So that's the kind of physical model which we came up with. Now coming to the next avenue, which is basically exploring critically twisted magnetic loops. As you already saw in the previous thing, so the coronal magnetic loop is not something which is like very well behaved, like connecting from a north to a south in a very well defined fashion. It always has a lot of twists and turns in it. So to give you a picture of why this is so for example, this is a vertical scale goes up in height. So you have the corona, photosphere, and the convection layer below. So the convection layer plasma is highly turbulent, and it keeps moving and turning and moving around magnetic fields as well as it does its convective motions. And in the process, what you get is like if you start even with uniform magnetic field loop, you will end up with a lot of twists and turns. And it builds up a lot of magnetic stress in the system, which is released often by the reconnection events. So there was an interesting simulation done by Godowski and Browning, where they showed that how a magnetic field loop, which starts out very uniform, it gets highly twisted up, and it goes into something called a very critically twisted phase, where it tends to undergo a series of reconnection events across the loop to basically untwine the loop and give it a more ordered configuration in the end. And this process usually is followed by a series of particle acceleration events and also associated heating. So they also gave us interesting results with respect to particle distribution. So as you can see here, when it is in a critically highly twisted state as above, so the particle distribution also has these weakly patterns. So as it relaxes, the particle distribution also follows some sort of the magnetic field structure, and it also gets relaxed. So interestingly, so there is this spatial distribution of particles which carry the imprint of the magnetic field at every period of time. So we can probably, since radio observations are sensitive to this accelerated particle beams, and these accelerated particle beams are actually produced from these kind of particle distributions, we might have sensitivity to how these magnetic field dynamics, which is also changing, because the accelerated particle beams are actually coming from these twisted or crazy magnetic field distributions as well, right? So what I did basically is that in the previous part, I showed you how the flux density evolution of the microflare associated radio source was varying. So you can just not only look at the integrated flux density evolution and make the spatially resolved by dynamic spectrum, you can also make the dynamic spectrum for how the structure of the source also varies. So what we did is like we had this 2D Gaussian source, so we fitted a 2D Gaussian structure to each and every source we found across time and frequency, and we explored the evolution of the source sizes across time and frequency. So now here what you are seeing is actually a snapshot, actually a spectral slice data from a mid-band actually, so mid-band of the observations as a function of time. So how the source area, which is actually the area of the Gaussian 2D Gaussian source on the sky, and the integrated flux density is the integrated flux density itself, and the position angle is the position angle of the Gaussian. So these are plots of how these three parameters, the structural parameters of the radio source vary. So the red one is the, like I said, the integrated flux density, which already shows this 30-second QPOs imprinted, which we already saw that it has this periodic particle acceleration. But along with that, it also shows pulsations in the source areas and source position angle, where area is the proxy for the accelerated beam sizes or the accelerated beam cross sections, and position angle is the orientation of it in the sky plane. So we find that even in the pre-flare, post-flare, and the flare phase, there are these nice pulsations in the blue and the red, blue and the green curve, which is the area and the position angle, which is the structure of these sources. So now to get a better picture of what is going on, what I did is like a normalized cross correlation analysis, where I did integrated flux density and area cross correlation, and what you see on the right is area and position angle correlation. So here in the area and integrated flux normalized cross correlation, you see that in the pre-flare phase, there is no much signal there. There is no much strength in that. But in the area and the position angle phase, so if you do the cross correlation there, you find that there is a strong correlation. So in the flare phase, we find that there is this strongly correlated variability in area and position angle. But at the same time, there is also a new mode of correlation which is coming up, which is the area and integrated flux anti-correlation. And in the post-flare phase, you don't see signatures of the area and position angle correlation in the sources, but the S mode or the area and integrated flux density anti-correlation prevails. So there are these two modes of structural QPOs which you see in the radio sources, which is a area flux anti-correlation, which is like a sausage mode, which is drawn here. Probably like so if you have a twisted loop structure, and there is also not just the twisted structure but also more relaxed ones like these. So and if in these relaxed modes can have something like a sausage wave or a sausage mode vibration, which is like this, where it goes like squishy and like a squeezing mode. So in that mode, you will squeeze these reconnection regions a lot when you go to the squeeze mode, and in a less squeezed mode, it is more relaxed. So this is a picture of a sausage mode, and the T mode is probably something like this, which you see down here, which is like a loop which is highly twisted. So it can have only one way of oscillation or a vibration, which is like a twisting and a winding and an unwinding mode, where in a highly wound configuration, you will have a theta minimum in of the cross section here, and in a loosely wound mode, you will have a higher opening angle or a higher theta, and also higher area for the electron beams which are coming from the reconnection joint. So a T mode could be a signature of a highly wound system, where like dominant mode of vibration is probably in the T modes. There is dominant energy there. And during the flare phase, somehow we find that it's not highly probably twisted. It's the magnetic field loops are also relaxing, as we saw in the simulation, where they were saying that the magnetic field undergo reconnections and they kind of relax. So that gives way to formation of more of these relaxed magnetic field lines, where you can now accommodate sausage mode like oscillations, and that could be why we see the S mode. And in the post-flare phase, the highly twined T mode oscillations are not seen. It's probably much more relaxed loop. So we find that there is this significant mode conversion in the radio burst source morphology evolution from a dominant T mode to S mode. So as I again said, so the T modes could be signatures of these highly twisted magnetic loop structures, where the electron or the particle distribution functions are also in a highly twisted configuration. And so if you accelerate beams in this configuration, you should be getting something like a beam which is also varying with regard to these twists and turns which is happening there. And then as the loop gets relaxed, so you distribute energy, the excess magnetic strain energy, to other modes of oscillations in the system, which is possible, which is now the more relaxed sausage-like modes, which you see as a rise of the S mode. And then finally, in a completely relaxed loop, you don't have much twists and turns, and you end up with the dominant S mode. So an interesting thing is, like, if you want to explore these kind of dynamics in a internally twisted magnetic loops, it's difficult with high energy observables, because as I already said, the high energy observables are often very weak. And the other observable is actually the microwave gyrosynchrotron emission from these accelerated particles. But even that needs a significant amount of accelerated particle distribution to give a good significant gyrosynchrotron output, which is also often weak in case of these kind of micro flares or nano flare regime events. So meter wave emission but at the same time gives you a novel technique to possibly track the evolution of these internally twisted magnetic loops. So this is a potential new way to explore the dynamics of these twisted loops, which otherwise is not possible. So yeah, so besides that, the next thing which I would like to touch upon is actually exploring the coronal turbulence. So we already heard how we can explore turbulence in the solar wind using IPS and stuff. But now what I'm going to talk about is like how we can probe the turbulence or the density fluctuation index much closer to the sun, and also in a much more routine way. So for this, we use the idea that the radio waves are, since they are formed very close to the plasma frequency cutoff, so they are affected also by propagation effects due to scattering. And often in a highly turbulent medium, the scattering of the radio waves actually give rise to something like a diffusive growth of the radio burst sources. So if you look at the radio bursts sources from the start of the bursts, often you see and if you track the evolution of the 2D area on the image plane or the 2D Gaussian size areas, you can see that there is you often find that there is a linear growth in the area, like you see in this plot. The red points are actually from observation and of a type 3 radio burst, where we saw that the radio burst source was increasing in its area in the initial phase. And this rise is basically due to the scattering in the medium. So it's like a diffusive propagation or a random walk propagation of the radio photons or the radio wave across the corona. So by modeling this rate of rise, you can actually get a sense for the density fluctuation index in the medium. And this is a reference where interested people can go and check. So this is a reference which gave a frame of work to a frame of a frame to work on, and how to use this area growth rate and infer delta n by n, or the density fluctuation index. So we employed their model, and then we inferred this density fluctuation index much closer to the sun. And with MWA bands, you can actually go from 1.2 to 2 solar radii and use these weak radio bursts and their start period when they show this kind of area growth, and then use the rate of area growth and get the density fluctuation index. So I also recently extended this to the entire MWA band from 80 to 200 megahertz. Unfortunately, there was not much happening beyond 160 megahertz, but I got a good coverage from 80 to 160 megahertz range in a picket fence observation. And this similar technique was employed there, where you can see like this is integrated flux density evolution during a radio burst. And this is the area evolution dynamic spectrum of the same event. And this was made by spatially resolved dynamic spectrum and then fitting the radio sources with a 2D Gaussian. And this gave rise to this nice plot where you can now estimate like the density fluctuation index in the inner corona from something like 1.5 to like 1.8 solar radii. And I also could derive this was a power law fit to the evolution, and the power law spectral index is around like 2.2. And what you see below is basically the saturation, theoretical saturation cutoff in the dashed line. So this is again from the model. So if your estimated fluctuation index is higher than the theoretical saturation cutoff limit, so it means that you are in a strong turbulence regime, so or a strong scattering regime. So this shows that during radio burst events, so we are already in the strong scattering regime or a strong turbulence regime where radio waves kind of propagate in a diffusive manner, like in a linear growth. Okay, so now coming to the conclusions. So I have shown you that I think meter wave high dynamic range snapshot spectroscopic imaging offers a unique powerful tool to do coronal tomography and explore the evolution of high energy particle activity across the coronal layers by doing spectroscopic imaging at a high cadence. And we can thus track the evolution of accelerated electron beams across the corona and study the spectrotemporal scales of particle acceleration in various environments. The radio sources associated with these accelerated electron beams are found to show structural quasi-periodic oscillations as well, along with their quasi-periodic accelerations in the quasi-periodic pulsations, along with their quasi-periodic pulsations in the intensity, which gave a new way to probably explore the magnetic field dynamics by looking at the modes of variability in these structural quasi-periodic pulsations. Then finally, we also have a new way to estimate inner coronal turbulence using the different bands of MWA and observing the radio burst area or the size evolution as a function of time. And thus we can routinely explore turbulence in much closer heights to the sun. So the outlook would be like, these are only examples from 1 or 2 events. So we need more data for various type of solar activity and to do more statistically robust analysis of these various phenomena and how they vary in their nature across activity types, like maybe flares, like eruptions, etc. So now we have only for a very weak non-eruptive event. So we have to have more exploration across the different types of solar activity and across multi-wave band, and use multi-wave band data and models to constrain the physics of what is going on. Yeah. So thank you.
Thank you for that very informative talk, Atul.
Yeah.
Do we have any questions for Atul?
Can I ask one?
Yeah, Ramesh, you can go.
Yeah, it's a very interesting work, but my question is quite simple. But for non-experts like us, can you say a little bit about what is driving that 30-second time line in for QPPs? What is it related to?
Yeah. So maybe we'll go back to that slide. So this one, right? So these fine structures, what you see, like I said, they are individual particle acceleration beams. So now these 30-second QPOs are actually like the timescales in bunching of these particle acceleration events, right? So we find that the particle acceleration events are not happening in a random manner. There is an inherent periodicity in exciting these. So when you look at the X-ray image here, so this is the soft X-ray image of the region. So we find that there is this twisted loop structure happening, loop structure there. So like I was saying in the later slide, so there can be this magnetic loops can get highly twisted. So this twist scale is around 12 megameter, which is which we find to be which we find to be similar to like the length scale if we compute from the 30-second periodicity. So we think that this 30 seconds is some sort of a excitation time scale or some sort of an avalanche excitation time scale in a way. So you can build up magnetic stress across this loop within this alphane time scale, right? So that's the time scale when magnetic field in which magnetic field works in a way, right? So That's the Alfvén time scale. So in that Alfvén time scale, you can build up stress across the loop, and that becomes critically unstable, and then it triggers this avalanche of particle acceleration across the region. I think.
Would that be the same timescale for all QPPs when you have multiple other events? Would that be the similar timescale?
But again, that depends, right? So that depends on the loop length and other features, I would say. Like, so this loop, in this loop, this was the twist scale. So we don't know how it would be in the other cases, right? So.
Yep. Thanks. Yeah.
Okay, any other questions? Okay, no raised hands. Nothing in the chat. I think that concludes our session for today. Thank you so much for all our speakers this afternoon. I will hand you over, guys, to Mia.
Fantastic. And yeah, I'd like to repeat my thanks to all the speakers and the session chairs for today. I just had the one final thing to mention before we sign off. It's a reminder that our website has a new look, so please check it out and let us know if you have any feedback. Information for astronomers can mostly be found on our wiki. And if you're an MWA member and you don't have login access to the wiki, please let me know and I'll sort it out. I can be contacted through the website or directly at info@mwatelescope.org. So thanks again, everyone. We'll reconvene tomorrow for the transient sessions. So until then, goodbye.